ये दिख मुझे। अच्छा देखिए, good morning everybody. We are going to have a marathon class today for 6 hours. I hope you can all see me and you can see the slide as well. If there is problem in the voice or the visual, then you can tell me in the comment section. Almost till around 4 o'clock, with a minor break in the mid, we'll continue the session. The whole of science and technology may not be completed today, so we'll have another marathon session next Sunday. Next Sunday we'll take 3 more chapters, and 3 chapters we'll do today, and next time we'll do more questions in the next marathon session. So let's see how much we can do today. We'll start from space science, then we will go to defense, and then the third chapter will take us biotechnology. Then ICT, nuclear science, nanoscience will take up next week. Okay. So let's start with the space science. First, I'll give you a very basic foundational concepts, and then we'll quickly switch over to the current affair updates. Okay, you all may be knowing it, but it will be a good revision if you sit back and just listen to some of the basic foundational concepts that will make the discussion later on easier and smooth. So before we jump to the current affairs, let me tell you a few things. Ever since India has launched Aditya L1 mission and has become operational, L1 and other Lagrange points have become very crucial. So there will be certain basic science I'll tell you before we will be doing current affairs. Lagrange points. This is the first thing I'm going to tell you. Lagrange points in space, between two heavenly bodies, there are 5 Lagrange points. Like between Earth and Moon, there'll be 5. Between Earth and Sun, there'll be 5. Between Mars and Earth, there'll be 5. If we have 2 heavenly bodies like this, so suppose Sun and the Earth, there'll be 5 Lagrange points. This is important for prelims. Whatever is important and relevant for the exam, we will do only that. So whatever the discussion is happening, take it very seriously. If you have doubts, you can request for a re-explanation. You can ask questions. Be active. If I ask questions, then reply. Be very active, very agile for the entire 6 hours till 4 o'clock. Lagrange points are 5 of them, and they are placed like this between 2 heavenly bodies. Like for example, between Sun and Earth, we call it L1, one that is facing the Sun 24/7. If something is at L1, then that is facing the Sun 24/7. There's a Lagrange point L2 behind the Earth in the Sun shadow region. So L2 is not having the sunlight directly. L2 is cool, L2 is dark, L1 is lit by the Sun 24/7. So L1 is a point from where Sun can be very suitably studied. There are other Lagrange points. If we can see, L3 is very far away, very far away. So there's no mission at L3. The distance between Sun and the Earth, just for reference, is around 150 million kilometer. And L1 is very close to Earth. Of the total distance between Earth and L1 is 1% of the distance between the Sun and the Earth. The distance between Sun and Earth is around 1.5 million, 150 million kilometer. 150 million kilometer. And the distance of L1 from Earth is 1.5 million kilometer. So this point is very close to the Earth. L1 is very close to the Earth. Similarly, L2 is behind the Earth in the Sun shadow region, and that is also almost 1.5 million kilometer. L3 is far off, very far away. To communicate from L3, if we send something at L3 from Earth, will be very difficult. And nonetheless, L3 is an unstable point. L4 and L5 are highly stable. L4 and L5 are so stable that something enters here, it does not exit. It is very stable. Let me give you an analogy that will make things even more clear. Imagine a bowl shaped like this. Imagine 3 of them, and the third bowl upside down. If you place a marble inside the bowl, and if you displace it, it will come back. If you displace it this way, it will come back. So the marble is in a very stable equilibrium. This is a very stable equilibrium. If you disturb the equilibrium, then the marble will come back. That is like L4 and L5. Things at L4 and L5 are very stable. So they move and they come back at L4 and L5. This is how things are at L4 and L5. So many of the asteroids have accumulated at L4 and L5. They don't leave that region. Like a little disturbance will not have the marble leave its center. It will come back. Stable equilibrium. L4 and L5 are like this. So the asteroids there, once you get there, you get stuck. So it's very crowded. And anyways, it's also very far away. So there is no mission. There is no space mission at L4 and L5. L3 is like this. It is there. If you can manage to keep a marble at the top of an inverted bowl, it may stay there. Like in a little disturbance will have it rolling and it's never coming back. This is highly unstable equilibrium. And L3 can have a representation like this. L3. Now, what we have at L1 and L2 is like this. You have the marble at the rim, and if you have the marble at the rim, the marble can stay on the rim if it is circulating. You know, circular motion brings stability. Like the bicycle will fall, but if you have bicycle in a circulatory motion, or if you have a linear motion, even if it is tilted, you have the stability. You have the stability in the well of death. If it is moving, you have stability. If it is a circular motion, then that is stable. So the bowl, if kept like this and the marble is rotating or revolving around the center on the rim, it could be stable, but this is not a very stable. So that is also thermodynamically, in terms of physics, called as unstable equilibrium. This is unstable equilibrium, but the stability is only as long as you can maintain the right circulatory motion. This is the scenario. This is the scenario at L1 and L2. You have to know this. Why? Because we have a very important mission, our first solar observatory, dedicated solar observatory at L1, Aditya L1. And because of that, whatever is at L1, the concept of L1, the concept of Lagrange point in general, they all have become very, very important. So this is how it is. This is how the distribution of Lagrange points are. So you can see there's a space mission. Now this is representation of James Webb Space Telescope. This is having a circulatory motion. So at whatever is at L1 or L2 is not fixed, hinged on a point. It's moving, it's rotating like this. So that's how you keep things at L1 and L2. And L1 and L2 in terms of physics are unstable equilibrium. You have to know that. Because they can give you this statement in the MCQ. Just because we are sending mission at L1 and L2, it does not mean they are very stable. In terms of physics, they are still unstable. An unstable equilibrium is at L1 and L2, but it's manageable. It's manageable because of the motion of the space missions. So the 2 points of interest are L1 and L2. Now you tell me L1 and L2, oh, how will they be beneficial? If I have to study the sun, which point should it be? L1 or L2? That's pretty basic. That's very basic. If you have to study the sun, then you can study it from L1. Now let me ask you some very basic questions and see if you can answer them. If I have to study the sun, then why should I send a mission at L1? Why can't I simply study the sun from the surface of the earth? What do you think? Can the sun adequately be studied from the surface of the earth? Yes or no? We can see the sun from here, and we can see the bright sun in the clear sky and all the insulation and heat coming from the sun. We can feel it. You can feel the warmth of the sun in the daylight, and you can see the sun with your naked eyes. So can we study the sun entirely from the surface of the earth? And as you may understand, the answer would be A hulk. No. The answer, as you said correctly, is no. No, because everything from the sun does not reach the earth. If it would have reached, we would have been dead. If all the gamma rays and the X-rays and all the ultraviolet reaches the earth, then we would have been dead. So this discussion would not have been going on. We cannot study from the sun because radiations from the sun do not come on the earth, all of them. What comes is visible light and infrared and microwave and radio wave. These are lower energy radiations. But the higher one, atmosphere, protects us. So everything from the sun does not come. The ejection, coronal mass ejection, the solar winds, they do not come. Magnetic field lines protects us from there. Gamma rays, how are we protected by gamma rays? The high energy of gamma rays that's utilized for ionization of nitrogen and oxygen in the atmosphere. And that's how we have ionosphere that you study in geography, ionosphere. Ionospheres, they are formed by the ionization of nitrogen and oxygen. So gamma rays is absorbed, the energy is utilized in making the ions. So gamma rays does not come. Same goes for X-rays. And the ozone layer that absorbs the ultraviolet. So we are saved. It's coming towards Earth, all of it is coming. But it is not coming on the surface, atmosphere, and the magnetic field lines protects us from the harmful radiations, harmful to the human body, that's coming from the sun, and allows the helpful ones to enter inside. That's how it's all arranged. So if you want to study the sun, it's at high temperature, and if you want to study anything at very high temperature, anything at high temperature will release energy at high frequency. They will release gamma rays and X-rays. Those are of your interest if you want to study the sun, but they do not come on the surface. So visible light is coming, of course, so you can study from it. As much limited study you can do that. Radio wave is coming, of course, you can study that. There are many telescopes which are terrestrial, they all work in radio wave frequency. So, but you cannot study in other ranges. So surface, no. Then the second best place is to go to the outer space, go to the low Earth orbit, go to LEO. So you cannot study it from surface adequately. And LEO, low Earth orbit, so you can have orbits around the Earth, and from the orbit you can study the sun. So whatever is coming from the sun do come on the low Earth orbit, much above atmosphere. Everything is there, all the solar winds and all the solar storms and all the radiations, it's all coming up. But you can study, and in fact there are many astronomies in the low Earth orbit to study the sun. Hubble telescope was also in the low Earth orbit, no problem. Problem is that you cannot have a 24/7 visibility, because if something orbits around the Earth, then it will cross this arc behind the Earth away from the sun in the sun shadow region. So if something is going round and round all around the Earth in the orbit, it cannot have 24/7 visibility of the sun. So it cannot study it all the time. So if you want continuous monitoring, continuously, I want to see at what time the solar radiation comes and what are the phenomena building up for the formation of CME, coronal mass ejection. I want continuous monitoring. That cannot happen from LEO. So then that's the only option. You have to send your mission at L1, and advanced missions to study the sun is at L1, and we have our first. They have it. European Space Agency has it and NASA has it at L1. They have it since decades. We have sent Aditya L1 at L1, which is a major mission of ISRO. So all of it becomes important, and things around it you have to know. So that's about L1. Now you can also see L2 here. So L2 will be utilized perhaps for studying what? L2 is not a good place to study the sun, most definitely, because you can't see the sun from L2. If you can't see the sun, then what can you see? What would happen at L2? Meaning, for what purpose perhaps, if you can tell me, we will send the missions at L2. L2 is cooler. L2 is darker. So cool means high energy radiation is not coming. So X-ray is not coming, and gamma ray is not coming, and X-ray is not coming, and ultraviolet not coming. So, but this place will have other radiations. We'll have radio waves and microwaves, and also we'll have infrared. Infrared waves will be there. And if you want to study the universe from in the infrared region, then your best choice is L2. Best choice is L2. Like for example, do you know that the most powerful telescope currently is James Webb Space Telescope? But prior to James Webb, the most powerful telescope was Hubble. But you didn't have Hubble on the surface of the earth. We have many telescopes. We have this year's budget also has given allocation for terrestrial telescopes. We have many telescopes in Ladakh. One of the best places that gives clear skies we have in Ladakh. Telescopes are terrestrial as well. But Hubble telescope was not terrestrial. Hubble telescope was in LEO, was in the low Earth orbit. So if you may tell me, try to think about it. Why the Hubble telescope was in LEO? Why not on surface of Earth? LEO is not very far away. LEO is just 400, 500, 600 kilometers away from surface of Earth, and you're studying millions of kilometers from your telescope. So this difference of 400, 500, 600 is nothing compared to the range of the telescope. So why not on surface of Earth? Because I'll tell you, I'll give you all the answers. If you can't answer, at least keep thinking and be fixated on the questions. And gradually the build-up will explain all the current affair topics, these teeny-weeny basic things that we are discussing in the beginning. You have to know that everything that absorbs radiation also emits it. So the sunlight coming to the earth, everything is absorbing, the tree and the water and the mountain and the animals and the humans, everything is absorbing the sunlight, will also emit it. Otherwise it will keep on getting heated. So after absorption there is emission, and emission from the earth and substance on the earth is an infrared region. So the earth emits in the infrared region. Of course, if we would emit in the higher radiation, we will be dead again. Infrared, so it can't be emitting gamma rays or X-rays or ultraviolet. It is not emitting in visible range, even lower energy than visible, infrared. Earth emits in infrared, it's not visible, lower energy, but you see, you feel that in summer, whole day Earth absorbs it. But at night it starts to release more. So if you're in a ground floor, you feel it, you feel the heat. It emits, but the emission is in infrared. So a telescope that is operating in the infrared region can't be on the surface of Earth, because surface of Earth is also emitting in infrared region. And you want to study the universe in infrared region. Why? I'll tell you in a while. But there are many telescopes that work in the infrared region. And those telescopes cannot work from the surface of the Earth, because the surface of Earth also emits in infrared region and there will be interference. So if an infrared coming from the faraway star, that will come, but the radiation from the Earth is also there. And when the frequencies are very similar, then there is a phenomena of interference. And the both waves will be lost, something else will be formed, will combine. So you cannot study things coming from the outer space in infrared region from the surface. So the terrestrial telescopes, they can't work in gamma rays does not come here. They can't work in X-rays does not come here. They can't work in ultraviolet does not come here. They can't work in visible, because sunlight will interfere. Visible will come here and the sun rays will interfere if a visible light is coming from the other stars. And so you can study in visible light at night. At day you cannot study in the visible light range. So these were gone. And you cannot study in infrared, because Earth emits in infrared all the time. So the terrestrial telescopes, if you have seen in what range that they work in the radio wave frequency, in the radio wave range. That's the only option. So if you want to study from the infrared, you have to go away from the Earth. So you have to go to LEO. So Hubble telescope was in LEO. That's why. Okay. All right. So I think you understand basically. And the second, so LEO will be the first best point to study in infrared, and Hubble telescope studied in infrared. Hubble telescope was in LEO, but James Webb telescope is not in LEO. James Webb telescope is at L2. L2 is 1.5 million kilometer away, and LEO is 600-800 kilometer away. very nearby. Hubble still is working very nearby. 1.5 million kilometers is far, far away. So as we progress into the discussion, I can't explain you right now. There will be a proper point where I'll explain you why Hubble was in Leo and why couldn't we send James Webb in Leo, why we have to send James Webb at L2. I'll open that discussion in a while, but not putting everything on the table right now. But any question from this much of discussion, then you are free to ask. So that's about L1 and L2 and L3 and L5. At L1 is 1.5 million kilometers from Earth. It is sun facing 24/7. And Aditya L1 is their mission, NASA's SOHO and Discover, that's also at L1. I'll give you the separate list of the missions at L1 gradually as we proceed. L2 is also roughly 1.5 million kilometers away. It is away from the sun, so it is dark, it is cold, it's stable. It's stable when there is a circulatory motion, but you have to remember for the exam, L1 and L2 are unstable. L1, this is thermally stable. This is not in terms of stability in terms of thermodynamics. L1 and L2 are unstable equilibrium. You have to know this because in the prelims they can give you a statement. You think that we are sending missions at L1 and L2, they must be stable points, but they are unstable. That's why you have to keep the missions moving. L4 and L5 are stable, so stable that asteroids are stuck here, not of our use. L3 too far away, not of our use, unstable. James Webb Space Telescope is at L2, Aditya L1 is at L1. And why James Webb Space Telescope is at L2, we'll see in a while. So that was some basic thing I want to tell you before we jump into the current affairs. Those Lagrange points, so much of understanding you must have. Now you must also know a little bit, you might already be knowing, but won't hurt if you hear them out again, something about the orbits. If you have to send something in space, it cannot be stationary, it will just fall. You can't be hanging things in the air. So if you want to send something in the space, there are many reasons to send them in the space, it has to move. Because that's the question Newton had. If apple falls, why doesn't the moon fall? He asked that question. Whatever is causing the apple to fall must also cause the moon to fall, but moon seems hung in the air, but apple starts to fall. Nothing can remain hung in the air, and the explanation is moon also falls. In physics, that is also considered as a fall. You are not falling into, but you're falling around. So you're not going like this, you're falling around it. Tangentially you're moving. Circulatory motion in terms of physics is also a fall, falling around a central point. So moon also falls. The force that pulls the apple is the same force that pulls the moon. Nature wise it's the same, not magnitude wise, nature wise it's the same. Gravitational force, and this force can rather create the circulatory motion. So that's the explanation. So nothing can be hanging in the air, otherwise the pull of the earth will pull it. So it has to move. So it moves in an orbit, and there are many classes of orbits. We have low Earth orbit, medium Earth orbit, a geostationary orbit, geosynchronous orbit, and there are others. Sun synchronous orbit and geostationary transfer orbit and highly elliptical orbit. Now before we move on, you might be knowing about these things, but I would want to tell you, and it won't hurt if you hear it again. Low Earth orbit is nearby, and low Earth orbit, technically the range of low Earth orbit could be 160 to 2000 kilometer. But bulk of the satellites that we have sent to low Earth orbit is in the range of 600 to 800 kilometer. This is the practical range. This is the practical range. Why this is the practical range? Because nothing can be revolving with a lot of stability very close to the Earth. Why? Because there's a Kepler's law. You might be knowing about Kepler's law as well. There are 3 Kepler's law. I just want to use one of them. The Kepler's law says, the result of Kepler's third law is that when the orbital radius increases, then the time period increases with this relation. If there are 2 orbits, you have to know this result. I'm not giving you the formulas and other things. You just have to qualitatively know the Kepler's law. If there are 2 satellites, S1 and S2. Now S1 has a bigger orbital radius. R1 is much more than R2. In that case, S1 is moving slow and S2 is moving very, very fast compared to S1 with the second order relation. S1, the higher the satellite, the slower it is. The closer the satellite, the faster it is. It's not about the mass of the satellite. It does not depend upon the nature or the shape of the satellite. Just the orbital radius decides the time period, and orbital radius decides the velocity. And now this is important for you because you have to feel it. If the satellite is closer by to the Earth, it is moving faster. It is moving very, very fast. If it is away, orbital, it is away in the space, it is orbital radius is high, then the satellites become slow. This is the result you have to remember. Orbital time period for satellite in LEO is around 90 minutes. Every 90 minutes, it is going round and round all around the Earth. That's very fast. 90 minutes, you're completing one full circle around the Earth. That's pretty fast. Pretty fast. The speed is around 7 meter per second. 7 meter per second. If you can sense that, that's very fast. The the satellites are moving at crazy velocity in these orbits. Crazy velocity. Now, 7 meter per second data I'm giving you if you're in the range of 650 kilometer. If you bring it to the lower limit, 160 kilometer, it will go to 9 meter per second, 10 meter per second, which is a crazy velocity. At that crazy velocity, there will be a lot of difficulty. Difficulty in terms of lifespan will be less because orbital decay will be there in the satellite. Satellites generally are stabilized for 5 to 7 years in LEO, around 10 to 15 years in MEO, and around 20 years in GEO. And after that, it will be lost into the space. Because, orbit slippage happens. So you have to make correction. You have to turn on the engine. And that maintenance of the orbit perhaps is possible for maximum 20-25 years in most cases in GEO. 5 to 7 years in LEO. But if you bring it to 160 kilometer, it is moving at crazy velocity and slippage will be high. You have to do a very high maintenance of such a satellite. Number one. Number two, if it is moving very fast in the handover, since it is moving away from a point, if you have to keep communicating from a point, then you have to switch, that ground station has to switch from one satellite to the other satellite. One satellite will move, other satellite will come in. So the continuous communication with the ground station also becomes very difficult at that very high velocity. Okay, so the practical range of LEO is 600 to 800 kilometer for that reason. The International Space Station is in LEO. International Space Station is at 420 kilometer. Satellites generally are in 600 to 800 kilometer, but ISS, International Space Station, is 420 kilometer, approximately 420 kilometer, because till 420 kilometer, the effect of Earth's magnetosphere is still there. So protection from the solar storm is still there. Now you can't come very close. You cannot be doing it at 160. You will move at crazy velocity. So the problem would be if International Space Station is kept as 160, 200, then you have to go with supplies to International Space Station. You have to take astronauts to International Space Station. Docking on a platform which is moving at crazy velocity will be even more difficult. So for practical reason, satellites are kept at 600 to 800 kilometer, but that far the effect of magnetosphere is less. So International Space Station is managed at around 400 kilometer because humans stay there and protection from Earth is still there. So it's not very near to Earth. So there is microgravity condition. It's not very near to Earth. So the radiation from Earth is less, but it's not very far away from Earth. Protection from Earth is still there. That's a sweet point. So that's why International Space Station is there. The satellites of Starlink, we'll talk about it later in the discussion. They'll also be in the LEO. Very fast, very fast. In 90 minutes, you go around the Earth once. In 90 minutes. In geostationary and geosynchronous, it will take 24 hours to go around the Earth. But this is taking only 1.5 hours to go around the Earth. The high-speed internet, space-based internet that Starlink is trying to develop, that will come from LEO. So there are more things to talk about, but I will discuss this space-based internet of Starlink gradually. I'm not bringing all the threads out at once. But right now you have to pick that LEO is close by. Closer it is, the faster it is. The faster it is, the more difficult it is to handle it. Lifespan is less. So you have to have more satellites on standby for your LEOs, because LEOs will not survive for very, very long duration. Within a decade, you have to replace it. Costly. It is very costly, but still we send to LEO. Two reasons. Traditionally, LEOs have been used as cameras for taking pictures. Imaging satellites are in LEO. Remote sensing satellites are in LEO. Why? Because it is nearby, because we didn't have very strong cameras. So if you go to GEO or MEO, there will be a problem. You cannot have high resolution pictures. So remote sensing satellites, they are in LEO. It's difficult to manage it from LEO, but they have to be in LEO. With the advancement of technology, with coming of synthetic aperture radar that we'll talk about, you can do sensing from high distance as well from Earth, no problem. And if you go higher, satellite becomes slower. You have to sense that, you have to feel it. If you are closer to the Earth, the satellite is very fast at crazy velocity. And that's why, you understand that. Have you thought about it? The satellite, towards the end of their lifespan, do they have a tendency to fall back on the Earth, or they have a tendency to fall into the space? What do you think? Satellites towards the end of their lifespan, they fall back. So all the satellites dropping on the Earth, or they have a tendency to be lost into the space, going further away from the Earth when their engine starts to shut down. Which one? Towards or away from the Earth? Which one? Well, if satellites had a tendency to fall towards Earth, then you will have in news all the time satellites falling, at least some part of it after being burned in the atmosphere. Some part of the satellite, we don't have that in news very often. Satellites do not come back on the Earth. They have a tendency to move away. They lost into the space. That is right. That is right. Not towards, Himanshu, not towards. They have a tendency to go away from the Earth. So they get lost into the space, not come towards, because to come towards, speed has to be high. And there is a restriction to come towards the Earth. If you cannot manage the high speed, then you cannot be deorbiting and spiraling towards the Earth. You cannot do that. Satellites which are closer by from the surface of the Earth, they are faster. Satellites away from the Earth, they are slower. So where engine shutting down and there is no way to increase your speed, you cannot come down. If the satellite, suppose, has to deorbit like this, it has to continuously increase its velocity. It cannot deorbit otherwise. Because Kepler's law suggests that when you are closer by, when the orbital radius is less, then velocity is more. And velocity is more. So if the satellites have to be brought back on the Earth in the future, they have to be deorbited and brought back. Their velocity has to increase. If you cannot increase the velocity, it cannot come closer. It will go away into the space rather. That's a protective mechanism. So that's the thing. So the satellites are faster in LEO. I hope you are getting some sense. There's a special kind of LEO called as sun-synchronous orbit. It's also low Earth orbit. Low Earth orbit, SSO is just a kind of LEO. So it is that LEO that is polar and inclined at very high angle. It's a special LEO. Low Earth orbit, suppose this is Earth, orbit can be like this as well in the equatorial plane, and orbits can be like this as well in the polar region. They all are LEO because LEO is defined by distance, not by inclination. Any orbit here, that's defined with distance. So if you keep the distance same, then you can change the angle as well, but they all will be LEO. But those LEO which are polar, they are polar around at 98-degree inclination. They are polar orbits. And they are special orbits. Now I will not get into the explanation of this. But I will tell you the result. The result is such that when you are in SSO, sun synchronous orbit, in SSO what happens is the satellite passes same location at the same local time. So if a satellite has to go through Delhi, suppose it goes through Delhi at 4 p.m, then every time after a few days when again it comes to Delhi, it will again cross Delhi at 4 p.m. Now the physics and mathematics behind it, how that sets up, That will be a little complicated to bring that discussion here, but you can watch some YouTube animations to understand that. But sun synchronous, it is synchronized with the sun, meaning it crosses at the same point on the earth at the same local time. And that makes calibration a little easy. Because suppose I am observing a place, how do I observe? I observe it as a remote sensing satellite. I observe it by what is coming from beneath, the radiations. And radiations are unique to chemical composition. If you change the chemical composition, then the radiation emitted out will change. So radiation coming out from a coal mine will be different than the radiation coming from a water of lake. That will be different from a copper mine, that will be different from a diamond mine, that will be different from iron ore mine, that will be different from concrete buildings. So radiation of H2O is different than chlorophyll, that's different from cement. Radiation depends upon chemicals. We call it the fingerprint emission. So what will be emitted, that depends upon what is the chemical composition. And that's how the satellites do the resource exploration. How does the satellite know what's lying beneath? That's how the satellite do the survey of the forest. That's how the satellite do the survey of the water bodies. Because there is a unique frequency in which the satellite will be sensing for water, and nothing else will emit in that frequency, only water will emit in that frequency. That's how it get to know. There are other ways as well, but this is the primary way of getting to know what chemical is lying beneath. So that's one thing, but the intensity of that frequency would depend upon the radiation. So suppose, these days satellites also predict that what amount of harvest will be there. In economic survey also uses a forecast, that wheat and rice production is forecasted like this, and that is done by the satellite, looking at the coverage area, and looking at the amount of chlorophyll, looking at the health of the crop. They do a forecast. So they get to know that there is a paddy crop beneath. They'll get to know all of that, because the emission of any substance is very unique. Like the fingerprint of humans are unique, and human to human it changes, just like the emission is very unique, but the intensity changes. So even if you observe a paddy field at 4 AM in the morning, then you do it at noon, and then you do it in the evening, and then you do it at midnight. So the radiation's frequency will be the similar, but the intensity will change. So if the satellite comes to the paddy field once in the morning, not getting enough intensity, then come next time in the noon, this time the intensity will be higher. There will be a problem. The satellite can misread that there is a higher density of crops because more intensity of radiation is coming. Then it has to calibrate for it. That previous data was at 4 AM, this data is at 4 PM maybe. So how will that change? For keeping things simple, remote sensing satellites are chosen such, and their orbits are chosen such, that it passes through the same location at the same local time. Then making sense of the observation becomes easier. So the remote sensing satellites, almost all of them, they are in SSO. SSO is also a kind of LEO. MEO is medium Earth orbit, and medium Earth orbit begins from where the range of the low Earth orbit ends. But for most practical purpose, the range of the medium Earth orbit is 20,000 to 22,000 kilometer. 20,000 to 22,000 kilometer, and generally navigation satellites are kept in the medium Earth orbit. Navigation satellites like GPS of US. GPS of US is a navigation satellite. NavIC of India, that's navigation satellite, that gives you the location, that helps in navigation. GPS is a navigation system, GLONASS is a navigation system, BIDO is a navigation system. It's Galileo of European Union, that's a navigation system. There are 4 global navigation systems, and India and Japan has a regional navigation system. So navigation satellites are generally put in medium Earth orbit. And why 20,000 to 20,200 kilometer? Because here the time period becomes 12 hours, the orbital time period. As I told you, if you keep moving up, the time period keep on increasing and the velocity keep on decreasing. So in LEO, the time period is 90 minutes, 1.5 hour. Keep on increasing and increasing, it will go to 2 hours and 3 hours and 8 hours and 10 hours. At some point, it will be 12 hours. You keep on increasing, it becomes 14 hours and 16 hours and 18 hours and 20 hours, 22 hours, 23 hours, 23.5 hours. At some point, it will become 24 hours. And that will be the third orbit, the geostationary orbit, where the orbital period of the satellite becomes same as the rotational period of the Earth. So this is MEO because it is 12, and the calculation becomes easy in servicing of satellite because of that is the half the time period of rotation of Earth. That's why this range is chosen. As you move up, the benefit that you have is the higher coverage area. This is the Earth and this is the satellite. The satellite that is nearby, that in the same angle of the cone, same angle of coverage will be less for a satellite that is nearby. Coverage will be more for a satellite that is higher up. For a satellite even higher up from geo, 1/3 of the Earth can be observed from geostationary orbit. So when you go up and up, then the coverage increases. So you can service whole of the Earth in fewer satellites. Starlink program, do you have any idea how many satellites are they planning for their space-based internet service? Starlink. Have you been reading that in news? What's their plan? How many satellites they'll use? Do you know? Himanshu, after the time period is over, we do nothing. In the current arrangement, we do nothing. It just becomes a space debris. Any country that is sending the satellite in the space currently is not obliged to bring it back. We do nothing. Like when the industrial revolution happened, what did we do? We did nothing. The effluents in the air and the effluents in the water, effluents everywhere, it was not even treated. Untreated effluents were given out. What did we do? We did nothing. Then we realized we are getting into a problem. Then through the Rio summit and other things, awareness happened, and now there are controls, there are filters in the vehicles and the filters in the flue gas in the chimneys. Now we are aware, so we are working on it. Likewise in space, nothing. We are polluting the space, creating nothing. There is no provision. And now European Space Agency is pushing for it, that in the Outer Space Treaty there must be a provision that whichever country sends satellite, within 25 years, the same country must bring it back. You cannot just leave it there. It will cost you to bring it back. So we just leave it there. Right? Behaving well is always costly. So we show bad behavior, and we showed that after Industrial Revolution, and we are showing that currently in the space technology. So we do not care. So with that is creating problem. That is creating a problem that a huge loss can happen to our space assets. There's a term called as Kessler syndrome. And Kessler syndrome says that there will come a time where a minute particle, if that collides with a satellite, then that cascading effect will be so high that much of the space asset will be destroyed. So we are, maybe that threat is coming, so now we are getting serious to work on it. All right. So I was telling you that that they're planning for 4,200. 4,200 satellite is planned. 4,200 in Starlink. Why? Because you are very close by. You are around 600 to 800 kilometer. You are very close by. But how many satellites are required in navigation system? Do you know? Like the navigation system GPS has how many satellites? Ideally 24 satellites do. 24 satellites. From 4,200, number comes down to 24. 24 satellites is enough for providing navigation services, but few satellites are kept in standby. So US maintains 30 to 31 satellites at a time. When the replacement has to happen, you don't have to launch it from here. The satellite is already there, so it can just take up the task. So the thing is that 24 satellites, and how many satellites are required to study the almost all the Earth, most of the Earth at least, barring the polar region, from geostationary orbit. From a geostationary orbit, you will require just 3. 4,200 to 24 to just 3. Just 3. 1/3 of it will be covered from geo. So one geo here, 1/3, another geo here, 1/3, and another satellite from geo here, 1/3. The whole of Earth will be covered by 3 satellites. For navigation system, you require global navigation system, you require at least 24 satellites. But from LEO, you require 4200 satellites, and their lifespan is also less, going to be very costly. So why do we do it? Previously, we used to do it because we didn't have strong cameras, so you have to be close by. And now we do it because of IT, because of high speed required. If the satellite is far away, then the latency will be very high, so the communication will be slow. Communication, for fast communication, for higher speed of internet, satellite has to not be far away from Earth. So the prime requirement currently is the high speed of internet, that we want it closer to the Earth. But being closer to the Earth means that their coverage area is less. And coverage area less means more number of satellites and a costly affair. Very costly affair. It's going to be very costly for having an installation of Starlink satellites based internet service. 30,000, they are calculating roughly that will be 30,000 installation charge and 3,000 monthly rental. Very costly compared to the internet that you may be having now. Installation charge is free if you have the installation for 3 months. And I think 600, that's a monthly rental. So going to be costly, very costly, because the whole project is very costly. So that's about MEO. MEO has navigation satellites. In navigation, the speed is not of essence. So you can be slow, so you can afford to go high. Many a times you see that you have reached the destination, the map has not updated. The Google map, in the Google map, you come to the point in a little delayed manner. So it's not very fast. There is latency in the navigation system. The Google map has latency, you must have felt that. So, but that's not a problem, because you know, when you're navigating, then a little delay is not a great problem for you. It's not a great problem. You can manage it and you can endure it. Why? Because it is cheaper that way. If the satellite is up in the sky 20,000 kilometers away, there will be some latency. Obviously there will be. But you know what? Only 24 satellite will be used. So the service will be a lot cheap. So that's the optimization that is done. So navigation satellites are kept there. Then geostationary satellite. Geostationary satellite is around 36,000 kilometers, 35786. This is the number exact at which around 24 hours. 24 hours, which is the orbital period of Earth, rotational period of Earth. Orbital period of the satellite and the rotational period of the Earth starts to match. This is a special number. As you start from here 90 minutes, 1.5 hour, it will keep on increasing as you go up, and there will be a point at which it will be 24 hours approximately, which is the time period for the Earth rotation. So this is a very special point, 24 hours for the satellite and 24 hours for the sun, 24 hours for the Earth. Now this is pretty good. Why it is good? Because in these orbits, the satellite can remain stationary. That is why it is termed as geostationary. Stationary because this is a unique satellite, and this is unique orbit. There is only one orbit. This orbit is equatorial. So in the axis of the Earth, there is a satellite. So Earth will rotate from west to east, and this satellite will go around the Earth. So if the Earth rotates, the satellite also goes along. So in 12 hours, suppose you have the satellite here and this point on the Earth just below it, they are face to face, head to head. In 12 hours, this point will go just behind, because the total rotational time for Earth is 24 hours. So in 12 hours, this point will go just behind, and the satellite is going around the circle in 24 hours. So in 12 hours, it will also go behind. So as the point on the Earth moves, so does the satellite, and they are moving at the same angular velocity. So they are not slipping with regard to one another. There is no relative velocity, and it will appear to a person on the Earth as though the satellite is overhead all the time. It simply does not move. So you could take any point, a person on this point, the angle that will be made, this angle with the satellite will remain unchanged. For every point on the Earth, it will appear the satellite is not moving relative to them, and hence they will become stationary because there is no relative velocity, because 24 hours and 24 hours matches. But this will be just one unique orbit. This orbit has to be in the equatorial plane of the Earth. If the orbit is, suppose, the polar like this, slightly polar like this, if the orbit is slightly polar like this, then it is not going to cut the ice. It won't. then there is motion. There is a relative motion. The points on the earth will go west to east, and the satellite is going like this. So the satellite was overhead above the point on earth, but the satellite moved like this, satellite moved like this, and the point on earth moved like this. So they have a relative motion with regard to each other. So unless it is in equatorial plane, it is not a geostationary orbit. Unless it is 24 hours, it is not a geostationary orbit. So geostationary orbit is an orbit at this distance. Distance is fixed and orientation is fixed in the equatorial plane of the earth. So there can only be one unique geostationary orbit. There is no other geostationary orbit. There is only one geostationary orbit. Theoretically, there will be tons of LEOs. The range is broad, and the orientation can also change. MEO, tons of MEO. There only one geo. Geostationary is represented as GEO. But if you are keeping it 24 hours, but not the orientation, it will still be called as geosynchronous, because the orbital period is still 24 hours, because orbital radius is still same. But the orbit is not in the plane of the earth, so it will not be geostationary. But nevertheless, those orbits are also special orbits that will realize in a little bit in the discussion. They are also very special orbits. They are all called as geosynchronous orbits, and they form a figure 8 in the sky. And this we use in NavIC, so I'll have to now tell you a little bit as to why they form the figure 8. Jupiter Saturn rings, Himanshu, they are having a range, but the orbit will be just a circle. It will not be a range. The ring around it is not a thin orbit, but the orbits of the satellites, they are at a specific orbital radius. It's not a range into which the satellites moves. Satellite moves around in a very specific orbital radius. So it's not synonymous to the rings around Jupiter or Saturn. Okay. Yes, sir. So I was telling you that you have to know this, that the geosynchronous orbit, geosynchronous satellites, geosynchronous meaning 24 hours. 24 hours and the equatorial plane, that is geostationary, but only 24 hours, that is geosynchronous. And geosynchronous satellites, they form figure 8. They form figure 8 around the earth. Now this is significant, and I'll have to take little time to explain you this as well. See, be little patient, you will understand it. Suppose this is Earth, and this is the equatorial, this is the axis. Suppose the axis, although is tilted, but I have drawn it like this. Okay, but this is the geosynchronous orbit. So this is not in the equatorial plane. If you have a satellite here, then if you have a satellite here, and the earth will be rotating west to east like this, but the satellite will go on this orbit. So the motion will be different. There will be relative motion. So this is not stationary with regard to points on the earth. This is not a geostationary orbit. Nevertheless, this is geosynchronous orbit, and there are also special orbits. How they are special? Let me tell you how they are special. See, suppose this is the starting point, and we are discussing 2 points. Satellite with regard to a point just below it at this point on the earth, but this point is going to go like this, correct? Like this, correct, on the earth like this, but the satellite is going to go like this on the orbit like this. So after 12 hours, where are they? After 12 hours, after 12 hours, after 6 hours, 1/4 of the journey is done for the earth and for the orbit, and they both take 24 hours. So after 6 hours, 1/4, the satellite has come here and the point on the earth has come here. They have gone too far away. After 12 hours, where are they? After 12 hours, half the circle is done for the earth and for the orbit as well, the satellite. Half of the journey is done. So after 12 hours on this circle, the satellite will be just behind. And after 12 hours, this point on earth will also be just behind on that other end, diagonally the opposite, on that semicircle. So they will meet again just behind on the Earth, just behind in the space from this point, they will meet again after 12 hours. So distance increased for 6 hours, then it decreased in next 6 hours, and they merged into 12 hours. And then distance will increase in 6 hours. In the 24th hour, they both will be back here at the same time. And distance will be 0 again after 24 hours. So they are together. In 6 hours, the distance increase, next 6 hours, distance decrease. In next 6 hours, distance increase, next 6 hours, distance decrease. Right? So they have to come back every 12 hours. 6 hours, then 6 hours. 12 hours, they came back. 6 hours, and then 6 hours. Next 12 hours, they came back. Because in 24 hours, both will be in their starting point. And suppose they are starting like this, then they will meet again. So with regard to any point, the satellite is moving in the structure 8 like this, in geosynchronous. And you have to understand this, that the point will always see the satellite. And the satellite will be over the map. The satellite will be over a space. Suppose this is the region. This is Southeast Asia and this. And you have Africa here. If the satellite is over a region all the time. Now, this may seem a little crazy. You think about it. The satellite is going round and round around the Earth. But the satellite is not mapping the complete Earth. The satellite cannot see in the other hemisphere ever. Because when satellite goes that side, then Earth also rotates and it sees the same side, that side as well. The satellite cannot see the entire Earth. You have to understand this. When the satellite is going on the other side, Earth is also rotating and there also it is seeing the same side. So the other side, satellite can never see. Leo can see, an orbit in Leo can see, because in Leo, the satellite is moving very fast. In 90 minutes, it's covering the Earth. So in 45 minutes, it will be just behind. But Earth is slow with regard to it. So in 45 minutes, Earth will rotate a little bit. So satellite will be faster than the Earth and can see behind the Earth, the other hemisphere as well. But the satellite in GSO will never see what is in the other hemisphere. Never see. It will always be in the same hemisphere. So it is going round and round the Earth, but cannot see both the hemisphere. Are you getting it? When it goes on to see the other hemisphere, Earth also rotates and it sees the same hemisphere. So what is happening is that the geosynchronous satellite is moving around the same hemisphere. It cannot see the other hemisphere. It is above the same region all the time. You have to think about it and get a good feeling of it if you did not get it already. But this is important because our design of NavIC constellation is based upon this idea. And that is what is written here, that a satellite, and depending upon the inclination, if you decrease the inclination, if you make it like this, then 8 will be flatter. If you increase the inclination, 8 will be elongated. But it will be like this. It will always be like this. So a satellite in GSO forms the figure 8 pattern. It does not see the entire, both the hemispheres. It's only over one hemisphere. So if you want to study a single point and you want to be fixated over a very small point on the Earth, you have to go to geostationary, because in Leo, the satellite is never over a single point or single region. In Meo, the satellite is never over a single point or single region on Earth. But in geostationary, it simply does not move. So with regard to any point, if you want to fix, you can just fix that satellite over that area and the satellite will continuously study that region, that point. It simply will not move from there. If you have to be fixated over a region, then you can send it to the geostationary. Like for example, you have to study Bay of Bengal. If you send a satellite to Leo, it will shift from Bay of Bengal to Southeast Asia and will through the Pacific and Antarctica will come back. It will shift. It will not stay there. I want the satellite to stay. I have only one satellite. I don't have to be hovering it over the world. I want to study my Bay of Bengal. The only way I can study my Bay of Bengal with only one satellite is to send it to Leo. That's how it will remain stationary. Or I send it to GSO with small inclination. So it's also around the region. Just stays around my region. That also serves the purpose. So, but that's the only way. That's the only way. So nothing is fixed on the sky. In sky, nothing is hanging, but it will appear as though it is hanging from geo. So now, so that's the only way. If I have to study Bay of Bengal, then I have to be in Geo, but Geo is far away. Geo is around 36,000 kilometers. So I can be over Bay of Bengal, no doubt, but I can be over Bay of Bengal at very high distance in the sky. From nearby, I cannot be over Bay of Bengal all the time. From Leo, it is not stationary. So that's a problem. One problem solved, that I'm over a point, but the other problem is I'm too far away in the sky, 36,000 kilometers. If my instruments are not very strong, then what will I observe? Observation satellites, remote sensing satellites, and Leo is easy to observe from here. From 36,000 kilometers, what will I observe? Even if I am over the same point, but the observation will be pretty weak, don't you think? So there is a technological breakthrough, and the term called as SAR, synthetic aperture radar. Synthetic aperture is something that has broken that barrier. So very strong observations, very clear observations can be done from very far away distance. We'll come to this term when I teach you NISAR. I'll take up the topic. I'll give you the concept of SAR as well. But the point is that it can be done from very high distance. Now high resolution images can also be taken. So problem solved. You are studying Bay of Bengal and the cyclonic development there, or for security or whatever purpose, you're studying a particular region. So you fix it to a point from Geo or GSO, and you also have strong cameras now. So pretty good, pretty good. There are other terms like GTO, Geostationary Transfer Orbit. Geostationary Transfer Orbit. Now if I ask you a question, that if you have your SUV, if you have a SUV and you have a full tank fuel, how long the SUV can go on the road, on the highway? If you have a pretty good mileage on the highway, if you have a SUV with full tank, what distance can you travel with that without refueling? Do you have any idea on that? What distance can you go with a SUV without refueling after having a full tank of fuel? You know that? Around, you know, if it's a highway with minimal brakes, etc., you can go to around 400 kilometer, maybe 400 kilometer. You can go to 400 kilometer, right? We are talking about 600 and 800 kilometer. We are talking about 20,000 kilometer. We're talking about 36,000 kilometer. At this great distance, you can have no vehicle that will take the vehicle, the launch vehicle, the rockets cannot be taking satellite directly to these great distances. Yeah, it depends on the mileage. Yeah, but roughly I was asking, it's around 400 kilometer, just 400 kilometer. But you know what will take the satellites to 36,000 kilometer, 20,000 kilometer, even 800 kilometer is too huge. You cannot be going. And once you do the fueling here, that's all the fuel you have. There is no fueling done midway. We don't have a fueling tank, refueling station midway. You don't have it. So whatever fueling you have to do from the surface of the earth, and once you launch, you have only that amount of fuel. So the satellites, I hope you understand, does not go to these distances directly. Directly they cannot be taken. Nothing, no vehicle can travel that long distance. If you have to go to huge distance, then the fuel amount will be more. More fuel amount meaning heavier the launching system. The rocket will become itself heavy because the fuel tank is bigger. The weight of the fuel itself will be heavy. Now that will bring you to a paradox. If you have to go to long distance, you have to have more fuel. More fuel meaning heavy rocket. Heavy rocket meaning difficulty in launch. Ideally, if you have 1 kilometer by 1 kilometer tank, it can take you to long distance. But what will pick it up? More weight to overcome gravity, more difficult. It's a problem that you cannot solve like that. So direct travel is not possible. It's not possible. So direct launch vehicles do not take the satellites directly. Rather, they leave it to GTO, Geostationary Transfer Orbit. GTOs are transfer orbits. So you know how it happens. It happens in a very roundabout manner. Very, very roundabout manner. From the Earth, something is sent to just around 160 kilometer. Just 160 kilometer. It can be even lesser than that. And launch vehicles take it to only this distance, and this distance is maneuverable. You can go to till 160 kilometer with the fuel tanks. You can go. More than this, it's not possible. More than this, more fuels, more weight. More weight, then lifting is more difficult and you're stuck with the problem. So the problem is solved using science, and the science is that there is gravity and gravity assisted motion that guides the satellites. So what is done is the satellites are taken only to this, and then the satellites forms highly elliptical orbit, which is your last orbit here. Highly elliptical orbit. Highly elliptical orbits are formed like this, and the satellites move on this orbit. When the satellite comes here, then there's always a very small engine in the satellite. Once the launch vehicle has done its job, satellite has been placed in the orbit, there's a small engine that can lift it up. So when it lifts up, then the distance from the other side will decrease. In next round, it is lifted a little more, then distance from the other side will decrease. Next round, lifted a little more, then distance from the other side will decrease, and gradually it will start to become circular. This is called as circularization of the orbit, and the orbit becomes circular gradually. So that long distance, if you have to send, cannot be taken from the launch vehicles directly, and in multiple rounds the orbits are formed, and that is gravity assisted. And in one round you have to start your engine of the fuel, and that is very easy. To lift it a little bit is not difficult because you are not acting against gravity. You are far away from Earth. So in space, a little impulse can lift you up, no problem. That is microgravity condition. So a little bit of engine and little bit of fuel will do the job. Difficulty is when you are closer to Earth. At the surface of the Earth, the highest amount of pull is there. To move a fuel tank on the surface of the Earth, that's the difficulty. To move that big fuel tank in space, that's not difficult. You're in microgravity condition. Very easily you can move things there. So that small engine will do the job there in the space. A huge engine is required. Powerful engine are required on the surface of the Earth. So the satellite has those small engines, and through those, this correction happens. So that explains you GTO, that the launch vehicles goes till GTO. That explains highly elliptical orbit, which are formed from the GTO, and the circularization. So I've given you some basic concepts on orbits. These will be required for understanding and for the discussion that we are going to start. So let me jump, and if at all some more basic concepts will be required, I'll give you during the discussion. So let me take a little jump and give you some updates. Recently, ISRO has done space docking experiment. Docking, you have a platform which is moving, and another spacecraft settles there, docks there, rests there. Challenge is something is moving. If something is moving, you have to match the velocity, come close, so that there is no relative velocity, there is no jerk, there is no slippage. So something is moving, you have matched the velocity with the moving platform, and then you softly land on that. Otherwise, it will be crash landing. You will destroy the system. International Space Station, 400 km. Now I have explained you much of the things. Closer you are to the surface, faster you are moving. So International Space Station is moving at crazy velocity. If it is moving at crazy velocity, then you have to send supplies there, and you have to send the astronauts there. You have to bring them back. You have to do to and fro on the International Space Station. And unless you learn how to do docking, you cannot imagine to be running an International Space Station. And India has a plan. For Bharatiya Antariksh Station, there's a plan. And the plan is that we have but this is pretty basic. Unless you have docking capability, you have proven that, you cannot be even dreaming of having an International Space Station. We have to learn this first, and we have done it. It's a major thing. It's a major thing. You'll understand in the next slide when we do the updates on Chandrayaan 4. It's a major achievement ISRO has achieved. India has become the 4th country to achieve this satellite docking in space. And how we have done the docking, we don't have an International Space Station of ours. What we have done, we sent 2 satellites, and we docked 1 satellite over the other satellite. That's how the docking capability we have shown, which is pretty good. And the launch was done by PSLV. Our launch vehicles, the most powerful launch vehicle is GSLV. Earlier it was called as GSLV, Geosynchronous Satellite Launch Vehicle, GSLV. GSLV now has been renamed as LVM3, Launch Vehicle Mark III. Geosynchronous. What does that click? Geosynchronous, geostationary. Those are the satellites where you send communication satellites. Communication satellites because they do not move with regard to a point or a region. So like the direct to home dish TV connection people have at home, direct to home, there's an antenna. Antenna communicates with satellite directly. If the satellite moves with regard to surface of the earth, then as the satellite moves, you have to move the antenna as well, so that the line of sight is maintained and the satellite continues to communicate with the antenna. But you don't have to make the adjustment. Once you decide where the satellite is and you set it, because the satellite does not move. Because why? Because it is in geostationary. A satellite which is in geostationary orbit does not move, so the line of sight does not change. That requires just one initial adjustment to see where the line of adjustment is, where the line of sight is, to do that the adjustment. But once it is done, it's done. And the satellite is not slipping away, it is a stationary. So geostationary, geosynchronous satellites, they are used for communication purpose. Okay, so GSLV and PSLV. GSLV are powerful satellites. Communication satellites are heavier satellites. So generally, if something has to be sent up above in the sky, in geosynchronous orbit, geostationary orbit, then GSLV is used. PSLV is polar satellite launch vehicle, and we have done polar orbits. Remember when we did LEO, we did SSO and sun synchronous orbit. That's a kind of LEO, but it is a polar LEO. So polar satellites will go to the polar orbit. Polar orbits, that is in reference to the SSO, and the satellites that goes to SSO are for remote sensing purpose. So polar satellites, they are in LEO, and LEO is nearby. So you know, to send something nearby, and anyways the remote sensing satellites are lighter, not heavier as the communication satellites. So the payload capacity of PSLV is lower. So initially ISRO was launching mostly remote sensing satellites. When we begin to launch the heavier communication satellites, we required GSLV. I'll talk about the launch vehicles in another section. But you have to take, whenever you study a news, you have to see India is at what number in that. You have to see which orbit is that. You have to see which launch vehicle was used. So launch vehicle used for space docking experiment, since it was done in nearby space in the LEO. In LEO we use PSLV. Mostly for LEO we will use PSLV. So PSLV was used for the launch of 2 satellites, and 1 satellite was docked over the other satellite. That's how we have achieved the docking experiment. This will be very crucial for our future space station and Chandrayaan 4. We'll talk about Chandrayaan 4 mission in a while. Gaganyaan mission. Among the ongoing mission of ISRO, the most advanced mission is Gaganyaan. And Gagan, where is Gagan? Gagan is space, in the sky. And where is the space? Technically, space begins where the aircraft stops. That highest point at which the aeroplanes goes, above that there is a space. So technically space is above 100 km. But properly the space is where the International Space Station is, around 400 km. So in that range, 350 to 400 km Gaganyaan will go. We haven't sent humans in the space. We have sent many satellites already, but we haven't sent human in the space till now. Indians have gone into space in the Russian mission, and most recently in one of the private space agency mission of US Axiom. The Axiom 4 mission, Shubhanshu Shukla has gone to International Space Station, and Rakesh Sharma went on a USSR mission. Indians have gone, but Indian Space Agency ISRO has not sent humans to space. Sending humans to space is risky. Recently you have heard that 2 consecutive launches of PSLV has failed. It is a dangerous thing, and such events can happen. So you have to have safety measures. You have to have safety measures. You have to have multiple modules. You have to have environmental control and life support modules where that oxygen will be maintained inside and CO2 will be removed, temperature and humidity will be regulated. You don't require these mechanisms if there are no humans. So humans' presence will require special arrangement. Just in case of crash or engine not operating, any stage of the vehicle not working, you have to bring them back. So safe re-entry through the parachute mechanism, you have to have special arrangements. These arrangements we do not have for satellites. Satellite engine doesn't work, stops, then stops, satellite get lost, it get lost. We do not have those mechanisms enough. It will be costly if you do that in every launch. PSLV has done 60 launches from 1993, 60 successful launches, 4 failures, altogether 64 launches so far. Out of 64, 60 launches are successful. It's a great success story of ISRO. So you will not have those safety mechanisms unnecessarily. That will be very costly. Increase the payload also. So the more amount of fuel will be required, becomes costly. The first launch of PSLV was a failure, first launch. You know what, after first launch for decades in 2017, there was a failure. And then recently it has happened 2025 and 2026. 4 failures, only 4 failures. But you can't take chance when they are humans. You have to make special arrangements. So the trials have been done, the precursor mission, robots have been sent, a female humanoid robot. I do not know how they identify their sex. It was a female. Robot was a female, but Vayomitra, a female humanoid robot, was there. So we have tested it. Now the real humans are going to go. There are 4 IF officers. They're getting trained in Russia. Russia is a huge partner country for India in many sense, and in Gaganyaan mission also, much of the training, some training has happened in India as well. But since it is our first mission, are we getting help in getting our officers trained in Russia? Okay, so they will go in space, spend some time, and they'll come back. How will they come back? Right now, we haven't developed mechanism to bring them back. ISRO has done no sample return mission, which is also very important for your coming prelims. We have a planned mission, but so far we have done no sample return mission. So far we haven't developed, and no country for that matter has developed mechanism to deorbit the satellite and bring back safely on the Earth. We don't do that. We send satellites. Satellite get lost, no problem, we'll send another satellite. We haven't sent any human mission before, and we have not brought any sample. So how to bring things back on the Earth, that's not our forte. We haven't done that. Everything get lost. See, when we launch a satellite with launch vehicles are all spendable. We don't have reusable launch vehicles. So we do not bring even the launch vehicles back. Nobody comes back. Imagine, many of the passengers in the aeroplane, and the journey is there in the sky, and none of them come back. Neither the plane come back, nor the passengers come back. Nobody comes back. And the passengers here are the satellites. They're on board a launch vehicle. Launch vehicle is like the aeroplane. Aeroplane goes and the passenger goes, the satellite goes. The satellites are placed in the space. They don't come back. They get lost in the space at the end of their lifetime. And the aeroplane also does not come back. The whole aeroplane was made only for a single journey. So obviously it will be costly, very costly. In the reusable system, the aeroplane comes back. In the feature system, the passengers will also come back. The satellites will start to come back on the surface. But right now for us, nothing comes back. So bringing things back on the Earth safely is not our forte. For the first time, we are going to do that. And there will be a splashdown into the water through the parachutes, either in Bay of Bengal or Arabian Sea for them. So they'll go like the satellite goes, and they'll come back through the re-entry module like a parachute landing. Because we do not have the reusable launch vehicle. So launch vehicle will go and the launch vehicle will come back. We don't have such mechanisms. Launch vehicle does not come back. So what will come back is the parachute gliding and splash down into the water. That's how they will come back. India will be the 4th country again. In most cases, India will be 4th. NASA and USSR, they have done it, and China also in many cases they have done it before us. So in many of the cases, India will be the 4th one in all the endeavors. India is 4th here again for indigenous human space flight. Shubhanshu Shukla became the first Indian astronaut to go on International Space Station. See, there are many astronauts of Indian origin. As such, if you count number of Indian origin, 6 of them has gone to space. But Indians with Indian passport, people who are Indians, proper Indians, not just Indian origin, they're just 2. Rakesh Sharma was the first one, and he is the second one. Shubhanshu Shukla is second Indian to go to space and first Indian to go to International Space Station. International Space Station has been the program of US. It is US led. China is not there. US and European Space Agency and Russia and Canadian Space Agency and JAXA, the Japan Space Agency, they are there. India is not a party to it. India is not a party in International Space Station. So he became the first Indian to go to International Space Station as part of Axiom 4 mission. Axiom is a private company. It's a startup of US, and NASA has done a lot of hand-holding of the private companies, lot of hand-holding. And Axiom 4 take the supplies, take the astronauts, do to and fro from the International Space Station, Axiom 4. So in the mission of Axiom 4, Subhanshu Shukla went, and this was made possible because India became the signatory to Artemis Accord. And as part of Artemis Accord, to take forward the cooperation between NASA and ISRO, Subhanshu Shukla was given the opportunity to go to International Space Station to warm up, cozy up our relation with the US, because India signed the Artemis Accord. About Artemis Accord, we'll talk in a while when we start to discuss the lunar missions. It's a US-led agreement, and it's not a multilateral agreement, it's a bilateral agreement. US individually with every country is entering into the agreement bilaterally. It's not within UN. Within UN, there's a lunar treaty, there's outer space treaty. From the outside of UN, outside the aegis of UN, US is getting into the bilateral agreement. India's position always has been that we prefer multilateral agreement within the aegis of UN. That is our position in most of the international issues. But since it was bilateral, so we were not very comfortable signing it. For years we did not. But in 2023, when PM Modi visited US, generally in the prime ministerial visit, you expect some big bang announcements. It was one of them. It was one of them, and India became, in 2023, India became the member of Artemis Accord. All right, we'll talk about Artemis Accord more in a little while. We are doing the updates of ISRO, okay? In the updates of ISRO, NISAR is also very important. NISAR is NASA ISRO Synthetic Aperture Radar. It's a major satellite. It is the most powerful remote sensing satellite of the world. NASA ISRO Synthetic Aperture Radar. It was launched by GSLV Mark II, which has an engine little smaller or less powerful than GSLV Mark III. Our most powerful rocket launch vehicle is GSLV Mark III. GSLV Mark II is lighter version of that. You have to remember this. It was launched from India, and it was launched by GSLV Mark III. It's the first dual frequency radar. Dual frequency because it uses L band and it uses S band. L band is 1 to 2 gigahertz and S band is 2 to 4 gigahertz. So L band is of lower frequency and S band is of higher frequency. Generally the satellites either use L band or use S band. Satellites, the remote sensing satellites, they do not use both the bands. Why? Because it becomes heavy, more instrument, it becomes little complicated. So they prefer keeping it light, so either using L band or S band. It is the world's first dual frequency remote sensing satellite. You have to know that. Launched by India, GSLV Mark II, you have to know that. You also have to know that L band has been contributed by NASA and S band by ISRO. You know, UPSC reverses it. Whenever there is a 2-bit of information, UPSC tend to exchange it and make the statement incorrect. You have to remember, you may remember through Operation Sindoor or howsoever, S band has been contributed by, the instrumentation to work in S band has been contributed by ISRO, and the instrument that would work in L band, that come from NASA. You don't have to mess it up. S is for ISRO. And you also have to know one thing: higher the frequency, the more difficult it becomes to communicate. Frequency, if you increase the frequency, no doubt the communication speed increases. But if you increase the frequency, then scattering also increases. Scattering happens where the particles, diffraction happens at the edges. So if you have more frequency, then the scattering and the diffraction increases. So suppose you have a tree. If you are doing the study of a forest, you have trees that has leaves, and this is the canopy, okay? This is the trunk, this is the canopy, and the leaves and a lot of branches. So if the radiation is given, radio waves developed by the satellite given down on the surface, then you can study these from S band. S-band has higher frequency, so the scattering and the diffraction of S-band will be more. So to study the canopy, S-band will be less, S-band will be good enough. But to do deeper studies, you cannot use high frequency because they get scattered from the first contact. They'll come to the first contact and see the surface, how the surface is at the first contact above. Okay, but it doesn't penetrate because it gets scattered. So if you have to penetrate the canopy, you use the L band. S band is better for surface features. You have to know this. They can add this to the statement. It is taking things a little higher into the science, but this is important. This is important. We will do this intensively in ICT chapter as well. If you have higher frequency, then the loss of the signal is higher. Everything has a cost. Higher frequency means high speed of communication. So, but if you're dealing with high frequency, to handle high frequency, it becomes difficult because the loss of the signal because of scattering and diffraction and other phenomena increases at higher frequency. So it becomes difficult. So in the first contact, it will come and will do the imaging. But to penetrate deeper, you have to work with lower frequency. L band is of lower frequency. So deeper part of the vegetation will be studied by L band, and the canopy study can be done by S band. At least this much you have to know. This is very sensitive, very sensitive. You know, the sensitivity of NISAR is around 0.4 inch. You know, inch is so small, so small. This much we say as 1 inch. 0.4 inch is so small, meaning any movement on the surface of the earth of this order, that can be detected by NISAR. That is the sensitivity of NISAR. It is world's most powerful remote sensing satellite, NISAR. Very, very powerful. 0.4 inch. And they used to boast about it. They didn't have it earlier, but they used to boast about it. That if you have a butt of a cigarette, that would be a little larger than 0.4 inch, around maybe half an inch. I don't know. Thing is that if you have an object of that dimension, the satellite can study that as well. That is the sensitivity of NISAR. Now they have achieved it for real. And together with ISRO. So this satellite is a big deal. It's a big deal. It's highly sensitive. So that's about NISAR. Now how has it become that sensitive? The magic is of SAR. This is the synthetic aperture radar technology that has made it possible. SAR makes it possible. Now again, I'll just take 2 minutes. Just 2 minutes to explain to you how does SAR work. Here, aperture, you understand aperture. Aperture means the area in which the light comes. If the lens has higher aperture, then more clear image will be there. You see the aperture in the telescopes, the powerful telescopes, they tend to be bigger. If they are bigger, that means more light can enter. If more light can enter, then the image will be more clear. If the lens is smaller, the image will be less clear. The professional photographers, they carry a bigger camera. They carry a bigger camera because the lens is bigger. From phone, you cannot have that size of lens. You cannot. The lens is smaller. The resolution is limited. So if you increase the aperture size, obviously the resolution will increase. But there's a limit to which you can increase the aperture size. If you're having satellite in the space, you can't make it too big. If you make it too big, they'll be too heavy. Too heavy, then what will launch it? You can't be launching mountains from the sky, from the earth. You can't be launching big boulders from the earth. It is costly. The weight lifting is not easy because gravity is pulling it. Engine has to be very strong. Burning has to be very powerful to lift it up for 50-60 kilometers. Beyond that, gravity becomes very weak. Above 100-200, there is microgravity. But on the surface, it's heavy to lift it up. It's cost. You can't be lifting things up. There's a limit to what you can lift up from the surface of the earth and send to the space. So you cannot make it very big. And if you make it very big, the mechanical strength will also decrease. It may break. So there's a limit. So traditionally there was a limit to the resolution of the pictures taken from the space. It was not very, very clear. That is improving. That's improving because there's something called a synthetic aperture. If there's a satellite, satellites will have limited aperture. And if you have to do the imaging of the surface, suppose you have to do imaging of this point, then this point will be imaged by these these aperture. So there's a limitation. If you increase the size of the aperture, then the image from different angles can come from the same point. So the resolution will be higher, the image will be very, very clear for this point. If you increase the size of the aperture, then the image will be even more clear. The finer resolutions, the finer fine prints of this point you can see, because you can see it from different angles, you can see more actually in that sense. If you can see more, there's more to show, so you can resolve it more, so you can zoom in more. If you can't see more, there's nothing to show. You can't be zooming in more, there's nothing to show because you haven't seen that yourself. But you have seen more this way. If you have seen more, you can show more, then you can zoom in more, meaning resolution will be more. But you can't be doing that. You can't be doing that. Get heavy and will become weak, it start to break from here. You can't be doing that. So it is not done. You know what is done instead? Very smart thing. Aperture is small. If imaging has to be done, then imaging is done with this aperture itself. Then the satellite moves and imaging is done from the other point as well. Then the satellite moves and imaging is done from the other point as well. And then the satellite moves and imaging is done from the other point as well. And before this point, the imaging was also being done. So the satellite takes images not from the same point. Satellite take images continuously. And all these images will be overlapped. This was all at once. This in bits and pieces. So if it is done in bits and pieces and collected, then the same satellite has seen it from different angles. So it also has the same data that a larger aperture will have all at once. And collating them, image will be created, will be just as good, even better, because now there is no limit for you. No limit. You can have a huge mammoth size aperture, as big as you want. There is no limit. And this increases the resolution. This is the technology as to how remote sensing is becoming better, and you can send it up in the sky as high as you want. From there also the resolution is improving. That's how it is done. This is synthetic aperture radar. Obviously the circuitry will become complicated. When you are here, you'll be imaging the other points as well. You're imaging the other points and you're imaging this point as well, and you have to keep a time stamping of the images of this point, and then the coordinates you have to maintain, and then you have to bring the images together specifically of a single point. There shouldn't be error in that. To develop that precision, it's not very easy. And NASA was the first space agency to get into this technology of synthetic aperture radar. Technology gradually has been given to India as well, but not to a great degree. So SAR remains a high-end technology. SAR, we are not autonomous in SAR yet. SAR still remains a very high-end technology. And using this idea, a very simple, ingenious idea, SAR has been made, and that's why it is so sensitive. That's why 0.4 inch up in the sky, this amount of resolution, this is great. Right? Human mind is ingenious. We solve problems like anything, The more you study science, the more you feel that there's hope in humanity. That's NISAR, okay? Then Aditya L1 also in the past has been a major mission of ISRO. It is India's first solar observatory, a dedicated solar observatory. It is the first, and we have sent it at L1. The point of sending it at L1 is that it will have 24/7 access to CERN, so study it continuously. Okay, so the mission already has been completed. It is already at L1, but recently it was making news because of its SOOT payload. SOOT is Solar Ultraviolet Imaging Telescope. There's also a particle analyzer that uses X-rays. So, you know, Aditya L1 works in ultraviolet region and X-ray region. You have to know this. It does not work in the gamma ray region. So, the Aditya L1, the higher the frequency, the more difficult it is to work in that region. Gamma rays will have highest frequency, and higher the frequency, the circuitry will be even more complex. For example, the frequency increases as we are going from 2G to 3G to 4G to 5G. And maybe by 2030, 2032, we'll have 6G. So when we take a generational jump, there are new technologies that come in, but the frequency that we use for communication, that also becomes higher. Correct? So when we go from 3G to 4G, when if we remember that phase when we were going from 3G to 4G, then more telecommunication towers were used, and the receivers and senders, that has to change. The handset has to change. There were advertisement that now the 4G enabled phone, then 4G to 5G, they were advertising 5G enabled phone. The same handset cannot operate on the 4G network and the 5G network. The same handset cannot. The same handset which was only designed for 4G cannot communicate in 5G because the frequency is different in 5G and it was not designed for that frequency. So you have to change your handset. The new handset can also communicate in the older ones, but it will communicate with the 5G as well because it is designed for 5G. So instrument has a design and they can work only in that design, in that designed frequency range. Frequency ranges changes, then the instrument will not work. So, and higher the frequency, more complex is the circuitry. Semiconductors, more complex, processors, more complex. So if you keep on increasing frequency, it becomes difficult to deal with it. So gamma rays is a real tricky thing, and many instruments are not designed, many telescopes are not designed even for gamma. There are very few gamma rays based telescope. So Aditya L1 works predominantly in ultraviolet and X-rays region. Aditya L1 has to study corona, solar winds, coronal mass ejection. It also will do space weather prediction. Now corona and coronal mass ejection and solar wind, what are these? For this, again, allow me 5 minutes of time to tell you some basics again. We have time, we'll conduct it next week as well, so I don't want to rush it. I want to go drip and give you all the concepts. Since India has said Aditya L1, Aditya means sun. So after Aditya L1, sun as a static topic, that also has become important. What UPSC does is it picks some static thing from the current affairs. So even if they ask on Aditya L1, suppose there are 3 statements, 2 of them may be from current affairs, but one very static basic science they will ask. They mix it up. So you have to know the basic science of sun as well. And even to understand what's happening in the what you're reading in the news, you have to get it. So let's come back to this basic part. Sun has 6 layers. Traditionally, 6 layers classification has been done of the sun. The innermost layer is core. Core is the innermost layer and it is highly packed, it is very dense, it is highly pressurized and is at very high temperature. The temperature is around 15 million degrees Celsius in the core of the sun. Core of the sun is massive. The heaviest thing in our solar system, massive. So the pressure at the core will be very high. The temperature at the core is also very high. In this extreme condition, it is possible to do fusion. So the nuclear fusion in which hydrogen atom are fused to form helium and huge amount of energy is released. That fusion happens in the core of the sun. And then the energy starts to be released from there. You have heard of black hole? If time permits, next week we'll just have a discussion, a little bit of discussion on astrophysics, and we'll discuss about black hole. You know, black hole will not allow even the photons to pass through it. Lights cannot pass through black hole. It will get absorbed. If there's a black hole, if light's crossing by, it will bend, called as gravitational lensing. If light approach very close, it cannot be reflected, it cannot pass through it, it will be completely absorbed. Black hole, the mass is so dense there, so dense, that the gravitational pull is so strong that not even photon can escape. Photon is almost massless, rest mass is 0, but it's moving with some momentum, so mass in motion, there is some mass when it is having motion, but negligible. And gravitational force depends upon mass, but in that negligible mass as well, substantial force will be created because the mass on the other side is very dense. So not even photons can escape. So escaping is not possible in black hole if it approaches very closely then. Now here the density is very high. It's not a black hole, it's not that dense, but density is also very high. Point I'm trying to bring home is escape of photon from here will also not be easy because of high density. So in the second layer, that is called as radiative zone, in the second layer there's energy transport and the energy moves from the inner layer to the outer layer, and energy moves in the form of photons. But energy moves outward as photons via radiations, and it takes around 1,70,000 years to come out of the radiative zone. It's not that they can burst out, they will come out very slowly, you understand, because it is very dense. That's radiative zone, and now you're moving away from the core, so temperature will start to decrease. The third zone is convection zone. Convection zone is where the heat transfer happens. The heat from the core passing through the radiative zone has come to the convection zone, and materials in the convection zone will get heated up, will become plasma. Heated up, plasma, and then rise. They get heated up because of the heat coming from the radiative zone, because of the inner core. Fusion is happening. Heats come from the radiative zone and will heat up the material in the convection zone. It will rise, get away from the source, and then cool, then sink, and the cycle will continue. And this is the reason, because they are in plasma state, they are charged, and charged particles moving in a closed loop, that creates magnetic field. So sun's magnetic field is because of this reason. The plasma that is moving in a closed loop, charged particles in the convection zone. So sun's predominantly magnetic field comes from the convection zones. Okay. Then the fourth layer is photosphere. Photosphere is what we see from the earth. It is also called as surface because in the picture we can see photosphere. This is the fourth layer, but this is taken as the surface of the sun, not the fifth, not the sixth. The reason is that they are very thin, and they are not thin in density. They can extend to millions of kilometers, the last layer, but they are very, very less dense. So if you take a picture from the camera as well on earth, you take a picture from photosphere. So since they are very thin, so it is visible. Photosphere is visible to us because of very low density of chromosphere, the fifth layer, and the corona, the sixth layer. So that's why it's also referred to as surface of the sun. Phenomena like sunspots, they are on the photosphere. Sunspots, if you can Google, you might have done this in geography, I'm pretty sure. These everything I'm telling you, if you have done your geography, you must have done these things. And phenomena of sunspots, it's a darker, cooler region, and you can see the pictures also on Google. There will be spots, black spots, because light's not coming from there. Why not coming? Because they are cool, so they are dark. Because light's not coming, so they are dark. Light's not coming, so they are cool. So they are dark and cool region of intense magnetism. Why are they cool? Meaning light's not coming. So why are not heated up? Because energy perhaps has been transported from them. And energy is transported, magnetic field lines becomes the conveyor belt for the transportation of energy. So if energy has been transported very quickly through some mechanism, so they become cool. If they become cool, they do not emit much, so they become dark. So how exactly it is happening, it's not very clear, and there are many theories around it, but we'll not get into that. What we'll get into rather is this. The temperature decreases here. Look, what is the temperature? 5,500 degrees Celsius. 5,500 degrees Celsius. And from where did we start? We started from 15 million degrees Celsius. From 15 million degrees Celsius, the temperature has dropped to 5,500 kilometer. Which is good, which is understandable, not a problem. It is not a problem because we are moving away from the source of the energy. So when we move away from the source of energy, it is very natural, obvious, it's logical, understandable, very clear to us that temperature has decreased. Problem will begin from here. When we go to the outer surface, then the temperature increases. The fifth layer of the sun is chromosphere. Chromosphere is like the atmosphere around it. It's very less dense. It's a pinkish red layer visible during eclipse. When the sun is eclipsed, even then this layer is not eclipsed because it's very thin and extends outward. So chromosphere and corona extends outward too much. So they will always be visible. They cannot be eclipsed. That's one thing. The other thing is that the temperature here starts to increase and goes on to 20,000 degrees Celsius. See, they are thin and you can penetrate through it, through the cameras. You can see the layer below it. So they are very, very, very less dense. And fusion cannot happen here. Fusion happens at extreme condition. So there is no mass density, there is no pressure, there is very less low density, very, very low density, and there is no possibility of fusion here. So why would the temperature increase? Temperature is increasing perhaps because of something else. There is no clear source of energy in this layer. This layer has no source of energy. Energy is coming through some process, some mechanism from beneath. But this is something, there are many theories now have come because of for this, but we have not been able to clearly understand, and there is no final verdict on this that we still have. We don't have any final verdict on this. Why the temperature starts to increase in chromosphere? This is something we are yet to completely understand. Or if you know, you can tell me. What do you think? Why the temperature starts to increase? Perhaps what is happening? So temperature starts from 5500 to 6000 degrees Celsius to 20,000 degrees Celsius, and then there is a very narrow transition region where the temperature increases rapidly, very rapidly. From 20,000 it comes to 1 million, meaning 10 lakh. 10 lakh degrees Celsius. From 20,000 to 10 lakh degrees Celsius, rapidly temperature spikes up. And then the last layer is corona. The last layer is called as corona, and it extends millions of kilometers. It's very, very less dense. Millions of kilometers it extends. This is the outermost layer. These layers are visible during solar eclipses. Chromosphere and corona are visible. Temperature can rise to 1 to 3 million degrees Celsius in corona. This is called as coronal heating. Corona is the outermost layer, but it is very hot. Something happening within, as you come out, the temperature ought to decrease, but the temperature increases, and from the photosphere the temperature started to increase. It's hotter than the fifth layer, it's hotter than the fourth layer, which is very intriguing. Being the outermost layer, it is very hot, and since it is very hot, you can understand the outermost layer is loosely held. The inner layer's material will be packed because of pressure. It is the outermost layer, it is loosely held, and this is very hot. So the outermost layer is in plasma. Plasma is there in the second layer as well. Plasma is there in the convection third layer as well. It's all plasma. In the convection zone, in the third layer, there is plasma. So there is charge, and they are moving in a loop. That's the reason for the magnetic field lines. This is also plasma, but that plasma is tightly held inside. This plasma is not tightly held. This is extremely hot and poorly held. So what will happen? It will just come out. There is no binding force. It will just ooze out, and 24/7 some of the plasma will keep coming out from the sun 24/7, and they are called as solar winds. They are a continuous 24/7 phenomena, because if the outer layer becomes so hot and come in plasma, there is nothing to stop it, nothing. So there are some solar phenomena like solar wind. Solar wind is a continuous phenomena, supersonic stream of charged particles from the corona, because corona is very hot, and in that material is in plasma state. There's nothing to stop it. It will keep coming out continuously. That is the solar wind. So there's a huge threat. You have to go in a special suit as an astronaut. On the moon is coming, on the Mars it would be coming, everywhere in the space it is coming. It is coming to Earth as well. Thank God we have magnetic field lines, and they are going to the pole and convert into polar lights. We are protected. We are protected by the magnetic field lines and our atmosphere, but they are coming to Earth as well. They are coming in the entire space, the solar winds. And then there is coronal mass ejection. Mass meaning they have particles. Solar flares. There are two terms you have to familiarize yourself with. Solar wind, I hope you have understood. Coronal mass ejection and solar flare. Solar flare is radiation. Coronal mass ejection, that has mass. So what are they? We do not know exactly how and what is the reason. We do not understand the sun properly, to be very honest. So we do not properly understand the sun. but we know a lot of things. We know that solar wind comes out, we know their temperature distribution, we know that there's fusion happening there, and we know that there's some ejection from the sun, and two of the major ejections is coronal mass ejection, because we thought, okay, from where the particles will come, from the outer layer. That's the first guess anybody will take. If you observe particles coming out, heavier particles, in solar winds you'll have electrons and neutrons and protons, some atomic particles, but you'll have ions of iron and ions of other elements. They will be heavy and they are huge in numbers. It's massive. So initially we thought that these ejections would be coming from the outer layers. So we have termed it as coronal mass ejection because the outermost layer of the sun is corona. But now we have analyzed, and with the particle analysis it is clear it is not coming from corona. Why? Because the particles we observe are not in corona. The coronal composition we know, and the composition of corona is different than the composition of these particles. So it is coming from chromosphere, not corona. But name remains unchanged. It is still called as coronal mass ejection. But the latest research shows that it comes from chromosphere. In older books you will see that it's written in the books as well that they are coming from corona. But the research 1.5 years back that has revealed that they are not coming from corona. It is coming from the layer beneath the corona, that is chromosphere. Okay, how are they coming then? How are they coming? It is something to do with magnetic field lines. All the phenomena, the increase in temperature, all the phenomena are to do with magnetic field lines. You know, perhaps suppose there's a building and there are different floors. The lift that starts from the ground floor doesn't go to the first floor and the second floor, directly goes to the third floor. So you can have huge rush on the third floor. You can have huge amount of supplies going to the third floor directly. But the first floor and the second floor may be relatively calm. Too many people are not coming there, too many supplies not coming there, connectivity is not good with the first floor and the second floor. If you have arrangement like this, then your third floor can be very busy compared to your first and second floor, ideally, which is not the case. But because the arrangement of lift is such, then it could be the case. The magnetic field lines can bring energy from the convection zone, the third layer, directly and more to the fifth layer, chromosphere, and to corona. If that is done, then the inner layers will be bypassed. If you have a channel of magnetic field lines that is acting as a conduit of energy and bringing the energy out, so it is heating the outer layer, but it's not heating so much the inner layer. Perhaps this is just a theory. Perhaps something like this is happening. So it's all to do with the magnetic field lines. You might have in your earlier classes drawn the magnetic field lines of Earth. In your class 10th, you might have seen the pattern of the magnetic field lines of Earth in your class 10th chapter magnetism. Sorry. They do not touch, they do not cut. Your teacher must have explained to you that the magnetic field lines do not cross over. They do not cross over. They do not cross over. If they cross over, that means there is an intense amount of energy that needs to be stabilized. Intense amount of energy, and you have to untangle it. So when the magnetic field lines cross over, suppose because of some extraordinary situation, the magnetic field lines cross over here, this is not a stable pattern. This is not stable. And something will happen to stabilize it. And a sudden rearrangement of magnetic field lines will happen to rearrange the magnetic field lines. And when that sudden rearrangement happens to stabilize it, then the particle spikes out. At supersonic speed, the particles comes out. That is ejection. Coronal mass ejection, because everything is in plasma, it's in unstable states, and any sudden events can happen that can connect them, tangle them. They want to get untangled, and that perhaps is the reason why the particles that ejected at supersonic speed, such a high speed. Though it must be something to do with that. Coronal mass ejection. Okay, so coronal mass ejection comes from chromosphere according to our current understanding, not from corona, and something to do with the magnetic field lines. When the sudden events happen, like the two black holes, they collide, neutron stars, they collide, high energy also happens. Particles will come out, but energy will also be released. When energy is released, we call it flare, solar flare. Solar flare is radiation. It is also linked with the rearrangement of the magnetic field lines. Now they are correlated but not always. There could be cases that you're observing coronal mass ejection and not observing solar flares. But generally they come together, and those sudden events in the sun eject the particles out and releases energy as well. So that's that. So these will be happening now and then, every now and then. But solar wind, that is continuous. All right. Okay then. So much of basic would be good enough. So we did all of that, and you have to do, because we have a mission at L1. Aditya L1 necessitates that you understand all these things. Aditya L1 at L1 will be studying the solar wind. You know now what solar wind. We'll be studying the outer layer and the layer beneath and the layer beneath, corona, chromosphere and photosphere. Aditya L1 will study all the three outer layers. It will also study the coronal mass ejection. You know now what is coronal mass ejection. Space weather prediction. This is related to this solar flares and coronal mass ejection. So if you see the streams of high energy particles because of the coronal mass ejection coming out, then you can send alerts. So your satellites should be having the shielded part towards in that direction. Or you can, in extreme cases, change the orbit a little bit, a little maneuvering of the satellite to safeguard it from the incoming radiations. So space weather prediction is for our space assets. Space weather prediction will also have to become very critical when we have space tourism, when you have more human space missions. That will become very critical in the future. All right, so that's about Aditya L1. Aditya L1 study in X-rays and ultraviolet. Every information given here you have to absorb, and all the important information for the exam is here. Chandrayaan 3. In the recent past, Chandrayaan 3 also has been a major success of ISRO. Major success. We had Chandrayaan 1. Chandrayaan 1 was an orbiter. Chandrayaan 2. Chandrayaan 2 was a planned orbiter and a lander and a rover. Orbiter of Chandrayaan 2 is still there, but the landing couldn't happen so softly. So we had a hard landing, and that destroyed the lander and also then the rover in Chandrayaan 2. In Chandrayaan 3, that was our third shot for a lunar mission and second shot for a soft landing, and we got it right. Chandrayaan 3 was a success. Chandrayaan 2 was also a success because orbiter was already there, and lander while landing took a lot of images. Couldn't land, okay. But in Chandrayaan 3, soft landing happened, and soft landing happened, it was a great feat. Soft landing is difficult. Landing on a moving surface is even more difficult. So docking experiment that we did as a first topic is quite significant. Not an easy thing to do, because landing on a fixed surface is also difficult. Landing on a moving surface is even more difficult. We couldn't do it in Chandrayaan 2, but we did it in Chandrayaan 3, and we landed on August 23, 2023. This event was so important because it was our first lunar landing. This day is celebrated as National Space Day. India has become the first country, this is very important for you to remember, India has become the first country to land on lunar South Pole. Apollo, they have gone to moon in 1972. NASA claims that they have records for it. 1972, they have gone to the moon, but they were going to the equatorial region. In the moon, they were going in this belt or in the northwestern region. Mostly these are the areas where they have visited the moon. They were going in the equatorial region. And India is the first country to land in the South Pole. South Pole of moon is very, very significant. For the reasons that we will see in the next section, in the lunar section, South Pole, the reason why we are going to South Pole. But each and every planned mission, every means every, without exception, every planned mission of the moon is for the South Pole. Earlier they used to go in the equatorial region. Equatorial region is relatively easy to go because it is less rugged. The topography is easier in the equatorial region. But topography in the South Pole is very difficult. In the South Pole, there are craters, deep craters. In the polar region, there are very deep craters, so very deep craters. And these deep craters are so deep that sunlight through any angle doesn't reach there. So they are very dark and they are very cold. Minus 230 degrees Celsius is expected there, and there are ice sheets. There are ice sheets in these craters. and it is expected that they are preserving the original material after Big Bang. So from the science perspective, from research perspective, it is very crucial, not the equatorial region, but the polar region, the South Pole. So India was the first country. Earlier, all their missions, the Russians mission, USSR's mission, the NASA's mission, Chinese mission, none of them has gone to the south. They have been landing, no doubt, they have gone before us, but they have not gone to the rugged areas of the South Pole. India is the first country to land on the lunar South Pole. Remember that. And again, the fourth overall, you understand, the first three countries. Fourth to do a soft landing on the moon. So the mission was done earlier, but recently there are some news regarding this. Number one, you have to know that it has detected sulfur. Chandrayaan 3's lander has detected sulfur. So what does that mean? If you detect sulfur, what does that tell you? Do you know? Well, this is a general current affair update, so could be useful. SSC, you do not have to go very analytical, but of course, knowledge is always useful, And for SSC, if you're doing it, you can just stay for 15-20 minutes and see. These are quick updates, and you ought to know it for any competitive exam for that matter. Okay, Praveen. Okay, so now listen up, listen now. I was asking you something, and what did I ask? I asked you that it has detected sulfur. That's one of the major news among other elements. So if you detect sulfur, what does that tell you? It tells you about the volcanic activities. Sulfur. So volcano happens through the plate tectonic movements. There are already moonquakes that are detected there. So it tells you about the structure of the moon, that the plates that we have, the geological plates here on Earth, quite similar, that's there on the moon as well. So that's about sulfur. First in situ confirmation of sulfur on lunar South Pole. So this is your major news, which has been done by Chandrayaan 3 lander. First in situ confirmation of sulfur. Where? On the moon, lunar South Pole, because that's where we went. The point at which the landing was done has been named as Shiv Shakti point. You have to know this, and in prelims they can give a trap, put a trap statement. There has been many lunar missions, there has been many orbiters and their landers as well. Now we have our lander as well, but our lander has not detected so far water ice. If they give that Chandrayaan 3 has did a confirmation of the water ice on the South Pole, that will be an incorrect statement. Water ice confirmation has not come so far. So please keep a track of it, that they can trap you in the prelims statement. Okay, so Chandrayaan 3, these are the important updates regarding Chandrayaan 3. Chandrayaan 3, the lander and the rover, the Vikram, the rover, has performed hop experiment. Hop experiment. Hopping, you understand, the birds do hopping, getting off both the legs and landing, and you keep moving forward. Hopping. Hopping is important because in the future, hopping will be required more and more, because there are craters and there are deep craters. So if you have to move around in the South Pole, the topography is very rugged. It's very difficult topography. So if that is the case, and your rover is, we are again planning for a rover, and you have to send your rover. So if some crater comes, rocky terrain comes, if you can hop for 1 or 2 meters, 3 meters, 5 meters, and you can do a safe hopping, then that will be one good way of moving around on the surface of the moon. Okay, and that experiment has been performed, although it's on a smaller scale, 40 centimeter, but that experiment was performed by the Vikram rover in Chandrayaan 3. Chandrayaan 4. Among all the upcoming missions, I would say that Chandrayaan 4 is the most complex and challenging mission that ISRO is taking up. Chandrayaan 4. We have done Chandrayaan 3, Chandrayaan 4. Chandrayaan 4 will be our first sample return mission. ISRO hasn't done any sample return mission. We have not returned things, the satellites or the humans or samples, anything. We have only sent things from here. Sample return mission we have done none. They got sample from the moon. In the Apollo they got, I think, 382 kg of sample because it was a human mission. Sample return mission USSR also has done. They have brought the sample from the moon. Sample return mission has been done from asteroids as well, from comets as well. Interstellar dust they have brought back. They have brought back the particles from the solar wind from the sun, from L1. Lot of sample they have collected, NASA and JAXA and European Space Agency, 3 of them, they have done lot of sample return mission. We have not done any sample return mission. Very significant. This Chandrayaan 4 is very significant. This will be our first sample return mission, and there will be 5 modules here. And you have to pay attention. If you pay attention, you will understand it. There are 5 modules. There is descender and ascender module that will be in one group. Propulsion module, transfer module, and re-entry module. And there will be 5 modules. These 5 modules will be very heavy. First you listen. If you listen carefully, you will understand. 5 modules will make it very heavy, so heavy that our launch vehicle will not be able to pick it up. It will not. So they are divided into 2 groups. So in one group there will be 2 modules, descender and ascender, and in the other group there will be 3 modules, propulsion, transfer, and re-entry. So in 2 groups they will be sent in a gap of 1 month. So first one group will be sent, then in the second phase the other group will be sent. One group that will be sent will be orbiting around the earth and wait for the other group to come. When the other group is sent, then they both starts to orbit around the earth, and one come closer to the other and docks on the other, and they become 5 in the space. And that is the space docking. Space docking experiment we have done, and then I told you it's important for Chandrayaan 4. So in Chandrayaan 4 that docking will be required. So 2 we sent and 3 we sent, and they come together, merge on each other, they become 5. And from here the journey will begin towards the moon. So the propulsion module will take everything towards the moon. How does it take? I have given you in the beginning of the class. Things goes like this. How do they go? They go like this. They go like this. So it starts from Earth, and highly elliptical orbit will take it close to the moon. And from this side, suppose the moon is here, in the highly elliptical orbit, it will go close to the moon. And in every round, you decrease from this side, and you go on the other side like this. So start to orbit around the moon and leave the orbit from the earth. So it will take multiple rounds, and that propulsion module will help you in going from the orbit of the earth to the orbit of the moon. Slowly, gradually it will happen. When you start to orbit around the moon, then the job of the propulsion module is done. It's done, so it will fall away. So now you are left with 4. So this is gone, because you're already around the orbit of the moon. Now in the orbit of the moon, 2 will remain in the orbit of the moon and 2 will start to descend. So the descender module will take the group descender and ascender down. So from the orbit of the moon, you have the soft landing on the surface of the moon. Because we already have done Chandrayaan 3, that's successful. So we know how to do soft landing on the surface of the moon. So we have done the soft landing of the surface of the moon through the descender module. Now we are on the moon. Descender module job is done. The 2 of them now are dispensed. Now in the ascender module, there will be a rover. From the ascender module, rover will come out and will rove and will find the right point to do some small drilling. And after drilling, will pack the material, and the packed material will be handed over to ascender module, and rover will stay on the moon. It is also dispensable. Now with the sample, ascender module will ascend from the moon and will come on in the orbit of the moon, where these 2 were already waiting, transfer module and re-entry module, and will hand over the sample to them, again docking and then de-docking. So the job of ascender module is also done. It is also not dispensable. Now there are 2 of them, the transfer module and the re-entry module, and this has the sample, and 2 will start their journey from there and come in the orbit of the earth. So as we went from the orbit of the earth to the orbit of the moon, the reverse of that, and that is the transfer module. So when it comes around the orbit of the earth, then its job is done. Now it is also dispensable. Now you have a re-entry module around earth, and it has to enter inside. entering inside brings you with crazy velocity. So you have to increase velocity and then have a control. You shouldn't have a strong crash somewhere. And how do you control? Parachutes, they fall in a controlled way. Why? Because there is a drag of earth that decreases the velocity. If it's not a parachute based system, then you have to have propulsion. You are being dragged towards earth, you have to bring the effluent down so that there is a push up. So that in a controlled way will bring you down. And then boom splash, either in Arabian Sea or the Bay of Bengal. And then we will go and collect the sample from there. So that's how it will come back. We do not have a reusable launch vehicle, something like that of Elon Musk, that properly vertical coming back re-entry will happen. Our re-entry will be in the water, both in the Gaganyaan mission and also in the Chandrayaan 4. And that's how the sample is going to come back. So it already sounds complex. Doing it will be hell of more complex. It will be a very advanced mission. Why it's like this? Because we have a lower engine capacity in our launch vehicles. Our launch vehicles compared to the global launch vehicles are not of very high capacity. Even Japan has a bigger launch vehicle, more powerful launch vehicle. Our launch vehicle's capacity is of 8 ton, 8,000 kg, 8 ton, 8 ton. Our launch vehicle capacity is 8 ton. NASA's most powerful launch vehicle has a capacity of 130 ton. SpaceX, they have 110 ton. 110 ton. So that's something we are lagging behind a little bit. But this is the ingenious idea of ISRO, that we should not be limited in space exploration just because the launch vehicle capacity currently is on a lower end. So for the heavier satellites, if our satellites, some of them are 10 tons, so our launch vehicle cannot launch it. We get it launched from the French launch systems. Heavier ones, we own satellites, it's our satellite, but they are heavy, then that cannot be launched by our own. We launched other satellites. Remote sensing satellites are lighter. So remote sensing satellites, US satellites and French and Japan's and Germany's and UAE's satellites, we launched by PSLV. We launched PSLV satellite. Nepal recently had a satellite in the mission that failed of PSLV. We launched satellite of many countries. But the heavy ones we cannot manage ourselves, but the heavy satellites we take help of generally France or Japan, sometimes US. So the thing is that, but we are not limited by it. By having this docking experiment and docking them in the space and then again docking it in the orbit around the moon, we are pulling it off. This is the design of Chandrayaan 4. It's going to be amazing mission of Chandrayaan 4, and a lot of intricacies will be required. Heart will be throbbing at every stage. If they do not dock properly, then it's failed. And if they do not, ascender will come from the surface of the moon. We have never done that. Lunar ascent, we always had our launch vehicle from the surface of the earth. We launch from the surface of the earth, then the rocket is lost and the satellite is in the space, nothing comes back. We have never done launching ever from other surfaces. We have not done launching from the International Space Station. We have not brought back. We have never worked with that. We have never launched anything from the other planet. We have launched nothing. We have only gone to the other planet, like Chandrayaan 3. Chandrayaan 3 has done landing on the surface of the moon. It has not done ascent from the surface of the moon and come back. But this time it has to come back. So far we were only sending in the space. Now to bring it back, it has to start an ascent, come to the orbit of the moon, then the gravity assisted motion from the orbit of the moon to the orbit of the earth, the transfer. Okay. But we have never done that. We have never done that. For the first time, we will do that. Very precision landing on the moon will be required. Docking will be required multiple times in the orbit of the earth. Then when the ascender comes and the re-entry module and transfer module will be waiting, it has to dock and hand over the sample, then have to get de-docked, and these two starts from there. So multiple docking will be required and the ascent from the moon will be required. Earth re-entry, I told you things move with crazy velocity at the earth re-entry. Earth re-entry, we enter towards the earth, we have come close to the surface, there's a chance of a hard collision somewhere. You have to control the speed. Controlling speed when the speed has a tendency to increase will also be a complex thing. We have not done re-entry. Gaganyaan will be our first safe re-entry. In the Gaganyaan mission, the astronauts will be brought back from the space. But we do not bring back in other missions. Gaganyaan will be done before Chandrayaan 4. So in Gaganyaan we will do safe re-entry. Chandrayaan 4 will be our second re-entry. So the mission is quite complex and very ambitious. This will be our first sample return mission. That's Chandrayaan 4. We are also planning Chandrayaan 5. Chandrayaan 5 is also called as the LoopX mission. Chandrayaan 5 is a joint venture between ISRO and JAXA. Chandrayaan 5 will have the component of lander and a rover. You have to take a good note of it that there is no component of orbiter. Chandrayaan 5 does not have a component of orbiter. Chandrayaan 5 has a component of lander and a rover. Chandrayaan 5 is a joint collaboration between ISRO and JAXA. What about Chandrayaan 3? Did we have orbiter in Chandrayaan 3? Do you know? Yes, of course. Of course, Athulk, you are saying that how will they come back? Just like it happens in launching from the surface of the earth, it's a complete module, like the ascender module and descender module. So it will be like a mini rocket there. It will be smaller in size because moon is smaller in size, and so the pull from the moon is around only 1/6 of the pull from the earth. So it will be 6 times easier to pick something up from the surface of the moon. So it requires smaller rockets with a smaller amount of fuel. It gets easier. So it's a complete module. Just like the arrangement we have for the launch from the earth, there same kind of arrangement will be there for the launch from the moon. So that's why the complexity, I've told you, it's much more complex than it is sounding. It might already be sounding complex, but actually it is much more complex than what it sounds. Okay, that's a very ambitious design by ISRO. Announcement has been made, and Chandrayaan 4, the work will begin by 2028. Chandrayaan 5, I was asking you, do we have an orbiter in Chandrayaan 3 mission? Chandrayaan 3 had a component of orbiter or not? And the answer is no. Chandrayaan 3 did not have the component of orbiter. It had the component of only lander and rover. Why? Because Chandrayaan 2 already had the orbiter, and the orbiter of Chandrayaan 2 is already there. The problem was in soft landing in Chandrayaan 2, but the orbiter was placed in the orbit properly. So Chandrayaan 3 did not have the component of orbiter. LoopX mission will also not have the component of orbiter. It will have component of lander and rover, because orbiters have been too many. There are many orbiters of NASA, there is orbiter of ISRO. So, and as much of observation as could have been done from the orbiter has been done. Now the time is to get on the surface and bring back the damn sample. Do some in situ research on the surface. So it's not the era for orbiter. For decades there have been lunar orbiter. So the component you have to remember will only be lander and rover. And you have to remember the lander will come from ISRO and the rover will come from JAXA. Do not mess it up, do not interchange. As you remember clearly for NISAR, L band from NASA and S band from ISRO. You have to remember this as well. You have to, dear. The lander will come from ISRO and the rover, which is a little more complex component, that will come from JAXA. What you also have to remember, who will launch it? The launch of NISAR was done by ISRO, was done by GSLV Mark II. You have to remember that. The launch of LoopX mission Chandrayaan 5 will be done by ISRO or will be done by Japan. Tell me, what do you think? If I give you this detail, then it will be easier for you to think a little bit. It will do drilling up to 1.5 meter. See, Chandrayaan 3 also had a lander and a rover. Chandrayaan 3 will also go to the lunar south pole, the polar region. It is also for lunar exploration in the polar region. Chandrayaan 3 is also for polar region. Chandrayaan 3 also had a lander and a rover. Chandrayaan 5 will also have a lander and a rover. So what's the difference? What's the difference? We are going exact at the same point. We are going with the same components as we already have gone in Chandrayaan 3. Difference is that in Chandrayaan 5, the drilling will be much deep, 1.5 meter. You understand how long this is? This is higher than the height of the human, 1.5 meter, or at least my height, 1.5 meter. 1.5 meter drilling. Have you seen in the construction site? The construction site drillers, they are half a meter. The strong drillers are half a meter, and the man is using it. His body is shaking like crazy. The one who is using the drilling machine, not easy to control. You have to have a good stabilizing system to have a driller that drills this deep. You have to have a huge driller, and that will be in the rover. So the rover will be huge, of size of a SUV. Huge size of the rover would be there, huge size. So since this is huge, that's the thing. The thing is that although it has the components lander and rover like Chandrayaan 3, is also going in the polar region like Chandrayaan 3, but unlike Chandrayaan 3, it will do deep drilling. And after deep drilling, the sample will be collected because there are ice sheets. So you have to drill through the ice sheets into the deeper region, and that is why it is different. It is different. So this is, you can say, a bigger version, a grander version of Chandrayaan 3. Now you tell me, whose rover are you, whose launch vehicle are you using? Should be ISRO. Good, very nice, very nice. But good that you're thinking, and good you are participative. Point is that I'm telling you that it is size of a SUV. The driller will be huge, and if it is huge, then it will be heavy. And now you understand, if it is heavy, we can't launch it. We have a limitation. So the launching will be done by Japan. This information is not here, but this PPT will be attached to the video section. I don't know if it's already attached. If not, then after the session, I will get it attached. But the vehicle name is H3. H3, this is of Japan. And Japan's H3 will launch it. It is not in our capacity to launch. Such a huge heavy mission, we cannot launch. So we will launch from Japan using the launch vehicle of Japan. Remember that, that's very important. Going in South Pole again, and China has the Chang'e series for lunar missions, and it will be similar to the Chang'e 7 mission of China. But in the next section, I'll deal with the Chang'e series of China. Regarding ISRO's mission, there's also a very important update on Exposat. Exposat will stand for X-ray polarimeter satellite. X-ray. You know, this is our second space observatory, and this is India's first and world's second dedicated X-ray polarimetry mission. India is only the second country, only after NASA, to have a telescope that will study dedicatedly in the X-ray region. We have other observatories. Aditya L1 is also a space observatory, and Aditya L1 studies in ultraviolet and soft X-rays, not in the entire region of X-rays. It doesn't study in hard X-rays. I've told you one thing, and I'll tell this many a times: higher the frequency, more difficult it is to design the instrumentation. There are very few telescopes that studies in gamma rays. Studying in X-ray is also very difficult, so difficult that in the entire range of X-rays, the higher frequency X-rays as well, the hard X-rays which they are called as, in that range as well, to study there you require very, very difficult instrumentation, and only 2 countries have done it. So after NASA, ISRO is the second space agency to have a space observatory in a dedicated X-ray region. This is no mean feat. India is the second country to have it, so you have to remember that. And why do you have to study the universe in X-rays? Why is it important that you study in the entire region of X-rays? Why is it important that you study the hard X-rays as well? What would happen if you start to study in X-rays and gamma rays? Then compared to, let's say, soft X-rays and ultraviolet, that is the main payload in Aditya L1. Why do you want to study in X-rays, hard X-rays or gamma rays? Can you tell me? Why are you looking for this? Say. Who will say? I will say. You're not saying that, I'll say. Now, thing is, see, hotter the object, the higher the energy. And if you're studying intense events like the merger of the neutron stars, the collision of the black holes, more intense the event, higher the energy. And higher energy will be released in gamma rays and X-rays. So if you do not know how to study the in gamma rays and X-rays, then there will be intense events in the universe that you cannot study. So to study very high temperature, again gamma rays and X-rays. To properly study the sun, gamma rays and X-rays. To study the intense events, gamma rays and X-rays. Any high energy radiations will be in the range of gamma rays. If nuclear reactor is working, gamma rays are released from there. In nuclear fission, gamma rays are released. So if you want to track which country is, perhaps if you want to know for the reconnaissance intelligence activity, which country is running the nuclear program, gamma rays you'll find there. You have to know how to detect gamma rays. So it's very important. And India is the second country. We have not reached to gamma rays, we have reached till hard X-rays. So in the entire range of X-rays, we detect. Polarimeter, you know, polarization is a phenomena where you can study the incoming radiation from different angles. That can tell you more, give you more information about the source. So all these rays, I'll not get into the technicality of it. If you understand, it's okay. If you don't understand, even then it's okay. It's the magnetic field lines and the electric fields. It's a sinusoidal wave of the magnetic fields and the electric fields that creates these radiations. All of them. X-rays, gamma rays, and ultraviolet and infrared and visible. That's what they are. Electromagnetic waves they are called. Why? Because they are electric and magnetic fields, and one is perpendicular to the other, like this. So when you change their angle and you study them, then you get to have more information from them. That is called as polarization. So polarimeter will do it to probe from where it is coming and what kind of material could be there, what kind of condition could be there. You use a polarimeter that does polarization. That's just to study the source. We'll not get into it. Nevertheless, it's a polarizer and it studies the space in higher radiations. Intense events in the space, higher temperature bodies in the space can be better studied with higher radiations. That is why it is important to have our instruments in this range, and ISRO has done remarkably well. That's one institution in India all of us are so proud of, has done remarkably well. Before that, we had another space observatory, and that was called as AstroSat. AstroSat was India's first space observatory, and that is multi-wavelength observatory. So that studied in X-rays as well, the soft X-rays, but in optical range as well and ultraviolet as well. These are easier to design. Telescope in optical range easy, infrared easy, radio wave easy, ultraviolet easy. Designing it in X-rays and then hard X-rays and then gamma rays, that's difficult. So we achieved this much in our first space observatory, which is called as AstroSat. And in the second space observatory, we have Exposat. Exposat is more advanced because it covers all the X-rays radiations, right? To study the black holes and the neutron stars and magnetars, you have to learn to study things in higher energy radiation. So that's important. Let's talk about another achievement of ISRO, NavIC. NavIC is navigation with Indian constellation. Previously, NavIC was named as IRNSS. That was the first name given, Indian Regional Navigation Satellite System. But then ISRO had ambition of converting that from regional to global navigation system. We didn't like it, and in the future it will become a global navigation system. So we changed the name. Now it is called as NavIC, navigation with Indian constellation. There are few things you have to know about NavIC. It is an old mission, and you know the NavIC series of satellites began to be launched from 2013. 2013 it became fully operational by 2017-18, and so it's not a new thing, but there are new updates that you have to be abreast with. So first let me tell you a little basic about it. It has a constellation of 7 satellites. Design is to work with 7 satellites, but it keeps 11 satellites. 4 are kept in standby. All the navigation system will have some satellite in standby, because if something happens to one, then your services will be dismantled. So 7 is the bare minimum, but always some satellites are kept in standby. So in the design of ISRO, they keep 11 satellites, but one at a time. At a time, 7 satellites are used. That is the design. Of this 7, 3 are in geostationary, and 4 are in GSO, geosynchronous orbit. The reason is that it has to cover region around India. It's a regional navigation satellite. It's not a global navigation satellite. So generally the navigation satellites, they go to MEO, medium Earth orbit. But we have 0 asset. There is no satellite of ISRO in MEO. You have to know that. For remote sensing, we have in LEO. For communication, we have in GEO, and our navigation satellite is also in GEO. The reason is, you will understand it very easily why we are not keeping it in MEO, because if you keep satellite in MEO, it will slip with relative to Earth. So it will not remain stationary. So if I want coverage only of this region, I do not want coverage of the Alaska region, and I do not want the rest of the Africa to be serviced, or Australia to be serviced. I want only in the Indian region. Then I cannot go to LEO, I cannot go to MEO. I have explained you this in the beginning of the class, that there are two orbits from where you can be looking at a particular point or a particular region. If you have satellites in GEO, then they remain fixated in the sky over a particular point on Earth. They do not move at all. So 3 are in GEO. They will not move even a point from the surface of the Earth. If theoretically speaking, but practically there will be slippage, and you have to keep on doing corrections. But never mind, that will be very closely following the points on. It will be almost stationary overhead. So there are 3 of them. And I've explained you already that a satellite moving in GSO goes in a pattern of 8 like this. So there are 4 of them. When this comes this side, this will go that side. They move, but a clever design ensures that they take each other's position. Similarly, there are 2 here, and they take each other's position. So at a time, if you see, at a time you'll have satellites in roughly this arrangement at a time. So you keep on continuing to serve this area because you have your assets above this region. That's a clever design ISRO has chosen. That is why we did not go with MEO, because regional navigation satellite you cannot do with MEO, because satellites move related to surface. So when the satellites are moving, it's not a problem, because in a particular region servicing is done by one satellite, moved, went away, the other satellite is coming in. So now this satellite will do the servicing. You have to do a handshake, and I am using GPS in my handset, so my handset has to connect with a satellite, but that satellite moved away. How will I get the signal now? I get the signal by another satellite. So handshake between the satellite is done. If it is moving, it's not a problem, but the thing is, as it is moving, the other one should be coming in, and as this is moving, the other one should be coming in. So if you have too many satellites, then there's no problem, satellite moves, but you still continue to serve a point continuously. But that you will require more number of satellites. So you can work from MEO, no problem, but then you require at least 24 satellites. We work with only 7 satellites. With 7 satellites, you cannot work in MEO. Right? With 7 satellites, you can work only like this. All right. All right then. So you have to understand, that's the clever design. So we are in GEO, 3 of them, and we are in GSO, 4 of them. So this was the design of NavIC. So we worked with a constellation of 7 satellites, 3 plus 4. The NavIC series was designed to work in 2 bands, L band and S band. And Government of India has updated on the PIB multiple times that NavIC is more accurate than GPS. So the statement is NavIC is more accurate than GPS. You have to go with a yes, because government has reiterated it many times. And the point is, the explanation that PIB also gives, that it works in two bands. It works in L and S band. Remember L and S band, I've explained you in NISAR. I've explained you L band and S band. And NavIC works in both L band and S band. You know, L band is further divided into L1, L2, L3, L4, L5. So specifically it works in L5 band and S band. So this is about NavIC. Now there are two updates on this. Two updates. It covers, in a region of 15, this is also from the static portion, it covers India and the 15 kilometer, this rectangular box around India. So it's a regional navigation satellite, 3 in GEO and 4 in GSO. In the new series, L1 band also has been added in the NavIC satellite. The handsets that we generally have may or may not be your handset be enabled to connect with NavIC. If you switch on the location button in your phone, then you connect with NavIC or GPS. Most of the phones are designed for GPS, not for NavIC. Qualcomm started to develop that processor to connect with NavIC as well. So maybe some of the handsets, they connect with both NavIC and GPS. So it will give you both the options to connect with NavIC or with GPS. But many of the handsets do not have the option for NavIC. Why? Simple thing. To communicate in a particular frequency, there has to be a particular design. The phone cannot communicate in all frequencies. It can communicate only in those frequencies for which it is designed. And it was never designed to communicate in L5 band. It was designed to communicate in L1 band, because GPS uses L1 band. We chose L5 band and S band because of higher frequency. L1 band ki frequency kam hogi. They work with L1 band. We worked with L5 band. But now a change has happened, that the new satellites that we are launching, because in 2013, for the first time, the satellite was launched in the NavIC series. And it has been how many years since then? It has been 15 years, 14 years. And you know that the replacement of the satellite will be required around this time. So some of the satellites now require replacement. Okay, so now the satellites require replacement, so the new satellites are being launched. When the new satellites are being launched, so the new versions, the better ones are being launched. They are now launched in two ways which are better. Number one, apart from L5 band and S band, the satellite also work in L1 band. Now you understand, the phones are designed to pick up the signal from L1 band, because GPS works in L1 band, but cannot connect with NavIC because NavIC was not using L1 band. If NavIC uses L1 band, then no major change is required in the structuring or the manufacturation of the handset. The same handset now can connect with L1 with NavIC as well, because NavIC also communicates in the L1 band. So it will become GPS interoperable. So the older phones with little bit of upgrade of software in the new update, they can allow you to connect with NavIC as well. But if the frequency range is different, software cannot do anything. The hardwares are also designed to work in a particular frequency. If NavIC's frequency is different, then the hardware has to be changed. So some phones can have it, but many phones will not have it. But now without any change of hardware, the phones can. So that is one change. The other change is in the new series, in the NVS series of satellites, for the first time, ISRO has started to use indigenous atomic clocks. Atomic clocks were imported. Rubidium based atomic clocks are made, and they were imported for so far, but there were errors in many of the atomic clocks. The slippage was high, so we manufactured our own so that we can do rigorous testing of those clocks, and for the first time we have started to use them. In the future, perhaps in all the satellites we'll have our indigenous atomic clocks, but in the series NVS series of the NavIC, for the first time indigenous atomic clocks have been used. That is a thing you have to know. So NavIC is a regional navigation satellite for now. Regional navigation system for now. It has 7 satellites. But there are global navigation system other countries have, like USA's navigation system is called as GPS. It has 24 satellites, but they keep 31. They keep some satellites in standby. Russia also has a global navigation system that is called as GLONASS, Galileo for European Union, and BeiDou for China. So these 4 countries or these unions, they have global navigation system. So there are 4 global navigation systems that exist. None of the other countries have it. Israel doesn't have it, France doesn't have it, UK doesn't have it, Germany doesn't. They do not have it. It's just the US, Russia, China and European Union. These 4 powers have a global navigation system. There are 2 regional navigation systems. One is of India and the other is of, do you know? The other is of, you can write that in the comment section if you wish, because there is some lag. Perhaps what I am telling you will reach to you after a few seconds. Okay, so there is a little more update of ISRO, and then we'll go to the global space systems, space agencies, and look at the updates from China and JAXA and NASA and other space agencies. You see, there's something in news called as CROPS 1. CROPS 1. CROPS 1, you know, there has been experiment on seed germination. A cowpea seed has been seen as to how it germinates in the space. The idea is, these experiment has been done on the POM platform. POM is PSLV Orbital Experimental Module. PSLV Orbital Experimental Module. PSLV is what? PSLV is our launch vehicle. It's a polar satellite launch vehicle. What are the satellites which are polar? Polar satellites are the satellites that goes to SSO, Sun Synchronous Orbits, which is also a LEO, a special LEO, which is a SSO. So polar satellite launch vehicle. It has 4 stages: solid, liquid, solid, liquid. There are 4 alternating stages in PSLV, and the 4th stage is used in the experiment. You know what the thing is, that the first stage of any launch vehicle is always solid. Always solid, because in the first stage you have to get out of the field of the earth. The highest pull from the earth is experienced in the first stage. That's right. So in the first stage you have to have highest amount of impulse to get away from earth, and higher impulse will come if the engine is doing fast combustion. And for fast combustion you have to have more supply of fuel, and supply of fuel is always higher in solid state because material is more dense in solid. It burns like crazy. The solid state can give you higher density of fuel, so rapid burning, more impulse, and more impulse gives that thirst to get away from earth. First stage in any rocket is solid. By 50 to 60 kilometer away from earth, gravity becomes substantially less. So now this stage is not required anymore. So much of pressure you do not require anymore. Now it's get easy to move away from earth. You're almost reaching space. So the solid state is spent. It comes down, burns in the atmosphere. It's gone. Now you have only 3 stages. The liquid stage will require liquid stage when you require control. When you are launching it, you know, it can meet some atmospheric disturbance. Maybe a jet stream, maybe the satellite hits the jet stream and get deviated. The cyclonic weather could be there multiple times. Air breezes, that will also create some drag. So now you are out of your trajectory. You have to come back on the trajectory. The first stage was getting away from earth. So you have managed that. But now in the process, when you're tearing through the atmosphere, you may have got dragged from your trajectory. So now you need a control and to put yourself on trajectory. Control always comes from the liquid phase. These phases are the state of fuel. Liquid stage means fuel is in liquid state. If the fuel is in liquid state, then you can have a nozzle or a valve, and you can increase the burning, you can decrease the burning. You have a control. You have a control, but in solid you have no control. When it starts to burn, it will burn. You cannot stop it. If it stops, you cannot restart it. There is no control in the solid fuel. It just burns like crazy and take you away from earth. And then you require control in the second phase to improve the trajectory. That is why the second stage is liquid. Then third stage again is solid. Why? Because you have to increase the orbital velocity. If you do not increase the orbital velocity, the satellite will not stabilize in the orbit. So if you cannot be having a lower velocity and placing it somewhere, you have, before placing it somewhere, you have to have very high velocity. So you have to increase the velocity again. So again you require a solid stage. And then proper placement at GTO at the right exact point, you again require control. So the last stage is always liquid, properly placing it in the correct orbit. So if you see the distance of many satellites, it's between 600 to 800, but some are in 650, some is 653, some you will see 676. Those numbers are very precise. So you require precision towards the end. So you require liquid stage again in the fourth stage. So that's why the design is solid, liquid, solid, liquid. Now, this you pretty much be knowing already. The thing is that the update is now all these were spendable. Nothing is reusable. In reusable, you know what? It goes and come back. So the solid stage, what we do is, the purpose of the solid stage was to take it away from Earth, and once it's away from the Earth, job is done. We don't need it. It gets detached. When it gets detached, then the weight decreases. So it gets good to detach it. Why to hold it? So you could have held it as well. If you hold it, then it has done its job, then hold it. No problem if you still hold it. But if you detach it, then it becomes easier to take it forward. So as the modules do their job, they are detached and they burn in the atmosphere on their way back. That's what we do. But if you protect them and properly bring them back slowly, so the friction is not very high, so wear and tear is not very high, forget about burning, they're not burn, and wear and tear is low, so in a controlled way you bring it back. That will be reusable and again you can send. But we don't bring it back in a controlled way, we allow it to burn in the atmosphere. It's gone, it's spendable. It's spendable, it is not reusable. So in the last stage, this has gone in the space already. So last stage will not burn, there is no atmosphere there. Last stage will not burn. But what will happen to the last stage? The last stage will become debris. And so far we didn't care about it, because so far we were fixated only in the launch of the satellite. So now all these four are gone, the fourth stage become debris in the space, the three stage come down and burn in the atmosphere, and we forget about our launch vehicle, it's gone, only one time thing. But the fourth stage will not burn, there is no atmosphere there, it's not coming down as well. Nothing comes down, they have a tendency of going up in the atmosphere. But the fourth stage is used as a platform now. It becomes an experimental module. That's the POEM platform. So uses the spent PSLV fourth stages as orbital platform for experiment. So now when ISRO is diversifying and we are doing microgravity experiments also, and we are doing other research work, it's not a satellite launching company anymore. ISRO was in the beginning, no doubt, the whole purpose was to launch remote sensing satellites. But now the goal is diversifying, so now we are using the fourth stage to do some experiments, and fourth time it has been done. The fourth time the experiment was on the seed germination. So it was a POEM 4 platform. POEM 4 platform, 3 times as earlier also ISRO has used it. So seed germination, we want to see how things are different in the space. Do you think things will be different in the space? Do you think? Like the germination will be different, and the cell division will be different, and the alloy formation will be different, and the sedimentation will be different, the fluid dynamics will be different, or will it just be the same as on Earth? On Earth we have gravity, and all these processes are influenced by gravity. But in microgravity condition, the process surely will be different. You also might have read in the news that there is a plan to have a semiconductor factory. To have a semiconductor factory in the space. Why do you want to have a semiconductor factory in the space? To develop semiconductor wafers. Why not on Earth? What will be the advantage? When the semiconductor wafers are made layer by layer, then in the influence of gravity, the perfect crystal gets distorted. Even when the alloys are formed, one alloy, you bring two metals, one will be heavier, other will be lighter. It will not be a perfect solution. Under gravity, you break that perfection. Microgravity will do the distortion less. So the semiconductor crystal will be better in the microgravity condition. An ambition to have a factory in the space already has been shown. and countries like UK, US already started to work on it. So space offers microgravity condition, and the physical process will be different, fluid dynamics will be different, alloy formation will be different, semiconductor manufacturation, that will be different, cell division is different, seed germination will be different. I'm trying to do all of it in the space and see. So now these experiments are becoming the frontier end, and space technology offers these experiments to happen. They were doing experiments since ages in their International Space Station. They do experiments in the International Space Station. We don't have a space station, and we didn't have a focus here. Now focus is shifting, and we are carrying experiments in the fourth stage. What a ingenious way. We don't have a space station, but experiments are being carried out in the fourth stage of PSLV, and in the future we will have Bharatiya Antariksh Station. So that's about POM platform, and that's about the CROPS-1 experiment. It has been observed that in the microgravity condition, the process change, the folding of proteins, that change. Cell division is less effective. People start to age. If you see the astronauts coming back from the space, they look quite old for their age. You look old when you are wrinkles. There are wrinkles, that means cells are not being formed. It's not stiff, not healthy anymore. Cells are not forming properly, so you become old and frail. You look old and frail, quite old and frail for your age. Astronauts having too much of time in space, they look quite old for their age. If you have seen their pictures, seen their interviews. The thing is, that's why cell division is not effective, and these experiments have proven these things. So that is something you have to know. Now there are other important updates on this slide. Like India, you know from where we launched the satellites in India? What is that place? Do you know? Do you know? From where do we launch our satellites? We launch our satellites from Sri Harikota. All our satellites are launched from Sri Harikota. So we have only one spaceport. Our spaceport is in Sri Harikota. India is planning for a second spaceport, and the second spaceport is going to be opened in Kulasekarapatinam in Tamil Nadu. This is important. This will be India's second spaceport. Currently we have only one spaceport. So we are launching more satellites, and we have deregularized the space sector, and there are many private companies now coming up in the space sector with their own satellites. So the demand to launch the satellite has increased substantially, and one spaceport will not be enough. So another spaceport was required. That is there. You have to know the name, Kulasekarapatinam in Tamil Nadu, and this is in the southern tip of India. If you do a little bit of Googling, and you please do, don't sit like dead duck, do. If I ask questions, please answer. And if I ask you to check something, please check. If you check the location, if you on the map, if you check the location for Sri Harikota, and you see if a landmass lies below it or not, and if you see on map the location of Kulasekarapatinam, and if you see if a landmass lies below it or not, you will understand, you will realize this, that the landmass of course lies below Sri Harikota, and that landmass is Sri Lanka. Okay, but there is no landmass below Kulasekarapatinam, and that is a very significant thing, You cannot be taking the satellites or your missiles over another landmass of other sovereign country. Especially for satellites, in the beginning there is a chance of crash. If it crashes, then it will crash on the landmass. Ballistic missiles, they do not crash. Well, the launch failure of missiles are rare. Launch failure of satellites are not rare. They do happen. And if the launch failure happens, then it will all become debris quite early, will not burn completely in the atmosphere, and will fall. Substantial mass of it will fall. So the point is that that's not done. You never cross the satellites in the initial phase over a landmass. So we do it from Sri Harikota, because on the eastern side we have Bay of Bengal, and we launch it like this, eastward. Satellites are always launched eastward, because southward you will have a problem of Sri Lanka. So satellites are always launched eastward. These will be doing very fine if you have, this is suppose Earth, and we are in this equatorial region here. If the satellite has to go in the equatorial plane, suppose there is a LEO, if that has to go in the equatorial plane, or we are sending it to geo, that's there in the equatorial plane, no problem. You launch the satellite eastward, no problem. It falls on the in the water, and the orbit is also placed like this, so no problem. But if you have to send it to the polar satellite, and you know that the remote sensing satellites, they go to the polar satellite. If you have to go to the polar satellite, you have to go southward. So what is done is it's sent eastward, and from here it goes southward, and that is called as dogleg maneuvering. To avoid flying through Sri Lanka, this maneuvering will require more fuel meaning you are starting with a higher weight. If the weight of the engine and the fuel is high, that means the weight of the satellite will be less. But in the southern tip allows the rocket to launch directly southward over the Indian Ocean to reach into the polar, the sun synchronous orbit without any maneuver over land. So this saves significant fuel. So the choice of Kulasekhara-Pattinam is precisely because of this reason, and you have to know this for your prelims exam. So if there is no dogleg maneuvering, then the fuel will be less, the weight will be less, then you can increase the weight of the satellite. So relatively you can go with a relatively heavier payload. That's the thing. So this update is crucial, you have to be abreast with this. Space-based experiments, we go to the space for many reasons. Microgravity, as I told you, many things, alloy formation, crystal formation, fluid dynamics, that's changed because of gravity. You want to see how material behaves in microgravity, you have to go to space. So space-based experiments are for multiple reasons. One of the reasons is microgravity. Hard vacuum, that's difficult and expensive to create here, but you have that already in the space. Unfiltered solar radiation, if you have to study that, solar winds, obviously you have to go to the space, because on Earth that is filtered by atmosphere. And there is a better vantage point, because the telescopes from the surface cannot study the outer space clearly because of interference from the atmosphere. So you go to space for multiple reasons, and there are many experiments done for microgravity in space, like growing near perfect semiconductor crystal. They are attempting for this, experiments have been done, now they are trying to have a factory in the space. Formation of new alloys is studying fluid physics. They will solidify, when you bring back on the surface, then the gravity will not change the crystal. When the crystal is being formed, gravity alters the perfect arrangement of the crystal because of differential mass, and gravity brings imperfection. So having the alloys up in the space, making the crystal up in the space and bringing it back, that will work. They have been doing that in the International Space Station. You know, Bose-Einstein condensate, in schools you must have done, there are three states of matter: solid, liquid and gas. And then as you grew up, you know that there is a fourth state of matter called as plasma. And then as you grew up, might be, I don't know you're grown up or not, but if you have grown up enough, you would know that there is a fifth state of matter called as Bose-Einstein condensate. Bose-Einstein condensate is the fifth state of matter. Professor Satyendranath Bose, he was the prime mover of this idea, and he approached Einstein, presented idea to him. Einstein was graceful enough to have an article published in the Science, a very prestigious magazine, in the name of Professor Satyendranath Bose. And then later Einstein also worked independently on it and developed proper theories for it and gave more teeth to the idea of Satyendranath Bose. So Einstein also did contribute substantially, but originally the idea, statistical model, was of Satyendranath Bose. To honor both of them, the state is named in their name. So the fifth state of matter is called as Bose-Einstein condensate. But this is very fragile, and it is crucial to have experiments on this to prove part of the theory of Einstein. Theories of relativity can be partly tested on Bose-Einstein condensate. If there will be time in next week, we'll discuss these things from the particle physics section. But Bose-Einstein condensate is the fifth state of matter, very fragile, very difficult to construct them and stabilize them on Earth, because on Earth there are magnetic field lines, there are electric field lines, there are radio noises, there is gravity. Very difficult to do that. Much of the experiment on Bose-Einstein condensate has been done again in the International Space Station. So microgravity is required for this reason as well. Burning of flame, fluid flows, formation of foams, they all are affected by gravity. So in near zero gravity condition, how do they behave? We want to know, we have to go to space. So the many of the experiments in the space in the recent time has been precisely because space offers microgravity condition. There have been many biological experiments, like I told you, that cell division, and it has been observed, the result has come that the cell division doesn't happen properly in space. You know, there were twins of Scott Kelly, a twin, and the one twin was on Earth and the other twin was in space for substantial amount of time. And then the study was that there was a bone density loss of the twin in the space. Genetic expression started to change. There is vision impairment in space. Body doesn't grow properly because cell division is not proper. So if you want to test something, some medicine for Alzheimer, that's a problem in Alzheimer patient as well. So then the testing of the medicine can be done in space, because in space cell division is less effective. That's the problem in the patient's body as well. So it is very rewarding actually to have the experimenting platforms. For many reasons we want to go there and do experiments. That's why the POEM platform has begun, and that's why these experiments coming on the POEM platform. Protein crystallization, again that will be influenced by gravity. Perfect crystals that cannot be formed on Earth because of gravity. So better design of the drugs that can be done. We are talking of the semiconductor manufacturing factory in the space. Maybe those drug manufacturing factories in the future can also come in the space. Growth of plant, how the photosynthesis happens, how the seed germination happens, the veggie system on ISIS, ISS, not ISIS, ISS, International Space Station. That is done there, and they are working on it. You know why? Because there's a grander plan to have a human permanent post on the moon. And if that's the case, to have a permanent human post on the moon, lunar post, then these things are important. We have to learn as to if photosynthesis can be possible in the lunar soil in those conditions. Of course, within the casing, but within the casing as well, if that is possible. Okay, now let's do some lunar missions. Let's take break for 10 minutes, and after 10 minutes we'll be back. So around at 1:12 we'll start it again, and we'll see as to how much of it we can complete today, then maybe next week, and maybe also a third week to do it properly. I'm not rushing it and I'm not jumping it. So maybe to next Sunday again, or maybe next to next Sunday as well, we'll have sessions. So let's take 10 minutes recess. All right. Okay, we are back, and I hope the full screen is visible to you, right? Okay, yes. Now we are back, and we are doing lunar missions. Lunar missions, there is a phrase in the news called as lunar rush. Everybody going to moon. There's a lunar rush because there are many reasons why there's a lunar rush. We'll do that, but there are economic reasons, and there are strategic reasons, and technological reasons, and there are scientific reasons that the interest in moon has been revived. They went to moon in 1972 in Apollo mission, and then they lost interest in the moon. Then they got interest in Mars and Venus, and they are in the interplanetary spaces. But the interest in moon has come back. It has been revived. The major mission currently going on, the lunar mission, among all the lunar mission, is the NASA's Artemis program. This is the major mission of the moon. There are many phases in which the Artemis program will be done. Artemis 1 was uncrewed mission. It was testing of the rocket, their launch system called as SLS, Space Launch System. Sorry, Satellite Launch System, SLS. And it is the NASA's satellite launch system and Orion capsule, the spacecraft that will be launched, in which the astronauts will go. So the uncrewed testing, that was Artemis 1, it has worked, it has gone around the moon and has come back without humans, the systems they have tested. Artemis 2 was the first crewed lunar flyby. It did not orbit around the moon, but it was a flyby, so it flew in the spaces near the moon and came back. It was a flyby. So with humans, flyby has been tested. Now what? Now the final landing in Artemis 3, which is yet to be done. Artemis 1 and 2 they have done. Artemis 3 is yet to be done, and humans will land again, since they have done it in 1972 in the Apollo mission. So they will land on the surface of the moon in Artemis program. As I have told you earlier, then all the missions, all means all, without any exception, all the missions of the moon which are planned are being planned for South Pole. So Chandrayaan 4, South Pole. Chandrayaan 3 was in South Pole. Chandrayaan 5, South Pole. Artemis mission, South Pole. Chang'e of the China, South Pole. All the planned lunar missions are for the South Pole. So they have done the landing last time in the equatorial region in 1972. The landing this time will be in the South Pole. So it will be then first human landing at South Pole, because the previous human landing was not at South Pole. But the first landing on South Pole, that was of ISRO. First landing on South Pole. But that was a robotic landing. First human landing of on South Pole will be of NASA. You also have to remember that the lander will be SpaceX, the lander. The landing will be done by Starship. Starship is the vehicle through which the landing will be done. Like I have given you the different modules in Chandrayaan 4, the descenders and then the ascender. So SLS is the launch vehicle that will launch everything from Earth. It's a very powerful rocket. And launch where? I told you in the beginning that none of the rockets take it to the destination. They will not take it to Leo. Forget about taking it to the moon. That's very far away. Very far away. So where will SLS take it to? SLS will take the entire system from the surface of the Earth to GTO. That's it. And from there you have other modules to go to the orbit, around the moon and then descend. So you will have the Starship of SpaceX as a descender. But when you descend, you also have to ascend, because you are coming back. You're sending humans, they are coming back. This descender and ascender module will be given by SpaceX. So SpaceX is working in close coordination with NASA in the Artemis program. All right. SLS capacity of SLS is 130 ton. It can lift the whole payload of 130 ton. That's the strongest weapon that we launch vehicle that we have. It's the most powerful rocket that humanity has built. Then once Artemis 3 is done, they have a plan for Artemis 4. Under Artemis 4 plan, they will go and come back in 3 days. They'll spend time in moon 72 hours and then they will come back. But in Artemis 4, there's a plan to have a post, a lunar post. Like there's a permanent post, International Space Station. So astronauts come and go, but some of them are always there. So a permanent post on moon, they are planning for that as well. And that will be very ambitious mission. Like International Space Station, people are there all the time. A permanent post on the moon. And that will be the plan for under Artemis 4. It's a grand plan. There will be many private sector involved, and NASA will also involve JAXA, Canadian Space Agency and European Space Agency. So Russia and China are not part of it. Russia and China, they have not signed Artemis Accord. They have not. India has signed Artemis Accord. That's right. India has signed Artemis Accord. Russia and China, they are planning their lunar outposts separately. So there is a joint mission of Russia and China to do something similar to Artemis 4. And they're also on it. They're also making progress. Now the question is that why South Pole? There are many reasons why they are going to South Pole. In the next slide, I have all the reasons listed down. Why South Pole? We'll talk about it separately. So why South Pole? Yeah, here it is. Why South Pole? South Pole has water ice. How do we know? This has been confirmed by many of the missions. We have orbital missions. Right now there is no lander. They don't have any lander. Chandrayaan 3, it was the first lander there in the South Pole. So the information that we have, that is from the orbiter, and that is a clear information. We have clear indication of the water molecule in the South Pole. Icy, very low temperature. So it is considered that the original materials must be here. So from science perspective, it is very important. It's like a scientific archive. The ultra cold traps preserving volatiles and the original materials after the Big Bang. It is expected that to look in the past of time, these materials can help us. It can give the solar system history and also some clues as to how the Earth's surface may have changed over time and how the life on Earth would have come. So from scientific perspective, it is very important. Since ice is there, so life support for the permanent post can happen around there if you can learn how to use the water and purify it from the moon. The thick ice shield will also help protect from the radiation that's coming from the sun. Radiation is coming from the sun there as well. So you have specialized suits to protect yourself from that. Radiations will come on the moon, in the South Pole as well. South Pole has lower inclinations, but when you're around in that region, radiation will be there. So maybe a permanent post will be in craters where lights does not come. The ice sheets are there that protects from the radiations. So South Pole is a good point to go. From safety perspective, a good point to have a permanent post, a good point for scientific purpose as well. So in the South Pole near the craters, the points near crater, they are such that they are dark and they're cool and they're safe and they provide protection against radiation, and they also have original materials. And if you come close to these regions, you can have permanent sunlight here. So if you have to charge the batteries, you know what's the source of energy? The source of energy, battery is the source of energy for the satellites, but the battery will not last very long, so it has to be recharged. How the battery gets recharged? Through solar energy. So the main source of energy for the space mission is the solar energy. The batteries get recharged and you can do the operation, battery based operations again and again. That's okay. You can run the engine also from electrical energy. So, but you need to keep converting the solar energy into the stored energy of the battery. Some of the missions, they carry nuclear energy. Some of the missions, they have some isotopes of plutonium, and they break down, they release energy. So that's another way. But the safer way is the solar energy, use solar energy. But solar energy will be available only if there is sunlight. If you are into deep crater, you cannot have solar energy. So you have to do drilling here. Remember Chandrayaan 5. Chandrayaan 5 will do drilling to 1.5 meter, and drilling will require energy, and energy you will exhaust at some point. You will have to come back before you exhaust energy and charge yourself here and then get there. Okay. So it's a near constant sunlight near those craters. So that is a spot where you can have all the activities done. It's also a quiet zone. If you go a little southward, I hope you know that moon is tidally locked. Moon is tidally locked, meaning we see only one side of the moon always. Are you aware of this? We do not see both sides of the moon. So there are two faces, two hemispheres, one towards us and one opposite to us. It is said that moon is tidally locked, meaning we do not see the other side. Suppose this mobile phone. If I turn it like this, I see it. If I turn it like this, I see it. So if it is rotating, if it is rotating, I can see both the sides. Moon does rotate. Moon do rotate. Moon also revolve. But the point is, if it is rotating like this, one side faces me, and the other side faces you. Okay. And it rotates and it revolves. So it is turning and it's also revolving. So the thing is that this side is facing me. If it does not rotate and only revolve, it comes here and I see the back side because it does not rotate. But it rotates and revolves both at the same speed. So by the time half the circle on revolution, half the circle on rotation is also completed. So let me do it step by step. Half the circle of revolution is here and half the circle of rotation is here. So again I see the same side of the phone. So because of the rotational time and revolution time being the same for the moon, we are not able to look at the other side of the moon. You can think about it a little bit, it will become clear if you apply your mind a little bit, or maybe watching an animation video on YouTube will help you in getting this clarity. Moon is tidally locked and we see only one side of the moon, and the prime reason is that the rate of rotation and the rate of revolution of the moon, that's the same. So it is tidally locked. So the far side of the moon is called as the quiet zone, because there are many radio waves around in the space we have created, because our ground stations communicate with the satellites using that. Communication happens in radio wave signal. So a lot of ground stations and there are many satellites have filled the space with the radio waves. Telescopes also work using the radio waves. So if the telescopes have to do astronomical studies, lots of signals actually can create distractions and interference from ground based stations. One of the best place in space to use your radio waves based telescopes and study the universe is the far side of the moon, because the far side of the moon is not visible to us and there is no communication from there. That's why it is called as the quiet zone. Okay, because there is no radio noise. You have to remember this. This is also important. This was one of the point highlighted in many of the articles as to why we are going to South Pole. So that's very good for astronomical studies. Very, very good. And in the future, it will be done. People have gone to the South Pole. China has a mission in the South Pole, the far side as well of the South Pole. Now, strategic high ground. For the future, moon can act as a test bed for Mars. And if we are successful in moon, then the harsher condition on Mars, the technological development for having a permanent post on moon in the South Pole will prepare us to go in a harsher condition of Mars. The series of China for the lunar mission is Chang'e series. Chang'e 1 and Chang'e 2, they were orbiters. Chang'e 3 and Chang'e 4, they were landers. Chang'e 4 first ever soft landing on the lunar far side. Chang'e 4 was a lander in the lunar far side. Chang'e 5 was their sample return mission. It's a robotic sample return mission that successfully brought 1.76 kg of young lunar soil. Chang'e 4 is also a sample return mission from far side of the moon. Chang'e 5 was from the near side of the moon, in the northwestern side of the moon. Chang'e 6 sample return mission, both Chang'e 5 and Chang'e 6, they are both, but Chang'e 6 is a sample return mission from the far side of the moon. You have to know this, these are very important information. So, first landing of the far side done by China, not by NASA. On the far side, first landing done by China, that was Chang'e 4. In Chang'e 6, they got the sample also from the far side. In Chang'e 5, they got the sample from the near side. So, they have done their sample return mission, and both 5 and 6 were their lunar sample return mission. Chang'e 7, a planned South Pole mission featuring an orbiter, lander and rover and a flying detector to search for ice. Their Chang'e 7 is like our Chandrayaan 3. We have gone to the South Pole, they haven't. They haven't. We had our lander and rover in the South Pole, they haven't. So their Chang'e 7 is like Chandrayaan 3. No doubt their rover will be heavier like Chandrayaan 5, but its mission is like Chandrayaan 3. Their Chang'e 8 is like Artemis 4. To have a planned mission to test in situ resource utilization and key technologies for future lunar research stations. So they are also planning for a lunar research station along with Russia, and they'll be competing with Artemis 4 of NASA. So these lunar missions are important. They are important. Qiao was the relay satellite for the far side communication. You know, in the far side, there is no line of sight. How would you communicate? If your mission is on the far side, then those missions do send information to the ground stations, correct? Lander and rover, our lander and rover, we have seen in Chandrayaan 3 that we have for the first time has a confirmatory test of sulfur in the South Pole. So that information has to be given to us. How does that happen? That happens through the radio wave. And for that, there has to be a line of sight. But they are in the near side. So in the near side of the moon, there is a line of sight. But in the far side of the moon, there is no line of sight. So you cannot directly communicate. How will you communicate? How will you communicate? You can't tear through the moon and give the information on the other side. How will you communicate from the far side? So from the far side, there is a relay satellite. The communication is with the satellite, and the satellite is visible to us, and it relays the information from the lunar mission to the ground station. So whenever there is a far side mission, it cannot be done ordinarily. It has to be done through a relay satellite, and China has done that. China is the only space agency to do that. So we have done some lunar missions, and we have done major missions of ISRO. Now let's do some other internationally important missions before we jump into defense. Maybe today I'd like to start defense maybe in a half an hour or 45 minutes, and the thing will continue. It's going to take more time because I'm taking it slow. I'm telling you important concepts as well. So it's not a hushy thing that we are doing. So it's going to take, I think, clearly 2 more classes, 2 more weeks. Solar Parker probe. Solar Parker probe is one of the most fantastic thing they have developed. Overall, the scientific community of humanity, one of the most fantastic thing is Solar Parker probe. Solar Parker probe is said to be touching the sun. Touching the sun. The outer surface of the sun, remember, is corona. So it will enter into corona, Solar Parker probe. So far the idea was to study the sun from far away. The best they had gone to earlier was L1. And then the flybys, going around, going closer to the Venus and then studying the sun from there, having a close contact and taking images from a close distance. But entering into corona, this is the first one. No mission ever has entered into corona. And you remember our previous discussion, coronal heating, temperature increases like crazy in the outer layer of the sun. It goes to 1 to 3 million degrees Celsius. So it's not a very easy environment to be in. But the Solar Parker probe has entered inside the corona. So why? Because it's so mysterious that they thought that we should be taking a closer look. They thought that some of the things can be known only when we approach the corona very close by. So they are gone close to the sun, into the corona. The purpose is to unlock why sun's corona is millions of degrees hotter than the visible surface, which is photosphere. The visible surface, photosphere, has 5500 degrees Celsius. Corona has 1 to 3 million degrees Celsius. Now, this is something that we do not clearly know, although we may take a guess, something to do with the magnetic field, but we do not have a verified information on that. We do not. So that's one of the purpose, to discover the accelerated solar wind. Discover what accelerates the solar wind to supersonic speed. The solar wind comes at very high speed. Coronal mass ejection also comes at very high speed. Of course, the temperature in corona is high, so the material is loose, so they may ooze out. But it's like something is launching them. Very high velocity, supersonic velocity, more than the speed of sound. That's supersonic. So what is doing that? Perhaps what is doing the first is also doing the second and is also doing the third. Determine how the solar energetic particles are controlled at near light speed. Particles, solar energetic particles, coronal mass ejection, they also come at very high velocity. So what's happening? What is happening is perhaps to do with the sunlight, sun's magnetic field. You see, the idea was to have 24 planned close encounters. Suppose this is sun and there are many layers of the sun, and the outer layer goes to millions of kilometers. This is corona around the sun, also visible during eclipse. This is the corona. So the thing is that there's close encounter. In one encounter, suppose it enters inside the corona, comes out. In the second encounter, it have a closer encounter, comes out. And then in third, have a closer encounter and come out. Quickly comes out. And in fourth, little more close and comes out. There were 24 planned close encounters of solar Parker probe into the sun, and that has been done. All 24 has been done. Now it will go closer and closer and closer till the time it has been completely burnt. Now you might be thinking that the temperature is million degrees Celsius. Now how can something survive in million degrees Celsius? How is it even possible? You have to understand something, that temperature, the measurement of temperature is based upon the oscillation of molecules. The faster it oscillates, more temperature it has. Like you see that when the boiling of water increases, when the boiling temperature is reached in the kettle, you can see the bubbles and you can see the turbulence, you can see the motion of the particles. Now it is acting crazy. It is not shant. The tranquility is lost. So there's a kind of correlation. Higher temperature, higher oscillation. Idea of temperature is oscillation. That's how the thermometer measures it. It feels more oscillation, it declares more temperature. Okay, but that's okay if the mass density is high. If the mass density is high, then high oscillations and more mass, then more amount of heat will come to your body and you'll be burnt. But suppose there's only one particle, only and only one particle in a huge space. That particle is oscillating at very, very high rate. Then the temperature of that place is very high, because that's how temperature is linked with the oscillation of particles there. Temperature will be very high, but the heat is very less. If the particles hits you, you'll not be hurt. You won't be hurt. It's not carrying that amount of energy. But there are many particles at the same rate, then you will be hurt. If there are many particles at the same rate, if the other particles are also oscillating at the same rate, then the temperature remains the same. Temperature is to do with oscillation. But the harm that you will have will be huge, because there are more number of particles hitting you. Temperature is not with number. Small quantity of water can go to 100 degrees Celsius and a huge quantity of water can go to 100 degrees Celsius. Temperature is not to do with the number of particles. Temperature is to do with the oscillation of particle, right? So if you decrease the density, very thin, very low density, temperature still will be high, but the damage will be less. Understood? That is why corona, it is 1 million, 3 million degrees Celsius, but the density is less, so there is chance of survival of a mission even in corona. How? Two ways. There are two ways in which it is done. There's a heat shield. It might be written in the other slide. There is a heat shield. They use heat shield. It's a very strong composite material. The side that is facing the sun can withstand on Earth 1400 degrees Celsius, because the material density is higher on Earth, right? And this 14 degrees Celsius on Earth is good enough for million degrees Celsius in corona, because the material density is very less. So there are very strong heat shields and there are reflectors, and the side behind it there's a cooling mechanism. This cooling system that takes the heat from the front and give it to the other side of the space, which are cooler. So heat is not allowed to develop because of the cooling system. That is one thing. The second thing, as you understand, is the speed will be crazy. It is the fastest moving object that humanity has created. Fastest human made object ever. I have given you in the beginning of the class some ideas regarding the orbital velocity. It can go to 10 meter per second. 10 meter per second in Leo. In Leo, the pull is from Earth. Sun is more than 10,000 times more powerful in mass than Earth, very heavy. The pull from the Sun will be at a much more than Earth. So something going around the Sun or moving around the Sun will be pulled with very high force. So the velocity around in the orbits of the Sun, that will be much more than that. You cannot imagine how fast things are going there. We have never seen that motion in any man-made object, not in our satellites in Leo. It's crazy velocity. You know, in Leo the velocity is such that if there is an inch of iron piece, 1 inch, that strikes a satellite will be blown away. That amount of momentum is in a small piece of iron because of velocity is very high. Mass could be less, but velocity is so high. Huge momentum in small pieces, good enough to damage the satellite. 1 inch of iron. So the speed is huge, and imagine the speed in something going around the Sun. So this is the fastest human made object. So it goes very fast. So what I am trying to explain you from here, since it goes very fast, so it does not remain in corona for a long time. It comes out, and there is a gravity assistance from Venus. So through Venus, the circle is completed in multiple gravity assist and then come back to touch the Sun again. So it doesn't spend much time here, number one, as heat shield, number two. Because of that, it is managing to be in the corona. It does not spend too much of time in corona. And that's the thing. All right. So that's how it survives. That's how it works. Now there have been many discoveries. It has been there for a while, and all the planned 24 close contacts has been done. There have been many things it has discovered, but one of the finest thing that it has noted is magnetic field reversals, which was expected, which was theorized such a thing could happen, and that has been confirmed by the solar Parker probe. A sudden U-turn that the magnetic field lines take. Suppose the magnetic field lines were like this. It breaks and the direction changes. So from there to this side, the magnetic field lines direction suddenly change. This sudden change in direction will require a huge amount of gush of energy. And these are the reasons perhaps for the things that we are not able to fully understand. Solar flares or coronal mass ejections or solar winds, as to why corona is so hot, coronal heating. Everything perhaps in some way is linked to it. But solar Parker probe has not solved all the mysteries, and solar Parker probe has not fully to say have done all the studies of the Sun. You know, more theories have to be developed first, and then the experiments can prove it or disprove it. So it's going to take long amount of time to fully explain things. Like in geography, you have studied the Earth so well because many experiments have been done. For a long amount of time, we have done many kind of experiments, and there are many detectors of the earthquakes. We can make their waves so easily, and we know our Earth very well because we have spent time. So it will take huge amount of time to know the Sun very well. You have seen the magnetic field lines of Earth. It's like a bar magnet. You have done that in class 8th. We do not know the magnetic field lines of Sun very properly. So solar Parker probe has not solved all the mysteries, but have given important observations that will bring us close to understand the sun. Solar missions are important. Overall, the entire solar missions are important. So you have to know other solar missions. So the solar mission, Solar Parker probe, that's the most advanced mission that is going towards the sun. You know, 6.4 million kilometer, that's the distance of closest approach, 6.4 million. The other point from where you study the sun is L1. And what's the distance of L1 from the sun? You know, the distance of L1 from the sun. What's the distance? The distance of L1 from sun is, I have given you in the morning, in the beginning of the class, between sun and earth, the distance roughly is 150 million kilometer. L1 is very close to earth, L1. Distance between L1 and earth is 1.5 million kilometer. So rest of the 150, that is 148.5 million kilometer, is the distance from L1 and sun. So a mission studying sun from L1 is 148.5 million kilometer. But Solar Parker probe has gone very close to the sun with a distance of 6.4 million kilometer. So Solar Parker probe have seen the sun closely, it has touched the sun, they say, because they have gone inside the corona. So the other point to study the sun is L1, and our mission Aditya L1 is at L1. Since Aditya L1 is at L1 and Aditya mission, the sun mission, all the solar missions and all the missions at L1 becomes important for your prelims. There were other missions before. I have noted just important one. If you go just to the Wikipedia page, you'll find a whole list of column. There are many missions, there have been many decommissioned missions, there are other minor missions running from here. I'm just giving you the major one. There are dozens of missions at L1. One is SOHO mission, Solar and Heliospheric Observatory. The SOHO mission of NASA and European Space Agency. It's there from 1995. It's a flagship solar observatory of NASA. ACE, Advanced Composition Explorer. Composition Explorer. Composition of what? Composition of what is coming from the sun. What's there in the solar wind and what's there in the coronal mass ejection, what is there in the solar energetic particles. So that Composition Explorer, ACE mission, that's also there at L1. Discover mission, Discover is a primary real-time solar wind monitor. This is the solar weather forecaster, that is also at L1. And there are other agencies of US involved in the Discover mission. Aditya L1 is at L1. There's a mission called as Genesis. You must know this. Genesis mission is an old mission, but this was a sample collector mission. Collected samples of solar wind particles from L1 and returned them to Earth. You know, because Chandrayaan 4 is set the agenda of the sample return from the moon, I have a list of all the major sample return missions. In that list, Genesis will appear again. Genesis is a sample return mission, and it took the sample from the solar wind particles and brought it to the Earth. So it's an important mission. All these missions at L1 you have to sit down and memorize. After the session, you can download the PPT from the comments, from the pinned comment in the link. I'll give the link for this. In that section, you'll have a link. Please download it. There'll also be this is the PPT format. There'll also be in the PDF format that you can get a printout and study. Sun has been studied by Solar Parker probe, and 6.4 was the plan, but I think it has gone now to 6.2. 6.2 million kilometer. This has been the latest beyond the planned 24 contacts. It has gone closer to 6.2 million kilometer. This close to the sun. This is very close. Sun is 150 million kilometer from us. So going to 6.2 million that's too close, very close to the sun. Okay, but it is not an orbiter. It's not going continuously. It is not at this distance. It is a highly elliptical orbit. So this distance comes only in a short duration here. If this is the sun and corona, for a very short duration, it is at this distance. For much of it, it will be far away from it, and then again for a very short duration. That's how it is. That's how it was designed. This is a solar observatory, a solar orbiter of European Space Agency and NASA. See, at L1, if this is the sun, this is the earth, and here we have L1. At L1, you can have 24/7 study of the sun from L1. But what you cannot properly study is the polar regions. Polar regions can be best studied from above the pole. From L1, you can study this region properly, the equatorial region, but the polar region cannot be studied properly. So they had a solar orbiter for that purpose, and they provided the high resolution image of sun's poles, because sun's poles cannot be studied properly at L1. You have to take care of it. That will be one of the disadvantage of keeping the observatories at L1. Sun can be also studied from the low Earth orbit. We have talked about this also in the beginning of the session. And there are important missions in the low Earth orbit that you must be aware. Hinode, this is of JAXA, and NASA is also there, and UK is also there. This is in Leo, studies the sun, magnetic field. But the problem is, in the Leo, you cannot be observing the sun 24/7. It will be eclipsed. When you go behind the sun will get eclipsed. So that's a problem, but that's okay. That's okay. Not continuously, but nevertheless, you can study it from the low Earth orbit. IRIS interface region, imaging spectrograph. Interface region, which is the interface region? That region from where the temperature starts to increase all of a sudden. It focuses on chromosphere, then transition region, and then corona, where there is a mysterious interface between sun's surface, photosphere, and its million-degree corona. So in photosphere, in the sun's surface as we call it, the temperature is 5500 degrees Celsius. And then in corona it jumps to millions. So what's between the sun's surface and corona, that's what they're calling as interface. Interface region imaging spectrograph, IRIS, is an important mission of NASA. And they have tried to work it out very hard for a very long time as to why there is coronal heating, why the temperatures start to increase. But a final answer of this we haven't reached to yet, even after Solar Parker probe. That has provided a lot of data that will be analyzed for years, a lot of images. But we have not reached to the final answer as of now. There is a TRACE mission that's also in Leo, and that gives high resolution imaging of the coronal magnetic loops. Fermi telescope. See, Fermi telescope is working in gamma region, gamma rays. There are very few telescope that works in the region of gamma rays. Fermi telescope is one of them. And the difference between the solar flare and the coronal mass ejection, as we have talked about earlier, is that these are radiations, and the coronal mass ejection has particles. They will have elements, they will have ions. But solar flares is radiation, and they are high energy radiation. So much of it, a bulk of it, will be gamma rays. So if you cannot study in gamma rays, that means you cannot study solar flares properly. So to study solar flares, you have to get the gamma rays telescope, and that is the Fermi telescope, that is in Leo. You have to know these important sun solar missions in Leo. Okay. Now there's a section in the notes that is not very current affair, but they are engineering marvels. These are some important things. They could be also very old, but these are important things. Some of them I'll discuss, rest of it you can read yourself from the notes. Like having an international space station. Having an international space station was a no mean feat. To achieve it was not an easy task. Having an international space station, there were modules sent in parts, and then they were rotating around the Earth at a high speed, at very high speed, to bring them softly, nicely closer and assemble them. It's not on Earth, and everything is moving at crazy velocity in Leo, sending them in bits and pieces, and then assembling them, and then having it run, having International Space Station run for so many years. That's no mean feat. So you had the supplies there and the astronauts coming and going, and without any accident you have done it, and without any major incident, rather minor ones have happened, you have done it. Not a mean thing to achieve. Another feat humanity has achieved in space technology is James Webb Telescope. We'll talk about James Webb Telescope as a separate topic, so I'll not do much of the talking here, but you know already that James Webb Telescope is at L2. It is at L2. The previous most powerful telescope before James Webb Telescope was the Hubble Telescope. The Hubble Telescope is in Leo. But the reason why the James Webb Telescope has to be sent to L2, we'll talk about that in a short while. Solar Parker Probe, touching the sun, 4.2 million kilometer, getting inside the corona. That's not an easy task. That's a very intricate design that has made it possible. Previously, the closest approach was 43 million kilometer through a flyby. 43 million kilometer was the closest approach. This has gone to 6.2 million kilometer. This is Voyager 1 and 2. You might have heard of it. Voyagers 1 and 2. For 47 years, the mission is on. 47 years. And they have entered into the interstellar space. You might have seen the movie Interstellar. Interstellar is between the two solar systems. Between the two solar systems. Interstellar space. It has gone beyond our solar system, Voyager 1 and 2. So they have gone so far. And you know what? They still communicate. They still send the information. And for this long, no batteries can survive. For this long, no amount of fuel can survive. For this long, the energy comes from the nuclear energy. It comes from plutonium-238. Plutonium-238 has a very long half-life. Very long. Unlike uranium. So that's why plutonium is chosen, because plutonium gradually disintegrates. And with its slow disintegration, controlled amount of energy is released. And that thermal energy, heat energy, when the energy is released, it's released in the form of heat. Even in the nuclear power plant, released in the form of heat. Then using the heat, you convert the water into steam, and steam runs the turbine. Turbines run the generator. Generator generates electricity. That's what happens. So you require what? You require electricity to charge the battery. So there's a technology called as RTG, radioisotope thermoelectric generators. Thermo means thermal energy is heat energy, thermal radiation. Thermo is for heat, heat into electric energy. This is what it does. So the heat is coming from a radioisotope, a radioactive material. In this case, it is plutonium. So radioisotope thermoelectric generator. So it's an electric generator, and it converts the thermal energy into electric energy. So RTGs is a common term. It's there in other space missions as well. RTGs are used for long endurance space missions. And RTGs there in Voyager 1 and 2, and they still communicate. It's crazy that for 47 years the communication from Voyager 1 and 2 is still active even when they have gone to interstellar space. Perseverance is one of the major missions of NASA. It's a Mars mission. Perseverance is the rover. The previous rover was Curiosity, and Perseverance rover is the main rover on space. It's still in Mars. It's still active. We have sent rovers under Chandrayaan 3 to the moon, but for Mars we have an orbiter, MOM mission, Mars orbiter mission. We have an orbiter, but on Mars we don't have our lander and rover. In the future maybe we will have, but they have a rover. NASA has a rover, and the rover name is Perseverance. And this is a fantastic thing. This is one of the best that they have achieved in the recent time. We are planning for a SUV sized rover in Chandrayaan 5, I told you, drilling 1.5 meter deep. A huge rover. So H3 rocket of Japan will launch it because it will be huge. They already have a huge rover on Mars. What we are planning for Moon, they already have it for Mars. A huge rover of the size of SUV with sophisticated testing instruments to conduct the in situ experiments. And one of the experiment it has conducted is called as MOXIE. MOXIE experiment, oxygen production from CO2. You know, the Mars atmosphere is thin. It's quite thin. In that thin atmosphere, it's there will be two problems. One is the resources are less. 95% by composition, the atmosphere of Mars is CO2. Although CO2 is there, but it is thin, so it is very less dense. Nevertheless, they have tried to develop oxygen from CO2. From CO2, you can break it down and develop CO and oxygen. So, it can develop CO plus half oxygen. So, oxygen can be produced from CO2, and CO2 95% by composition. The atmosphere of Mars is carbon dioxide. So, not a problem. In the future, if you are serious about it, if Elon Musk plan ever will be materialized and permanent human stay can be made, then this will be required. How many oxygen cylinders will we take from the earth? It has to be done that we produce oxygen there itself. So that testing has been done and has been successfully completed, and that was the MOXIE instrument that converted the CO2 into oxygen and CO. And there are other things. Sample also has been collected, and Perseverance carries the sample from the surface of Mars. But another mission NASA is planning to bring the sample collected by the Perseverance rover back on the Earth. Sample return mission has not been done from Mars till now. They have a rover, this is the highest that we have come to on the Mars. But sample return from the moon has been done, from other comets and asteroids has been done, from the solar wind has been done. From the Mars, we don't have any sample return mission. But perhaps they will bring the sample that already has been collected and is there with the Perseverance rover. There's also something that they achieved in the same mission. In the mission that sent Perseverance rover with the MOXIE instrument and other advanced instruments, they also sent Ingenuity. Ingenuity is the name of the helicopter. And that helicopter that was there in the atmosphere of the Mars. Mars atmosphere is very thin. It is 1% as dense as Earth's atmosphere. Martian atmosphere is very thin. But Ingenuity was a small helicopter. If you see the picture of Ingenuity on Google, it's a very small helicopter. And for the first time, we have flown a helicopter outside the atmosphere of the Earth. The other planets also have atmosphere. Some have very dense atmosphere and very crazy atmosphere like Venus, very acidic atmosphere. But never ever we have flown helicopter outside the atmosphere of the Earth. Ingenuity was the first time. It was ingenious. It was ingenious design, and 72 times it has done the flight. In the 73rd it crashed. The blade broke because the terrain is difficult. If you have a rover and a difficult terrain comes, then if you can fly and cross over, that will be better. Remember, for Chandrayaan 3 also we have done a hopping experiment. Hopping is also to crossing over the hurdle, and they tried for it. Maybe in the future, if it is possible in some way, to, although the atmosphere is very thin, so very heavy helicopter will never be able to hover in that thin atmosphere, but maybe for some transportation, maybe some drones, lighter drones, they can be running there. So testing has been done, and it was also a successful test of a helicopter in the Martian atmosphere. Name was Ingenuity. The Falcon 9 and Starship, these are the strong launch vehicles. Starship is the major launch vehicle of SpaceX. They are also reusable launch vehicles. Falcon 9 was partially reusable. SpaceX will also be, SpaceX, a version of SpaceX will be fully reusable. And I would say that's also an engineering marvel. So I have this also in the list of space science. This is not a mean thing to achieve. This will make space tourism possible. This will make a permanent lunar post possible. This will make it possible. That's why they have been able to launch 4,200 satellites. That's their plan. In the Starlink program, 4,200 it's not an easy thing to launch satellites. Very expensive actually. Very expensive to launch a satellite. And you have so many of them, and charges 3,000 per month of your internet service in Indian currency. That's the estimated cost when the Starlink satellite services will come here, the internet based services. Installation cost of course will be there of 30,000 one time installation cost, but monthly rental will be estimated as 3,000. That's too cheap. If we have developed the infrastructure with 4,200 satellites, then that's very cheap, and that has been done because of the reusable feature of the rocket. Otherwise things would have been very expensive, and to give services like this would not have been possible. Hubble telescope was the most powerful telescope of the world up till James Webb. Hubble telescope is in Leo, and the Saturn V rocket was a very well known rocket, the rocket that took Apollo mission to the moon. Titan-Huygens lander, first and only landing on a moon in the outer solar system. Saturn's moon Titan landing has been done. That was the Huygens mission. And of course our Chandrayaan 3. Chandrayaan 3 has been the first mission to launch, to land, have a soft landing on the lunar south pole. Chandrayaan 3. So that's also a engineering marvel that ISRO has achieved. These, I just gave you a list of the important achievements. You can just do reading. They are not from current affairs, but LISA Pathfinder and the Rosetta mission and the Mars Reconnaissance Orbiter and the Artemis 1 that we have done. Event Horizon Telescope, Hayabusa 2, Venera program. These are the other important mentions. I did not keep it in that list, but these are also important missions that will not hurt you if you read about them and know. But they are not from current affairs, so I am skipping it, but you can please read that. Now, James Webb Space Telescope. This is an important thing that I need to explain to you. James Webb Space Telescope. This is the most powerful telescope currently in the world. And how is the power decided for a telescope? A telescope's power is decided by its ability to look into the deeper part of the universe. So the further away that you can see, more powerful the telescope is. That's how we judge the power of the telescope. So James Webb Telescope can see further away in the universe compared to Hubble telescope. Now it will take me I think at least 5 minutes to help you understand why James Webb Telescope can see further away in the space and why Hubble telescope couldn't see. And then another thing you have to understand is, if Hubble telescope was in low Earth orbit, Leo, then why can't we have James Webb also in Leo? Why James Webb has to go to L2? Why you cannot have a more powerful telescope from Leo? Okay, more powerful telescope cannot be from Leo. As powerful as it could be, we already had, that was Hubble, and that's the best we can get from Leo. To go to make a more powerful telescope, meaning to see even further in the universe, it cannot be done from Leo. It has to be done from L2. Why? That we have to understand why. So allow me some time. Let me do a little build up for the concept so that we can really understand the why part. Okay. This is how the electromagnetic wave is classified into these 7 categories. The wave with higher frequency, that's gamma ray, and the electromagnetic wave with lower frequency, the lowest in this classification is the radio wave. If you see here, the frequency is high. When the waves are very close spaced, the frequency is high. Here the waves are not close spaced, meaning the wavelength is higher. The peak to peak distance, that's the wavelength, that is more. Wavelength is more, then the frequency is less. Peak to peak distance is less, so wavelength is less, frequency is more. Frequency is how fast it is coming. Suppose you have a receiver. You have a receiver and it receives this, and after this there will be a lag, then the receiver will receive this and then this. A receiver is receiving the wave slowly. So then the frequency of reception is less. So frequency is less of wave of this kind. But here if you have a receiver, it will be receiving the wave very fast. So in 1 unit of time, you will have more number of peaks entering through the receiver. In the same unit of time, you have less number of peaks entering the receiver. So frequency is how fast it is coming, meaning one wave packet, how quickly it comes. In 1 second, how many packets comes. That is frequency. So in same unit of time, more packets will enter here than this. Why? Because speed is same. Speed of all the electromagnetic waves are same. I hope you know that. That is the speed of light. Speed of light is c. What is this? What is c? Speed of light. What is light? Light is the visible range in the entire electromagnetic wave that is visible to us. We can't see infrared. Infrared is everywhere. You know the cameras, the infrared based cameras that detect presence of a person? Because waves are everything. Any object will be emitting all the time. All the time. Emission is coming all the time. So the whole space is filled with infrared. We can't see it. We can't see radio waves. We can't see microwaves. We can't see ultra. We cannot see anything apart from this narrow band in the electromagnetic wave. That's how our rod cells and cone cells are designed. That's how our eyes are designed. That's how our optic nerves and brains are designed. It cannot process signal. Everything is coming to the eye. Infrared is there in the environment, could be falling on the eye. It's not picked up by the nerves. Nothing happens. We don't feel it. We feel, and our instrument, our brain, our optic nerves, our cells in the eye, they are designed only to work in a very narrow frequency. Like any instrument, any electrical circuit is designed to work in a narrow frequency range. Our eyes are also designed in a narrow frequency range. So the design of our system, that range is called as the visible range. That we call as light. And the entire electromagnetic wave is very broad, and that could be from gamma rays. High frequency means high energy. Energy is directly proportional to frequency. So gamma rays, they are having high energy, they are high frequency. Radio waves are also all over, because the satellites use radio waves, the telecommunication tower use radio waves. Very close to radio wave and microwave, the Wi-Fi use microwave. When you communicate with the phone, it connects with the telecommunication tower. The phone is emitting in the range near to the microwave and radio wave. So it is also filled. The whole space is filled with radio waves and microwaves because of all the instrumentations that we have around us. So, but we can't see in that, we can't feel it. It doesn't have impact on our instruments, our eyes or our skin. Radio waves is not harmful. It doesn't impact us. Our body is transparent to radio waves, almost transparent. So this is how it is. This is the general classification of things. Okay. So their side high energy, this side low energy, and there will be special use of all of them. For example, for communication we use radio wave, in Wi-Fi, in satellite to satellite communication, in mobile to telecommunication towers communication, telecommunication tower communication, we use microwaves, right? If the telecommunication tower has to communicate with the satellite, it uses radio waves. So the ground station communicating with the satellite, it uses radio waves. For communication purpose, we use radio waves because radio waves are having low frequency. And when I was teaching you NISAR, I taught you that higher frequencies have high scattering, high diffusion. So the loss is more if frequency is higher. So if we have to communicate, we have to send signal to long distance. And in long distance, it will attenuate. If the frequency is high, it cannot go long distance. It cannot simply travel through atmosphere. It will get absorbed, scattered, diffused. So the receiver will not get it. To send something long distance, we have to use radio waves. So for communication, radio waves and microwaves are used. For pattern recognition, for persons recognition, for, the cameras can detect animals also, birds as well, for a burglar as well, a thievian as well. At night, if the infrared camera detects a person, it will send you the alarm. The screen will splash and the person's captured image will be shown, or the video will be shown there. How do they know? How do they know that the person has come, a human has come, or an animal has come? There are ranges for emission, and human body, just like earth, just like any other material, just like the animals and the birds, they emit in infrared. But ranges are different. Human body will emit in an infrared region with a little different frequency than animal of body of another animal. Outside the camera, in the outside there are concretes, they are also emitting. A doormat is also emitting. Plants also emitting. But ranges are slightly different for everything. I told you the range depends, emission range depends on chemical composition, and chemical composition of the doormat or the concrete or the human body or the animal body slightly different. Animal body and human body, concrete and human body very different. So the camera that is calibrated for a particular range, maybe some animals or maybe some humans, it is for that. So it works because infrared is used in cameras. Infrared is used in border management. Those cameras detecting the transgressors, that is there in infrared cameras. So it has a purpose. All the remotes, they use infrared. They use infrareds. The remotes, they send signal so that the device understands something, and that signal is sent through infrared. The TV remotes, in the car remote, these days we have remotes in washing machine and fan, all work in infrared. Visible, that's how we know the world, that's how we see the world, and there are many applications of visible as well. Ultraviolet is used as a disinfectant. It kills the microbes. So purify water, ultraviolet radiations are used. Ultraviolet radiation is used in the lithography, manufacturation of the semiconductor chips at nanoscale it is, and you have to do the circuit design, cannot be done with the physical instrument, has to be done with light. So ultraviolet has a purpose. X-rays, all of us at some point might have had our X-rays done. X-rays can be used for medical purpose to find the cracks in the bones. X-rays can be used to find the cracks in the concretes as well. So if there's a density difference, muscles allow it, bones doesn't allow. Crack in the bone will allow. If it's not crack in the bone, it won't allow. So the crack in the bone can be identified, fractures identified through the X-rays. Crack in the concrete can be identified through X-rays. X-rays can also be used for sterilization. The bacteria and microbes in the food, X-rays are passed through it, and so they get killed, and the medium becomes sterile. Gamma rays have more energy. Gamma rays are very the highest energy is gamma rays. So that can be used for the functions quite similar to the X-rays. So these are the basic things you already know. What I had to tell you here is this: red shifting. So it will take me some time. You have to be a little patient and just hear me out, and gradually you will understand things. Just patiently hear me. You know, there is a term called as cosmic microwave background radiation. Cosmic microwave background radiation, and it was discovered accidentally. Accidentally so happened that a physicist was trying to observe the universe using the telescope, and in whichever direction he would put the telescope, he will see that some microwaves are being detected. I told you ground-based telescopes that work in microwave and radio wave. So there's some signal of microwave is being detected. Wherever, in whichever direction. Now, he initially thought that there's some calibration error. He checked and rechecked and triple checked and quadruple checked it and checked it multiple times, and then he came to the conclusion the instrument is fine. There's no problem with the instrument. And if the result is that there is some same intensity of the microwave around in the space throughout, then that's the fact. There are microwaves in the same intensity around. So that's why they call as background radiation, because whatever the direction you are pointing your telescope to, it does not matter. In each direction and every direction, it is just the same. That's the point. If it is just the same, then the direction is not deciding the intensity. Direction ought to decide, because suppose the radiation is coming from a particular star. So if I am directing my telescope, I am getting it. If I am changing the angle, it is reducing. If I change the angle, it becomes 0. So if the radiation is coming from outer world, then the direction always is important. This was the intuition of the physicist as well, astrophysicist. The direction is important for observation, but here there's a peculiar observation that regardless of the direction, in whichever direction you pointed out, it's the same. Now that's very curiously interesting. How is that possible? If it's same everywhere, that means there is a 360-degree symmetry. And you know what? 360-degree symmetry comes from a point source. If you have a charge as a point source, then there is a 360-degree symmetry in its field. Like there's a 360-degree symmetry for a perfectly sphere mass of like Earth. Earth is not a perfect sphere, so there's no symmetry. Like there's slight variation in gravitational pull from the pole to the equator, but there's a pull on all sides because there's a central mass. 360 degrees symmetry means a point source. So if there is cosmic microwave background radiation, this was the first proof of the Big Bang. This was the first proof of Big Bang. Why? Because the Big Bang theory theorizes that everything came from the point source. And before the Big Bang, there was singularity. From this point source, all things from the universe has come from this point source. The equation of Einstein, E is equal to mc square. And according to this equation, energy can convert into mass with this equation. Mass can convert into energy and energy can convert into mass. So all the mass that we have in the universe was not existing. Because all the mass cannot be packed into a point source, there was energy nevertheless. Energy can be packed. Energy was packed and then there was a bang. A big bang. And then energy got converted into mass, and that's how mass came into existence from this equation, E is equal to mc square. So after the Big Bang, mass came into being. So when you have an intense event, Big Bang, when you have black hole collision, there are high energy radiations. When you have neutron star collision, there's high energy radiation. Big Bang, they are nothing compared to Big Bang. These events are nothing compared to Big Bang. It was the most intense event perhaps in the history of formation of solar system. Not perhaps, it was indeed the most intense astronomical events. So if there's such an intense event, then there ought to be high energy radiations, and radiations came in that moment. And when the universe expanded, those radiations filled the space all around. But they all started from a point source, and that's why there is a symmetry. So existence of symmetrical background radiation shows that the origin of universe is from the point source. Had it not been the case, then there wouldn't have been a perfect symmetry. At whichever direction you see, you always see these microwaves. It's not possible. Perfect symmetry is possible only with a point source. So this is the first proof of the Big Bang. Alright, now the question is that it was an intense event, so much of the energy must be coming in the X-rays and gamma rays. So why do we have microwave as background radiation? If this was such an intense event will call for gamma rays and X-rays, correct? Gamma rays and X-rays, but microwave has lower energy. And this lower energy, why the lower energy radiation is filling the universe? Event was intense. So X-rays and gamma rays must be filling up the universe. Why microwaves? This background radiation is microwave, not X-rays or gamma rays. Now that is the last leg of our understanding, and this will clear up everything. It is microwave because of a phenomena called as redshifting. Redshifting. Now what is redshifting? Let's understand what is redshifting, and then the pieces will be joined and the larger picture will be visible. Redshifting. Redshifting is a phenomena where the wave, there's a phenomena called as Doppler effect. You might have heard of Doppler effect. If you have done your science in your class 11th, then definitely in this chapter of sound you must have done Doppler effect. I'm not quite sure if it was there in class 10th as well. But Doppler effect, if you have heard of the Doppler effect, you must have experienced this for real in your life. Suppose there's an ambulance or there's a police vehicle with a siren. When the vehicle is approaching you, suppose from the right, the vehicle is approaching you, it's very hard on your ears. That sound the pitch is very high. So it seems very uncomfortable on the ear when the vehicle is approaching you. When the vehicle passes by, all of a sudden, the ear gets the comfort. The vehicle has not gone too far away. The distance of the vehicle that it was on the right when your ear was uncomfortable, and now when it is on your left when the ear is comfortable, is almost same distance. It's not about the distance, but the comfort is different when the vehicle is approaching you compared to the vehicle is receding from you. The reason is that suppose you are standing here and suppose there's an ambulance and there's a hooter, the siren. when the vehicle is approaching you and the sound wave is also approaching you, sound wave and the vehicle velocity, that is in the same direction. So both the source of the wave and the wave, they are moving in the same direction. But once the ambulance, suppose, crosses by, so the vehicle is going away from you, but since the sound is coming to you, so sound wave is coming towards you, sound wave is going in all direction, but the sound wave approaching you, let's represent it like this. The wave is in this direction, but the vehicle is in this direction. When it's approaching you, the wave and the vehicle is in the same direction. It's not about the distance here, it's about the direction of the wave and the source of the wave. So when the wave, whether the sound wave or the light wave, when the wave source is moving, then we have a phenomena called as Doppler effect leading to red shifting in the case of light. So what happens is when the wave comes out and the vehicle also is moving, it's kind of what happens is a little complex, but the effect is like as if the vehicle is pushing these waves together and getting it and squeezing it. If it is getting squeezed, suppose the wave is like this, having spaces, it gets squeezed, it becomes of high frequency, right? It becomes high frequency. But if the vehicle is moving away, then it gets stretched. If these part of the wave, I stretch it, imagine them to be made up of wire, if I stretch them, then they become like this, they become of lower frequency. So since the vehicle was coming towards you, if we say that, that will not be proper language of science, but the vehicle will squeeze the sound wave, so the frequency will increase. That's why the pitch is high, it's difficult on your ears. But when the vehicle is receding away from you, then the pitch is less, because vehicle is moving in the opposite direction to the direction of sound. Sound is going in that direction, but vehicle is receding, is kind of as if it is stretching apart them. So it's stretching apart, then the frequency decreases, the wavelength increases. You getting it? You getting it? This phenomena is in light called as red shifting. Red shifting has nothing to do with the color red, nothing to do with color red. But in our world, the visible part of the electromagnetic wave that we can see, the red color has more frequency or the violet color has more frequency. Which one has more frequency, red or violet? Can you tell me that? Which color has higher frequency? Well, frequency, you can see red is towards infrared. This side, frequency is decreasing. So red will have lower frequency, and in VIBGYOR the violet will have higher frequency. So the higher frequency is in gamma ray, then X-ray, then ultraviolet, and it is connected to violet. Ultraviolet will have even higher frequency than violet. Infrared will have even lower frequency than red, but red has lower frequency than violet. So if the frequency decreases, then these light will go towards red. They all are waves, they all are electric field and magnetic field, nothing else. It's the frequency that makes it appear. It's the interpretation of the color cells in the eye, the rods and the cones that make it appear like red or white, but they are just magnetic fields and electric fields. It's the frequency that is creating this illusion in us that something is this color and that color. Color, nothing exists. It's just the wave that exists, nothing else. It's the interpretation of the brain that makes the world to us appear like this. The world is not like this, the way it appears to us. It's the rod cells and the cone cells and the optic nerves and largely the interpretation of the brain that makes us see colors. Colors, it's just the wave, nothing else. There's no color in this world. It's the brain that makes us see the color. It's all wave with different frequency, that's it. If you decrease the frequency of the wave, you're shifting towards red. So red shifting is because if the frequency decreases in our world, the waves having lower frequency is red color. So red shifting refers to stretching up of the wave or decreasing the frequency of the wave. Red shifting has nothing to do with red color, it's just a form of naming it, because the red color has lower frequency. So red shifting, if the frequency decreases, then that is red shifting. When will the frequency decrease? If the source of the wave is approaching us, then frequency increases. If the source of the wave is receding from us, then the frequency decreases. And the source of the light wave, they are coming closer or they are all going far away. After Big Bang, universe is expanding. So all the sources are going away from us. So we are in this scenario when the ambulance is going away from us. So then red shifting will happen and the frequency will decrease. So now that will complete the story. What's the story? The story of Big Bang is this, that before Big Bang there was singularity and then there was a Big Bang. And in that Big Bang, energy got converted into mass and mass came into existence in this universe. And after Big Bang, there is expansion and there is more and more expansion. Up till 1980s, we thought, you know what, that after Big Bang, universe is expanding. At some point, it will lose the steam, it will slow down and under the pull of gravity, it will come back. But now we understand it's never gonna come back. Never gonna come back. Universe is not only expanding, it is acceleratingly expanding. You know that, right? Universe is expanding more in any moment compared to the previous moment. The amount with which universe expanded yesterday, today it will expand more. Tomorrow even more, day after even more, day after even more. More and more and more. Now what is the driver of it? Driver of it is dark energy. Dark energy. You know, in the theory of Einstein, in the theory of relativity, it was there that space has its own characteristic. This is the result of Einstein's theory of relativity, that space has its own characteristic. What is space? Space is that region that was created after singularity. After Big Bang, you know, the particles, nebula, all that developed and then became concrete and then moon and the sun and the earth and everything. But it expanded. So space that is created after this expansion, that we call as space. This is our space. There was no space before Big Bang. Our space is this. It expands more, more space is created. Expands more, more space is created. So the space is not empty. Oh my God, no, it's not empty. It is created after intense event. And the mark of that event will be there everywhere. Space is not empty. So Einstein suggested that space will have its own characteristic because of this. And of course it has. We think that there is air, and if you remove the air, there is vacuum. What's in the vacuum? Nothing. In school books, this is what we have studied. There is emptiness in the vacuum, nothingness in the vacuum, because we can't touch and feel. Our instruments can't touch and feel. So we declare that there is nothing there. That's what we call as vacuum. Vacuum doesn't have nothing. It has many things. It has thousands of things. It's not just the air molecule that fills the space. There are subatomic particles. There are neutrinos there. We have learned to detect neutrinos recently. Previously, neutrinos also were going undetected. Now, since we are detecting, so we are ruling them out, so that neutrinos can still be there. But if you remove neutrinos also, then we think that's space. No, that's not space. There are things that we have not learned to detect, and there are thousands of them. Sun has discovered thousands of subatomic particles, and it's all filled everywhere. We are in an ocean. Imagine living inside the ocean, water everywhere. Like for a fish, it's in a medium and it's all around, it's all over. We think that we are in air, a thin medium. This is not a thin medium, this is a very thick medium because it's highly densely packed. There are too much of the subatomic particles, but it's too light, they're too light, they doesn't interact with us, so we do not know about it. But we are living in the ocean of particles and nothing is empty. Space is filled with these particles. Space has its own characteristic called as, now we are calling, we do not understand it though, so we're calling it dark energy and dark matter. So, you know, universe is expanding, but the distance between the sun and the earth doesn't increase. Distance between sun and the earth and everything in the solar system, that does not change. So how is it expanding then? Expansion is between galaxies. You know, the space between two galaxies, this will increase. Whatever is within the galaxy, that does not change. So what binds things within the galaxy is dark matter, and what pushes them out is dark energy. So dark energy is the characteristic of space. So when the Big Bang happened and space got created, dark energy came into being, and dark energy has a characteristic of being anti-gravity. So on the normal matter, it has an influence of anti-gravity. So it pushes, like gravity pulls, it pushes. It's a repulsive, although it as though it acts like a repulsive force. So because of dark energy, there will be expansion. Expansion will create more space. More space will create more dark energy, because dark energy is a characteristic of space. More dark energy meaning more anti-gravity force. So more expansion, more space, more dark energy, more expansion, more dark energy, more expansion, more space, more dark energy, more expansion. It is never gonna come back. The more it expands, the more it creates force to expand. So it expands more. So universe is expanding and acceleratingly expanding. All right. So there is redshifting, and so redshifting, so the rays, the X-rays and gamma rays, they have expanded and become microwave. Universe has developed that speed. You know, because of force, it is accelerating and velocity is more. So the speed with which it is moving is increasing and increasing. In the early stage of universe, if the speed was less, so gamma rays will convert into X-rays and X-rays into ultraviolet, suppose. So life cannot come in this stage of universe formation when the universe is filled with these high radiations. And with expansion, there will be higher speed, then more redshifting. Redshifting depends upon the velocity of the source. So more redshifting and more redshifting, so the background radiations have come to this microwave, and now the life can survive. So the life begins after billions of years after the Big Bang. After Big Bang, you cannot have life. These conditions are not met early. So that's the point. So now you complete it, the understanding. Background radiation means symmetry. Symmetry means point source origin. Point source origins, Big Bang. Big Bang means high energy. High energy is X-rays and gamma rays. But X-rays and gamma rays converted into microwaves. Why? Because of redshifting. So this is a cosmic microwave background radiation. That is the complete understanding. Okay. So this explains some part. But we started this whole thing to understand James Webb Space Telescope. So what's the matter then with James Webb Space Telescope? Why is it at L2? Now finally I have to explain you that. To understand that, you already have understood that universe is expanding, and the stars that we study, they are not stationary, they are moving, and if they are moving, then they will cause red shifting, correct? So suppose there are two stars, this is Earth and there is a star S1, and further away there is a star S2. So which star is moving faster, S1 or S2? In your view, which star is moving faster? Can you tell me, S1 or S2? The one that is further away is moving faster. Why? One which is at the periphery, closer to the outer space, will be always faster because there will be more dark energy for S2, and there will be this much of dark energy for S1. So more repulsive force for S2. The further away something in the universe, faster it is moving. That's the idea. Further away, faster. So S2 is moving faster than S1. So you want to study the stars, they are moving at different speed. Further away, higher speed. Higher speed, more redshifting. More redshifting, less frequency. Less frequency, and bulk of it will come into infrared category. If you are further away, S3. Further away, higher speed. Higher speed, more redshifting. More red shifting, maybe they come in microwaves. So further away, more speed, more speed, more red shifting, more red shifting, maybe it will come in the radio waves. So the thing is that we cannot see very far in the universe. If we attempt to see very far in the universe, then the radiation starts to be redshifted, and when the radiation starts to be redshifted, then bulk of it come here in the infrared region. That is why James Webb telescope has to study them in the infrared region. Now you understand that. James Webb Space Telescope is not interested in X-rays and gamma rays. Why? Because you are studying the further part of the universe, and further part of the universe will be moving at higher velocity. You understand that, because of more dark energy, more repulsion. So higher the velocity, they don't have them. They don't have them. What they have is the red shifted version of them. So they have these, they have the infrared. So when that is infrared, then you have to study them in infrared. That's why the powerful telescopes, they study in the infrared region. All right. Now the infrared also is divided into near infrared, the region closer to the visible range, that is called as near infrared, and then far infrared. Near infrared and far infrared. Now the star that is further away, that will have more red shifting. So the star that is further away will study in far infrared, correct? You have to study that in far infrared. The star that is closer by will be less red shifted, and many of them will be near infrared. So the Hubble telescope studied in near infrared. So it cannot see far away. If you have to see far away, you have to study in far infrared. But then there's a problem. To study in far infrared, there's a problem. Far infrared will have lower energy because we are moving in that direction. Far infrared energy will be less. And this is called as thermal radiation. And this is the radiation in which the Earth also emits. This is the range. The emission from the Earth is in far infrared. So if you're on the ground, can you study the deeper part of universe? Answer is no, because the deeper part of universe can be studied from far infrared. And if you're on the ground, then Earth is also emitting in the far infrared. And then there will be interference. You cannot study. So where do you go? You go away from the Earth. You go away from the Earth. So where do you go? You go to Leo first. Hubble telescope went to Leo. But the Hubble telescope studied in near infrared. Hubble telescope also did not study in far infrared because there will be some influence of the radiations coming out from the Earth in Leo as well. So Leo is also not a very good place to study the radiations in far infrared. So now where to go? Go far away from Earth. Go 1.5 million kilometers from Earth. Go to L2. At L2, you're substantially away from the Earth to cause any major interference. So Earth emits in far infrared, but far infrared is the region that is required to study the deeper part of universe. So the deeper part of universe cannot be studied from the Leo or the surface of the Earth. It has to be studied in the same region of the electromagnetic wave in which Earth is emitting. So you have to be away from the Earth. So you have to go to L2. That's why James Webb Space Telescope is not more powerful, because it is bigger. The aperture is bigger. That's not the only reason. The instrument works in far infrared, and that cannot be done from the ground. That cannot be done from Leo. So it has to go to L2. No doubt aperture is bigger. Aperture indeed is bigger. But that's not the only deal here. The deal here is you have to avoid the interference from the emission from the Earth. That's the deal. You understand? So James Webb has to go to L2. I just had to tell you this, and everything we discussed is to bring you here on this point, why it can be done only from L2. But in the mid, we have understood other things, and I believe you must have picked many of it, and those understanding will help you overall be comfortable with this section of the chapter. So you see here, James Webb Space Telescope, this studies in infrared, not in X-rays, not in gamma rays, infrared. That's the reason. That is the reason. All right. If you have questions, you keep on asking, but I'm explaining things as much as I feel is important. Then Europa Clipper. There are two important space missions study the moon of the Jupiter. Moons, there are many moons of Jupiter, but initially the 4 moons were recognized. They are called as Galilean moon. They are Io, Europa, Ganymede, and Callisto. 4 Galilean moon of Jupiter, and they're big and they're icy. These Galilean moons of Jupiter's, they're icy. It is said that the best place to look for life in our solar system, the best place to look for life apart from Earth is Ganymede. See, Ganymede, Europa, Callisto, and Io. They are the 4 moons, and these 3 of them, they have subsurface oceans, icy subsurface oceans, not in liquid form, but in icy form, subsurface oceans. So they are holding up perhaps some life beneath them. It is said that the best place to search for life is Ganymede. For Ganymede, you have to know, Ganymede is the only moon with own magnetic field. Do you know that the moon of the Earth, does that have or that does not have its own magnetic field? Do you know? Earth has a magnetic field. Magnetic field protects us from the solar wind. Solar energetic particles, they come and they put a lot of pressure. Atmosphere will be washed out by those winds. So those winds have to be stopped. Otherwise you cannot have atmosphere. Moon doesn't have atmosphere. Moon doesn't have atmosphere because it doesn't have magnetic fields. To have atmosphere, the prerequisite is that you have magnetic fields. So you create a protecting layer around the Earth, and then by some decomposition process, fumes will come out, gases will come out. So, and then in the process, those gases will change its composition in billions of years. You will have your correct atmosphere. Like Earth initially had nitrogen, and through the lightning process, gradually in billions of years, many of the nitrogen was changed into oxygen, and then the photosynthesis began and this and that. So, but whatever is happening, to contain it, you need a protective layer. That protective layer was the magnetic field lines of the Earth. Moon doesn't have it. Atmosphere never developed on Moon. Mars has the atmosphere, but I just told you Mars atmosphere is very thin. It's just 1% dense compared to the atmosphere of Earth. So thin because magnetic field lines are weak there. Very weak magnetic field lines. It is not because of as a bar magnetic field lines, as very symmetrical magnetic field lines like the Earth. Mars doesn't have that. Since it doesn't have that, nevertheless it has some magnetic field lines, so it is managing to maintain some atmosphere. Atmosphere is not dense because the magnetic field lines are weak. Okay, Ganymede, our moon doesn't have it. Ganymede is actually the only moon with its own magnetic field. Now what it does is, you can have an orbiter because the magnetic field lines are there. See, the mission of European Space Agency, JUICE mission, Jupiter Icy Moon Explorer. This JUICE mission is an orbiter. This is of ESA, European Space Agency. Europa Clipper is of NASA. This JUICE mission is for Ganymede. It will orbit Ganymede, one of the moon of Jupiter. Europa is also the moon of the Jupiter, and the mission for Europa is that of NASA, and mission for Ganymede is that of European Space Agency. NASA's mission is not an orbiter. You have to take a very good note of it. This is not an orbiter. What is it? It's a flyby. Meaning what? The Solar Parker probe, which was a flyby, will come in a close contact and then leave that area pretty soon. Come in a close contact and then leave the area pretty soon. Will not stay there for long. Will not stay there for very long because it will get burnt, because the environment around Jupiter is very intense. The rotation, it is also very fast moving planet. It has the highest rotational speed, and because of the fast moving things, the plasma around it, there's strong magnetic field lines, and there are temperatures, very intense temperature around it. So you cannot have an orbiter around Europa, the moons of Jupiter. You cannot have an orbiter. But you can manage to have an orbiter around Ganymede, because Ganymede provides protection around itself. That is why the mission for Ganymede is an orbiter, but the mission for Europa, that's a flyby. That's not an orbiter. This you have to keep in mind. So the Europa Clipper of NASA flyby. The JUICE mission of European Space Agency is an orbiter. All right. China's Tiangong spacecraft. You know, the International Space Station that did not include China. International Space Station has 5 agencies. USA is NASA and USSR. So Russia was also there. European Space Agency is there, and JAXA is there, and Canadian Space Agency is there. These 5 space agencies, they have worked together to develop the International Space Station. China was excluded, although NASA wanted some collaboration, but there was a bill that was introduced in the Congress to bar entry of China. China was excluded from this mission. Then China developed its own, and the space station of China is Tiangong. It's a smaller compared to International Space Station. Nevertheless, it is run alone by China. So this was in news recently, because in one of the return flight from their space station Tiangong, there was a debris that hit the capsule, and the capsule had to go back to their space station. So this is important. This is important because the debris has started to affect the human space missions, the human flights as well. So in the near future, if we want these things to not get escalated and maintain the safety of astronauts, you have to do something about the debris. And debris collection program, the space agencies must begin. Like European Space Agency is taking a lead in this, and they have a CLIP mission having a robotic arms to catch the debris and will remove it. Either you can bring it down, or you can take it up. You know, above the navigation satellites, there's a graveyard orbit where you can keep it so that it will not interfere with your launch as well, because you're launching most of the satellites are low Earth orbits, and at that height you have more space as well. That in the future that will also cause problem, because if you have too many debris in the graveyard, then how would you go above that in the geostationary orbits? It will create problem. It will. But that is a simpler solution, that removing debris from LEO, taking it up and placing it there. So much of the satellites which are in the LEO, they will get clearance from the debris. Or you bring it back then. That's more expensive, but you do that. You bring it back. So it has to be done. That becomes a major issue. Tianwen 2 was an asteroid sample return program from a comet of China. Tianwen 3, China's Mars sample return mission. This is important. We haven't had sample return mission from Mars yet. Perseverance rover, I told you, is holding the sample. It is holding the sample, and NASA is planning for a sample return mission to send a mission and bring it back, the sample collected by Perseverance rover. And that perhaps will be in 2029. But in 2028, according to the timeline declared by China, in 2028, China will complete its Mars sample return mission. That will be Tianwen 3. This is very important. You have to know this very well. Tianwen 4 is going to be their Jupiter space program. Now, sample return mission. Our Chandrayaan 4 is a planned sample return mission from the moon. So this becomes important for your exam. So I have given you a list of important sample return missions. You must go through it, memorize them. Apollo program was the first sample return mission. First and only human collected sample return mission, because they landed on moon and they brought 382 kg of lunar rocks and soil. That was a huge amount of sample return mission. The first sample return mission, the only human sample return mission. Lunar series was of USSR, and Luna was not a human landing. The sample return missions was not, and Luna, that was a robotic sample return mission, the Luna series, and Luna 24 brought 170 gram of the lunar material. But that was the second sample return mission. Stardust program of NASA brought it from comet. First comet, interstellar dust return, less than 1 milligram, because the density decreases there, right? So it managed to bring around 1 milligram of the interstellar dust, the stardust. Everything is important because they will jumble it up. Something from current affairs and something from very static legacy information. You have to be aware of that. Genesis, we have done this. Genesis was the program that we did towards the end of the table for programs at L1. Genesis is at L1. Solar wind particle was collected and brought back. So it is also a sample return mission. Hayabusa is the first asteroid sample return mission from an asteroid. Asteroids also move at crazy velocity. Asteroids moving, you have to land, have a soft landing on it, then hook up to it, then do drilling, collect the sample, unhook and come back. Not an easy thing. We haven't had any asteroid mission like this. ISRO so far hasn't done it. It was a very complex mission, and the first asteroid sample return mission was done by JAXA. Remember, these are super important informations. Then the second, Hayabusa 2, was done on asteroid Ryugu. Hayabusa 2 was a second asteroid sample return mission. Then NASA did its sample asteroid sample return mission, the Oryx Rex mission. The name of the asteroid was Bennu, and they also got it, but JAXA got it first. You have to take note of everything. Chang'e 5, we have done Chang'e 5, it was also a sample return mission, and this was from the moon, from the near side of the moon. Chang'e 6, also sample return mission from the far side of the moon. And we haven't had sample return mission from Mars. It will be a complex mission. But Perseverance rover has cached samples for future fetch. In the future, NASA is planning around 2029 to 2030s to get the sample. But China's timeline is 2028. So Perseverance mission has it. But you have to send another module to bring it back. There's no ascender module there. So it was all lander. It landed, from there it can communicate, but it can't bring it back. Now they are planning to extend the mission by adding another module to bring it back. So it's going to be their complex mission. It has to go very close to the Perseverance rover, and the handshake between them, so that a transfer of sample will happen, then ascend from the Mars, and then again the transfer orbit and re-entry will be very complex when NASA plans it. They have in plan, but the execution hasn't begun. Okay, Outer Space Treaty. Outer Space Treaty is the foundational space law, and there is no weapon of mass destruction allowed within the Outer Space Treaty. There is no sovereignty claim on any of the celestial bodies. Like we say Chanda Mama, like we may think that moon is ours, we can lay claim that they are our mama, Chanda Mama, but sample return mission we haven't had from there, and the one who can have the sample return mission, the resources belong to that country. Artemis program, they are planning for a permanent outpost on the moon. Like who will give you the right? How do you decide that you can claim this part, you will make some post there? You can't do that on Earth, right? You can't say I'll have a post. You have to take permission from the sovereign countries if you're doing in their waters, or you cannot have a claim on international waters. You cannot have claim on Antarctica. But if US is making a permanent post and they're capturing the areas of South Pole, so is there a governance rule? How will you control the resources that will be brought? There are rare earth elements there, and there is helium-3 there. We are running into nuclear fusion testing. In the future, maybe helium-3 will be used as a fuel for nuclear fusion. So you're bringing all the resources back. Will you only use, will you distribute? Because resources doesn't belong to one person. So how the governance of lunar governance will be done, it's not very clear. When we start to find resources in the asteroids and we bring it back, to whom will it belong? And can you lay claim that this region of the moon is yours? यहाँ पे entrance नहीं है किसी का, And you can say that South Pole, this region is mine, and you will go and lay the US flag there and start to mark the region. This belongs to US, because China and Russia are also planning to have an outpost there. So where the China and Russia will have the outpost, where the US will have outpost, that's going to create problem. And very elaborately, the governance rules are not clear. So it says this far that you cannot lay sovereignty claim, you cannot have the weapon of mass destruction, but both of them are about to get violated. Weapon of mass destruction they have taken to space, and when we start the defense chapter, we'll see at some point there, weapon of mass destruction has been taken there. You know what? Satellites can destroy satellites. Satellites can in the laser beam and can destroy the electronics of another satellite, a co-orbital satellite. Then it's done. If the electronics of the satellite is gone, it cannot communicate. It just will become a debris in the space. So that's a weapon. That's a weapon that you have taken. Weapon, China also has tested something called as fractional orbital bombardment system, FOBS. When we start the defense, we'll start from the missiles and we'll see Agni 5 and Agni 6 and this and that and their ranges. So how far the missile can go. You know, this has dissolved the concept of range of missiles. Missiles can go anywhere, from anywhere, because they are in space and they can deorbit. And they can launch anywhere. Any point they can deorbit and attack. So the whole earth is the range, and they have done this testing. That's clear violation of the outer space treaty, but they have done this. They have done the testing of striking from a missile a satellite. Satellites are very nearby, right? 600, 800 kilometer. Missiles have ranges, crazy range. Avangard of Russia has a range 14,000 kilometer. Kinzhal has 17,000 kilometer. These are the ranges of the missiles, 17,000 kilometer. Satellites are very nearby. You can strike a satellite and bring it down. And India also has done it under Mission Shakti, called as ASAT, anti-satellite capability, ASAT. So you can strike down the satellite from the missile, and they are doing all these stuff. China did it in 2013. So we were also forced to develop such a capability. We started to work from 2016, and we had Mission Shakti. We conducted it in 2019. We also showed capability that we have the capacity to strike down a satellite. Satellite is very essential. For any guided missile, you have to communicate with the satellite. For military operations, you require satellites, images, communications, and if those are brought down, then there's not much that you can do then. You cannot have a guided missile. But outer space treaty prohibits such a thing. Weapons should not be taken to space, but weapons have gone into space. Sovereignty claim should not be laid on celestial bodies, but seems like the Artemis Accord, an aggressive program of the Artemis program to have a permanent lunar post, both for Russia and China in one group, and US is trying that. It seems like they're going to lay sovereignty claim on the moon. So the governance architecture of the space is lagging behind. Things are happening at rapid pace, but these are old treaties, they have not been updated. You know, moon treaty, there's a moon treaty that was signed by major powers, spacefaring countries in 1979. But the major powers have signed it, but not ratified. India also has not ratified. US, Russia, China, India, none of them have ratified it. Perhaps the reason, why it has not been ratified, because they knew one day they'll go and they'll bring back the resource. So they don't want to be bound by this treaty. That is why US has opened up Artemis Accord. They don't want to work under the aegis of UN, because if a convention, a declaration, a treaty comes under UN, it will be democratic. It will be the welfare for the whole humans. So they will have claims like no weapon allowed and no sovereignty claim. But you want that. You want that. So they're trying to work out of the aegis of UN and having bilateral agreements on these issues. All right. The governance architecture of our space ecosystem is like this. We have a policy, space, major umbrella thing is the space policy that came in 2023. And in 2023, when this policy came, that completely deregularized the space sector. There is nothing in the space sector that the private companies cannot do. Nothing. Previously, the private sectors, they were making some sensors, some equipments, were contributing in the satellite development of ISRO, right? But gradually they were nurtured, they were skilled, and they were given technologies. A lot of technology transfer has been done from ISRO. So the thing is that now they are grown up and now they do many things and they have been allowed to do many things. Like they can make the satellite, they can make the launch vehicle as well. They can launch their own satellite with their own launch vehicles, and they can also give satellite based services. In fact, many of the startups have started to give satellite based services from remote sensing satellites. You want a clear image of your house, your farmhouse, this field or that field, this area, that area. For your insurance claim, for a crop insurance claim, you want a clear image, you want something, they'll give you very clear images. These services have begun. So it has been years, 2-3 years since the space sector has been deregularized, and in US also they have done it. Nurturing of private sector has to be done. See, we are talking about sample return missions. We haven't had asteroid sample return missions. We are having a planned lunar sample return missions. We have to send a lander on Mars. We have to do deep space study. We have to send missions on Venus. We haven't sent mission on Venus yet. We have to go to the interstellar space. Now, how long will ISRO keep on doing this remote sensing activity? Remote sensing, navigation, these are now not that high-end things. The private sector should be given opportunity, and ISRO now should focus on a high-end thing. So remote sensing satellites and weather forecast, much of the weather forecast in US is done by private companies. Much of it. These things has to be handed over. Two things will happen. Private sector will grow, ecosystem of science and research will develop, and ISRO can focus on higher end things in the space exploration. This is how the government does. In the area that government builds up, it opens up. Like railway, government has opened up. Nuclear, government has opened up. Biotechnology, government has opened up. Who developed it first? Government. That is what is happening in space as well. So they have in space, this is a single window authorization for private sectors. It's a regulatory body in space. NSIL is a commercial arm. So for example, if the private sector has to launch the satellite, it has to talk to the commercial arm of the space sector, that is NSIL. The thing to do with technology and the thing to do with money, that is done by NSIL. So who will get the slot in Sriharikota? A private sector company, Pixel or Skyroot maybe. They want a slot in Sriharikota for launching. We have only one spaceport, so management of that spaceport and getting into agreements and launching the satellites of the other countries, all of that, giving technology to the private sector, that is done by NSIL. So, and the regulatory body, that is in space. That's how it is. Okay, there are many companies coming up. Previously, there were hardly 8 to 10 startups in space. In last 12-13 years, the number has gone to 150 plus. Skyroot, Agnikul, Pixel, Dhruv Space, Digantara, they are the popular. Agnikul and Skyroot are the big shots. They are really big shots. They are into manufacturing satellites, they are into manufacturing engines, they are into manufacturing of launch vehicles. Pixel gives you the services of satellite imageries, clear pictures. Dhruv Space is into both. These are major activities, major and substantial startups from India. Microprocessors, when we see ICT next week, that will be possible. ICT, we'll see that we are a little weak in this area of development of that we can say semiconductor chips in normal parlance, or the microprocessors. We have started to design the microprocessors, 32-bit microprocessors, Vikram and Kalpana, and more recently Dhruv 64, the first indigenous 64-bit core processor. We didn't have this earlier. You know, we are completely dependent in microprocessors for space, even for defense, for missiles, for nuclear power plants. We do not have our microprocessors, and more discussion on this we'll do next week in the chapter of ICT. But advancement in these are required for sovereignty in space. We have done very well, exceedingly well in launch of satellites. In the launching vehicles, our PSLV has exceedingly good record. So the thing is that, but that's not complete sovereignty. Unless you have microprocessors, and there could be a backdoor that those suppliers can enter into our system through these microprocessors, because we procure their microprocessors. So for complete sovereignty, it is important that we have the one of our own. You know, there's an announcement that the GS Foundation P2I batch will start very soon, and there's a discount on the occasion of Holi, 55% discount that will end on 6th of March. So if you're interested, you can check up the further details and avail the benefit of the discount. Now we'll do some questions. Some questions based upon what we have studied so far. So I have tried very hard, not that very hard, but I did try enough, I think, to explain things to you. And let's see how much you have got, and you try to give answer of these in the comment section. With reference to space docking experiment, consider the following statements. India became the 4th country to achieve a satellite docking in space after USA, Russia and China. That's right, that's right. In many of the things, India will be 4th number, and this India is 4th. US, Russia and China, they have done it earlier. The statement is right. The mission was launched using LVM-3, Launch Vehicle Mark III. Well, I brought this to your attention that the docking experiment is done in LEO, and for LEO, PSLV is good enough. LVM-3 is a more powerful rocket, so it will be an over design for something that has to be sent to LEO. So it was PSLV and not LVM-3. So this statement is false. The technology demonstrated is essential for future space operations and Chandrayaan 4. Of course, you understand so much of docking required in Chandrayaan 4. So 2 statements here are correct. All right. The answer would be B, and you can be proactive to give your answers. Consider the following regarding Lagrange points and their applications. L1 will have James Webb Space Telescope. L2 will have Aditya L1. That's so bad. Aditya L1, the name carries L1, so it has to be at L1. This is wrong. And James Webb, that will be at L2, so this is also wrong. And L4 and L5, Trojan asteroids accumulate here. Of course, I've told you they are very stable. They are stable equilibrium at L4 and L5, and unstable at L1 and L2 and also L3. Highly unstable at L3. So L1 and L2 are unstable equilibrium. Remember that. I'm repeating it because I feel like it's an important thing you have to know. L4 and L5, they are stable equilibrium. So only one, right? With reference to Gaganyaan program, consider the following statements. It uses human rated LVM-3 and CE-20 cryogenic engine. The statement is right, but let's get to the answer, then I'll do a little discussion on the cryogenic engine. ECLSS, this module that maintains the carbon dioxide level and oxygen level and humidity and temperature level, maintains oxygen, CO2 removal, temperature, humidity for the crew. We have done this is also right. India will become the 3rd country for indigenous human space flight capacity. In most things, India will be the 4th one, and in this as well, India will be the 4th one. So this statement will be incorrect, that India will be the 3rd country. And 1 and 2 are right. Answer will be A. Cryogenic engine. This is the name of the engine, CE-20. There is also CE-15. So this is GSLV Mark III, now called as LVM-3. And in GSLV Mark II, we have CE-15. Okay, so this is the most powerful engine that we have, and we will use our most powerful engine because the payload in the human space mission will be high because of the humans there and also because of the other safety features. So of course LVM-3 will be used. This statement is right. There will be special mechanism to keep humans in healthy condition. This is also right. Cryogenic engine. Now, why cryogenic engine? Cryogenic engine is something that we have got after huge amount of struggle. Initially, Russia was ready to give it, but then under the pressure of US, it did not want to unnecessarily start its diplomatic relation back then with US. It did not give us. Then we had to develop on our own. And cryogenic engine is a pathway for space exploration. If we do not have cryogenic engine, then we cannot have heavier satellites sent into the space. We cannot have major missions like Gaganyaan missions. So it was an important key for the major space missions, cryogenic engine. Now let me tell you a little bit. You might already be knowing about it, but let me tell you a little bit as to why. Why do we need cryogenic engine? Why? We need cryogenic engine because cryogenic, you understand, this deals with materials at low temperature. When you study any material at very low temperature, that's called as cryogenic engineering. Cryogenic low temperature, so low that oxygen and hydrogen are in liquid state. So in cryogenic engine, you have liquid hydrogen as the fuel and you have liquid oxygen as the oxidizer. So when they are in liquid form, then their density enhances, and we also have a control on the engine. So you require compact. There will be compact fuel, and since they are dense, so you require little of them. Otherwise, you see the LPG cylinder, how big it is. If you have the CNG gas, the cylinder for that is also quite big. But if you liquidize it, then you can have a more compact arrangement. If you can liquidize it. So liquid hydrogen and liquid oxygen are more compact. They are more compact meaning they are light. And they are light meaning the weight of the satellite could be more, because rest of the arrangement of the launch vehicle is lighter. So your actual weight that you are launching the satellite could be more. If the rocket is itself heavy because of other parts, then engine has to carry its own parts, meaning rocket itself has to be taken up, and that itself is a task. And over and above we have satellites. So satellites weight couldn't go initially beyond a certain range. Currently also we have 8 tons in LEO, 130 tons in SLS of NASA, we have 8 tons. So depends upon the power of the engine, and one important way and a clever way to increase that is to make it lighter, and you make it lighter through cryogenic technology. So that's why it was so important. Otherwise initially we were sending only polar satellites, remote sensing satellites, and we are using PSLV. PSLV was our first launch vehicle. We required cryogenic to make GSLV so that we can make heavier satellites, communication satellites, and send it to GEO. Alright, so this is an indigenous technology and we have developed it on our own. Statement 1 is it is the first dual frequency radar imaging satellite jointly developed by NASA and ISRO. So this is in the context of NISAR. I have told you this is the first dual frequency radar imaging satellite. Absolutely correct. It is based upon advanced SAR technology, so it is very sensitive, very sensitive. The range, dear, 0.4 inch. It can study something of that size, any motion of 0.4 inch. So ice getting thinner in Antarctic, so easy. Build up. You might have done something as morphing in geography, that bending of the surface because of stress, and perhaps that's the early sign of the earthquake coming in the future when the pressure builds up. So warping, you might have done that term. You can do that, and the corrosion, the erosion of the coastal surface, if it is receding, 0.4 inch of movement you can see, the receding coastal surface you can see. So the rise of mountain you can study, erosion of mountain you can study teeny beeny changes on earth. That is very crucial in many aspects. So very powerful. NISAR is an important mission. L band is provided by ISRO and S band is provided by NASA. And for this day I had told you that be cautious, be very cautious. S band is provided by ISRO. They have interchanged here, this is not a PYQ, I have interchanged here, this is wrong. So if this is wrong, then the answer would be C, correct? With reference to rocket propulsion system, let's do this. With reference to Chandrayaan 3 mission, consider the following system. LIBS instrument provided the first in situ confirmation of surface at lunar south pole. That is absolutely correct, because there is nobody at the lunar south pole except us. We are the only one there. So who will give the confirmation? We. So we have given that. This is right. This is the first in situ. They have an orbiter and they do the reading from the orbiter, but that's not in situ. That's not from the surface. So the first in situ confirmation of sulfur, it's not that sulfur has not been identified. They have orbiters since ages, and much bulk of the study has been done by the orbiter. But this is the first in situ. First in situ confirmation of sulfur, and that has been done by one of the payload in Chandrayaan 3, one of the instrument there. This is correct, absolutely correct, important for you to know. India became the first country to land on the lunar south pole region. Yes, that point is now called as Shiv Shakti point, absolutely correct. Vikram lander performed a hop experiment after landing. Of course, Vikram lander performed the hop experiment. So how many of those? All three are correct. Answer will be C, correct? Am I going fine? Am I going fine? You have to tell me, am I? Consider the following space missions and their objective. Europa Clipper, study Jupiter's moon for subsurface ocean and potential habitability. That's right. And it will go to one of the moon of Jupiter, that is Europa. European Space Agency's mission JUICE, first spacecraft to orbit Ganymede. That is right. And it will orbit Ganymede. This will not orbit Europa. This will fly by around Europa. NASA Dragonfly, rotorcraft mission to Saturn's moon Titan. This will be somewhere in the notes if you read, and please download it from the link in the video. And this is also right. This is also right. So a rotorcraft mission to Saturn's moon Titan, NASA Dragonfly. All the three statements here are correct. Consider the following statements regarding India's space policy reform. InSpace provides a single window authorization for private sector participation. InSpace is the regulatory body, correct, that will give the authorization. NSIL is the commercial arm handling satellite launches and technology transfer. That is also right. Space Policy 2023 allows private companies for end-to-end space mission. That is also right. The space sector altogether has been completely deregularized. Deregularized meaning no license is required. Now end-to-end you can participate without special permissions. There will be some like you're allowed to do business, but still labor registration has to be done, and you have to get the permission from the pollution control board to run the chimneys. That obviously will be there, but there is no entry barrier. I mean, anybody doing these things can enter into industry and do business, correct? Anybody can have a manufacturing unit. So you have allowed private sector in these areas traditionally since ages, but in space you did not allow. Now you have allowed it. That's deregularization, but some norms still will be there. So answer, all three here are correct. Answer should be D. Which one of the following best describes Kessler syndrome in the context of space activities? We might experience it, you know, if we are not awakened and if we are not serious about it, if we do not work on it properly, then we might experience it. A cascading collision scenario where space debris creates more debris, making orbits unusable. So there's so much of crowding. One collision will lead to many more collisions because they are so nearby, and things can be very random because they are moving at crazy velocity. So if we do not manage space debris, it's going to become real. With reference to NASA's Artemis program, consider the following statements. SpaceX Starship will serve as a human landing system for Artemis 3. Yes. SLS space launch system will launch from Earth. Then from the orbit of the moon, the descent will happen in the Starship of SpaceX. This is correct, very important. NASA's Gateway is a lunar space station planned from Artemis 4 onward. Yes, lunar space station. It will be a space station on the moon, permanent outpost. That will be there in Artemis 4. That is also right. India signed the Artemis Accord in 2023. That is also right. India has finally signed it. We are now the member of Artemis Accord, and we need to do more diplomacy for much more technology transfer in space sector because of this. NISAR is showed the collaboration between ISRO and NASA, but we need more technology. We need more technology from them, and more diplomacy must be carried out after becoming the member of NISAR. Some joint missions, like we are having Chandrayaan 5. Chandrayaan 5 we are having with JAXA. Some major Mars mission, major lunar mission with NASA. That will be better. NISAR is what? NISAR is what? NISAR is a satellite. Major missions we have not get into NASA. We didn't have a combined mission of NASA and ISRO for the lunar missions or Mars mission. They do not help that much. But since we have become the member of the Artemis Accord, now we must draw more concessions from them. Nevertheless, all the three statements are right. Answer should be C. Consider the following statements regarding Exposat. Exposat is India's first and world's second dedicated X-ray polarimetry mission. And that's absolutely right. That's absolutely right. X-ray polarimetry helps in studying the magnetic field structure and emission mechanism of celestial objects like black holes and neutron stars. Well, polarimetry, I told you, this became a little technical statement. UPSC is less likely to ask it, but polarimetry uses polarization as a technique to study about the source material. So, studying the magnetic field structure and emission mechanism of the source like black holes and neutron stars, this statement is absolutely right. So, we need polarimeter, but polarization you can do of any wave, X-rays or visible, you can do that for infrared as well. We want X-rays, and the reason for X-rays is that these intense events and these bodies will emit in the higher energy radiation, and since they will emit in the higher energy radiation, so we require X-ray polarimeter. So polarimeter in general is to understand about the source of the radiation, and X-ray polarimeter, that is especially for celestial bodies involving high energy. Okay, with reference to China's Chang'e program, consider the following statements. Chang'e 6 achieved the world's first far-side sample return mission. Absolutely correct. Quickao 2 relay satellite enables communication with the far side. Far side mein when we go, we have to go through a relay satellite. Without the relay satellite, we cannot go to the far side. Absolutely correct statement. An international lunar research station is a China-Russia led joint initiative. Like you have Artemis 4, to compete with Artemis 4, they're having their own, they're planning their own lunar outpost, lunar missions. And that is also right. They have named it as International Lunar Research Stations. That is absolutely right. So please go through these questions. There will be more questions in the file that you will get hold of. Practice them, and through questions you will learn the important statements. Through question you will learn the traps as well. Okay, so that brings us to the end of the first chapter, and I understand that it was a long session because space science is a big chapter. Next time I'm ending the session here. Instead of starting defense, anyway we had to end till 4, but instead of starting defense, the discussion would not continue. So I'll start defense next Sunday, and next Sunday will be a little more quick, and we'll do it in an expeditious way. Today I wanted to bring down the concepts. Many of the concepts we did will be continued in the next chapter of defense as well. And looking at the condition of the world from yesterday, that chapter will be very, very relevant. So that will be more interesting, more fun. So please join again next week at the same time, 10 a.m. Thank you very much for being so participative.